Hello everyone and God bless you. Welcome to this new course of real analysis where we're going to discuss different aspects of calculus through straightforward exercise while referring to the theory whenever needed. So we're going to cover almost everything about calculus, proving an assumption, a theorem, an equality, all of that. So it is deep real analysis going to cover different subjects such as continuity, integrals, derivatives, differentials, all of what you could think of. Okay, so let's get started. Chapter 1, Foundations of Mathematical Analysis. The following exercises here are designed to reinforce the foundational concepts of real analysis developed in this module. Each problem is accompanied by a detailed solution and explanation emphasizing rigorous mathematical reasoning. Topics covered include properties of real numbers, absolute values, inequalities, suprema and infima, which is the highest boundary and the lowest bound of a function, sequences, completeness, convergence, monotone sequences, and Cauchy sequences. Exercise 1. Absolute value inequality. Problem: prove that for all real numbers x, y within R, within the spectrum of real numbers, the following inequality holds, which is x plus y, an absolute value, is less than or equal to x, absolute value of x, plus absolute value of y. Okay, you can think about it and try to solve it yourself before we get to the solution. This inequality is called the triangle inequality. We begin with the fact that x squared, x absolute value of x squared is equal to x squared. Okay? Now, for every real number, we consider absolute value of x plus y squared. Then, now, we know that anything squared would be always positive. So, the absolute value of x plus y squared is equal to actually x plus y squared. Let's expand. So x plus y squared is equal to x squared plus 2xy plus y squared. Now we know that for 2xy is less than or equal to 2 times absolute value of x times absolute value of y. Why? This is given the fact that either x would be negative here or y would be negative. So this product would always be less than or equal to, in its best condition, so to speak, in the best circumstances, 2xy would be equal to 2 multiplied by absolute value of x and absolute value of y. So, hence, we obtain that x squared plus 2xy plus y squared is always less than or equal to x squared. Now here, for anything squared, no need for the absolute value because it's already positive. Plus 2 times absolute value of x times absolute value of y plus y squared. You see, here is what or where we can encounter a negative value. 2 multiplied by x times y, which is this criteria here, because either x is negative or y is negative. But meanwhile, here for the second part, everything is positive because you have absolute values. Thus, we can for sure propose that x plus y in absolute value squared is definitely less than or equal to x absolute value plus y absolute value squared. You see? Why? Because here, both of them are positive. So definitely it's going to be all positive. But meanwhile, here x plus y, because absolute value of x is positive, absolute value of y is positive, but x plus y squared, one of them can be negative, despite the fact that the entire sum is an absolute value, it should be positive, right? So, since both sides are non-negative, taking square roots gives x plus y is always less than or equal to x absolute value plus y absolute value. Because here, either one can be negative, but to the right, definitely both of them are positive. That's why it is less than or equal to the second side, the side to the right. Hence, we had proven that x plus y in absolute value is less than or equal to x absolute value plus y in absolute value. In case we flew over this side note a little bit quickly, you need to pay attention that x squared plus 2xy plus y squared is equivalent to x plus y in absolute value square. So it is the same thing. But meanwhile, x squared plus 2 times absolute value x times absolute value of y plus y squared is the same thing as if saying x in absolute value plus y in absolute value squared. Why? This is given due to the fact that in this case, everything here above would be positive. So you can definitely rewrite it as x plus y, both of them, each one of them in absolute value squared. But to the left, x or y might be negative, though the sum is in absolute value, okay? Since it is squared, it's definitely positive, even without having to write these pipes here, these absolute value markers. Reverse triangle inequality show that absolute value of the absolute value of x minus absolute value of y is less than or equal to absolute value of x minus y. Now this is interesting, okay? For all x and y within or amongst the real numbers. Solution, starting from the triangle inequality. Alright, now, absolute value of x can be rewritten as equal to x minus y plus y in absolute value, correct? We simply subtracted and added y, so nothing truly changed within the equation. And still, everything was done within the absolute value boundaries. Now, let's apply the triangle inequality. So, absolute value of x is definitely less than or equal to x minus y in absolute value plus y in absolute value. Why? Because here, you see absolute value of x is definitely, by the way, both of them were equal here, correct? However, here absolute value of x, which is strictly positive, is less than or equal to x minus y in absolute value plus y in absolute value, correct? Given the fact that here you have the y, that would be negative, okay? So subtract y, meaning that this y over here, you move it to the left. So x in absolute value minus y in absolute value, we simply moved y from the right side to the left side, would become less than or equal to x minus y in absolute value. Interchanging x and y, meaning we simply flip x and y. Nothing changed. Nothing changes, okay? It's the same thing. So it's like as if we multiplied by minus the entire equation, but we haven't actually multiplied by minus. We simply swapped x and y. So what happens is, or what becomes of this is y in absolute value minus x in absolute value is less than or equal to x minus y in absolute value. A tiny thing I want to point at is y is absolute value of x is less than or equal to absolute value of x minus y plus y. And here is why. You see, absolute value of x is strictly positive. Meanwhile, you have here x minus y in absolute value, okay, plus y in absolute value, okay, so this is strictly positive, this is strictly positive. However, this component can either mean, which is absolute value of x minus y, it can either mean minus x plus y or plus x minus y. This can be either equal to minus x plus y or plus x minus y. That's the reason why x in absolute value would be less than or equal to this plus y. You see? In other words, we don't know which one is bigger than the other. That's why. Let's combine both inequalities. So you have minus x minus y in absolute value is less than or equal to x in absolute value minus y in absolute value less than or equal to absolute value of x minus y. Thus, you can say that the absolute value of absolute of x minus y is less than or equal to absolute value of x minus y. Supremum of a set, meaning it is the highest boundary of a set. Find the supremum and infimum, the lowest bound, of the following set, A equal to 1 over n, where n is among the natural number scope. N is a natural number. The natural numbers are, in other words, the numbers starting from 1, okay, all the way to infinity, without infinity being included. Infinity is not included, but it is all the positive numbers starting from 1 and going upwards. So, the set is the following. The set is A is equal to 1, 1 over 2, 1 over 3, all the way 1 over 4. It keeps growing, but actually, by the way, the limit goes to 0, because as 1 is being divided to larger and larger numbers, the limit goes to 0. However, it never reaches 0. So 0 is not part of the set. Meanwhile, the 1, which is 1 over 1, it is the maximum number that you can get. It is the highest bound, but it's also the maximum. Maximum means that the 1 is already actually included within the set. So the highest bound is part of the set itself, unlike for the case of 0. So 1 is within the set, right? It is part of the set. And every other element satisfies 1 over n divided over n is less than or equal to 1. Correct? So, in other words, the supremum of A is 1. This is the highest bound, but it's also the maximum. So, since 1 belongs to the set, it is also the maximum. As we mentioned, it is the highest bound, meaning it is the highest boundary that you can get, the highest number that you can ever get within this set. But this highest number, it's part of the set itself. This is why it's not only the maximum, it's not only the supremum, it's also the maximum. Let's determine the infimum, or the lower bound. So, the limit of 1 over n as n approaches infinity is equal to 0. It is the limit, correct? So 1 over n approaches 0. Now, all elements are positive, so 1 over n is always greater than 0, but it never actually gets to 0. It approaches 0. 0 is not part of the set. Hence, the lower boundary is 0, but it's not part of the minimum. It's not part of the set, so the minimum does not exist. No positive number can be lower bound because 1 over n can be made arbitrarily small. Therefore, inf A, so the infimum of A is equal to 0, which is the lower bound. However, 0 is not part of the set, so the set has no minimum. For bounded sequence, show that the sequence an equal n over n plus 1 is bounded. So let's examine the sequence at first. You have an is equal to n divided by n plus 1, correct? You can break it down into 1 minus 1 over n plus 1. We can rewrite it, which is very important, by the way. So it is equal to 1 minus 1 over n plus 1. Now, 1 minus 1 over n plus 1. We know that this part, which is n over n plus 1 is always positive given that n is a natural number. So this one is always greater than 0. Then the maximum number that you can get within this sequence is 1, because the other part is always decreasing. So as n approaches infinity, this approaches 0, this quotient here, but never actually gets to 0. Hence, an is always less than 1. It's never equal to 1, by the way. It's always less than 1. Hence, 1 is the highest bound, which is the supremum. Supremum of an is equal to 1. This is the maximum value that you can get, and it's not part of the set, meaning that you can never actually get an equal to 1 exactly because of this other factor, which is always positive. Even as much as it decays, it never gets to 0. It approaches 0, but never is equal to 0. Now, as for what is the minimum? The minimum value that you can get is when you have this second quotient is as close to 1 as possible. So when n is at its minimum, the minimum that n can get, since it's a natural number, is 1. So this is the minimum. The minimum equal to 1 minus 1 divided by 1 plus 1, which is 2. So 0.5, if we're considering that it's part of the natural number. Hence, now if n can be 0, you see, hence you can get 0, but n is never 0. Lowercase n is never 0. So, given that, the value that is the minimum that you can get is 0.5, and the lowest bound is 0. So an is always strictly greater than 0. And this is the upper and lower bounds. An is greater than 0, less than 1. 1 being the supremum, it's not part of the set, so there is no maximum for the set, and 0 being the infimum and also not a part of the set, as long as, or for every n belonging to the natural numbers. Thus, the sequence is bounded above by 1 and from below by 0, an greater than 0, less than 1. 5. Convergence of a sequence. Let's determine whether the sequence an equal 1 over n converges. What does it mean a sequence converges? It has a limit. Okay, it has a finite limit. So let's check out. First, we know that the limit is supposed to be equal to 0, because limit of 1 over n. As n approaches infinity, this becomes 1 over infinity tending to 0. But we have to prove it analytically. So it's not what you know, it is how to prove it. This is how to prove it. You see, we need to choose. This is, let's say, the function. For example, so we need to prove it by saying that as n approaches capital N, there exists a capital N value such as n should be greater than or equal to capital N in such a way that when lowercase n approaches n, then the limit, or 1 over n minus the limit, which is 0, is always less than epsilon, meaning that 1 over n, the actual limit, is so close to 0 that the value between them, or the gap between them, is so tiny as epsilon. So let me draw it again. Let's assume again this is the function. We're saying that as lowercase n approaches n, capital case N, okay, there always exists n is greater than whatever capital N would be. such as n approaches n, also the value of the function would approach its limit, which is 1 over n for whatever the value of n is, minus 0, which is the limit value, in this case 0. This difference is always less than epsilon, meaning that it's so tiny. So as n approaches capital N, the function approaches its limit. This is what we're saying. 1 over n in absolute value is equal to 1 over n without the absolute value. Both of them are strictly positive. Why? Given the fact that n is actually a natural number. So it's always positive. Now, choose capital N greater than 1 over epsilon. Okay, why is that? Why can we choose n like that? Okay, let me get back to the basics. You see, the formula was, or the assumption was 1 over n minus the limit, which is 0 in such case, is less than epsilon, correct? So 1, if we are going to choose lowercase n as capital N, 1 over capital N minus 0, which doesn't matter anymore, correct? This is an absolute value, but 0 is not even there. So 1 over n is less than epsilon. And we already know that lowercase n, or we've assumed lowercase n is greater than or equal to capital N. So now this one, you can flip it. If we get the inverse, you end up with capital N is greater than 1 over epsilon, correct? Capital N is greater than 1 over epsilon. But let me keep it like this. So you have 1 over n less than epsilon and lowercase n greater than equal to capital N. So we need to flip those two, and you end up with 1 over n is less than or equal to 1 over capital N. So you place here less than or equal to, okay, 1 over n, lowercase n, of course. Hence, 1 over lowercase n less than or equal to 1 over capital N less than epsilon. Hence, the limit of 1 over lowercase n as n approaches infinity is equal to 0. Why? Because we have met this criteria, this condition. Therefore, the sequence converges, and limit of 1 over n as n approaches infinity is equal to 0. Determine whether the sequence an equal to minus 1 to the power of n converges. What we notice over here is whenever n, which is a natural number, whenever n is even, meaning n modulo of 2 is equal to 0. In other words, if you divide n by 2, whenever it's even, the division would have a rest of 0. There would be no rest of the division. But meanwhile, if n is odd, is an odd number, n mod 2 would be different than 0. It would have a remainder. Anyways, whenever n is an even number, an would be equal to plus 1. But when n is an odd number, such as minus 1 to the power of 3, it will be equal to minus 1. So this is called an alternating series or sequence. Suppose the sequence converges to L. Then every subsequence must converge to the same limit. Consider a to n is equal to 1. Okay? Now consider a to n plus 1 is equal to minus 1. So it's never stable. It's never the same limit. Actually, there's no limit. It's alternating between plus 1 and minus 1. Thus, a to n plus 1 always equal to minus 1, and 1 different to minus 1. So since you have two values, you have no limit. Therefore, minus 1 to the power of n diverges, because it's always meteorizing, oscillating between two values. So it has no boundary, it has no limit, not boundary. It has no stable limit. So thus it diverges and not converges. Shows that an equal to 1 minus 1 over n is monotonically increasing. Now, one of the ways to prove that is simply to prove that an plus 1 minus an is always greater than 0. Or in other words, the next term is always greater than the previous term, which means that when you subtract the previous from the next, you get a positive value greater than 0. Let's compute an plus 1. An plus 1 is equal to 1 minus 1 divided by, instead of n, you place n plus 1. You replace every n within the equation by n plus 1. So equal to 1 minus 1 over n plus 1. Let's compare an plus 1 and an. We simply subtract them from each other. We remove an from an plus 1 to verify that the subtraction gives us a positive value, meaning that always the next term is greater than the previous one. So an plus 1 minus an is given by 1 minus 1 over n plus 1 minus 1 minus 1 over n. Let's simplify. So 1 over n minus 1 over n plus 1, because 1 is removed. N plus 1 is a common denominator, or multiplied by n actually. So you multiply here by n plus 1, here by n. You get 1 over n times n plus 1. Now n times n plus 1 is always strictly positive. Hence, you have an plus 1 minus an is always greater than 0, since 1 is greater than 0. Thus, an plus 1 greater than an. Hence, the sequence is monotonically increasing and an is always increasing. So that the sequence an equal 1 minus 1 over n converges. From the previous exercise, we know that 1 over n is ever decreasing, because as n increases, 1 over n goes all the way to 0, because n, as it approaches infinity, 1 over n decays. It approaches 0, but never actually gets to 0. Hence, an is always less than 1. 1 is the upper boundary, but it's never the maximum. Why? Because we never get to actually a value of 1. So 1 is not part of the set, because 1 over n approaches 0, but it is never 0. So as n increases, this second factor that's being subtracted from 1 decays all the way to 0, so an increases from a value that's very small all the way to 1, with its upper bound, but not the maximum, because it's not actually a value, but the upper bound or supremum would be 1. So monotonically increasing and bounded above by 1, but without a maximum. By the monotone convergence theorem, every bounded monotone sequence converges. Now, let's compute the limit, okay? So, since it's bounded, it definitely converges, because it has an upper limit. Upper bound is upper limit. So, whenever a function is bounded, it converges. Let's compute the limit. As n approaches infinity for 1 minus 1 over n, 1 minus 1 over n approaches 1, okay? Because the limit would be 0 for 1 over n. Hence, limit an as n approaches infinity is equal to plus 1, which is the upper bound. Now, by the way, it has a lower bound, which is for n equal 1, 0. That's the lower bound, and at the same time, it's the minimum. 0 is part of the set, because for n equal 1, an is strictly equal to 0. So not only a lower bound, but actually a minimum. An infimum and minimum, which is 0. Cauchy sequence. Show that the sequence an equal 1 over n is Cauchy. So what is a Cauchy sequence? For a sequence to be Cauchy, it should satisfy the following condition. For every epsilon greater than 0, epsilon being an infinitesimally small number, but still greater than 0, there exists capital N such that lowercase n are two numbers greater than equal to n. Hence, a of n minus a of m, which is the values of the function at n and m respectively, an minus am should be less than epsilon. So for these two numbers, the difference between n and m, which are the values that are greater than n, should be less than epsilon. Now we start from the premise 1 over n minus 1 over m, an absolute value, is definitely less than or equal to 1 over n plus 1 over m, because you have a minus here. Meanwhile, the other side is positive, correct? Here, this can mean either 1 over n minus 1 over m or minus 1 over n plus 1 over m. In both cases, you have a negative value, so it's less than or equal to 1 over n plus 1 over m. If m and n greater than or equal to capital N, then 1 over n minus 1 over m is less than or equal to, so you replace n and m by capital N to the right side, correct? Because m and n both are greater than or equal to capital N. So less than or equal to 1 over capital N plus 1 over capital N, which is equal to divided by n. We choose n greater than 2 over epsilon, correct? So basically, you place it like this. Let me get the pen. 2 over n is less than epsilon, correct? So if you switch n and epsilon, you get 2 over epsilon is less than n, or capital N is greater than 2 over epsilon, which is this premise. Hence, an minus am is less than epsilon. Why? Because n is greater than 2 over epsilon, correct? Which is correct. So this is how we choose n. When we choose it greater than 2 over epsilon, and we know it is greater than 2 over epsilon because epsilon is a tiny number, but n is a colossal number also. So n approaches 2 over epsilon. Hence, an minus am is less than epsilon, correct? So thus, 1 over n is Cauchy. Consider the intervals. In is equal to the bounded interval 0, 1 over n, with 0 and 1 over n are actually values that are included. They are not excluded. They are within the interval. They are part of it. Find intersect in from n equal to 1 all the way to infinity. The intervals are 0, 1, 0, 1 half, 0, 1 over 3, all the way to 0, 1 over n, where n is always greater than 0 because it is a natural value. Each interval shrinks towards 0 gradually. Never gets to 0, but it shrinks. Okay, a number x belongs to every interval if x is between 0 and 1 over n for all values of n. If x is greater than 0, choose n greater than 1 over x. Then 1 over n is less than x. So, if x is greater than 0, choose n greater than 1 over x, which is correct. So what does it mean, this premise? N greater than 1 over x, so you can say that x here is less than or equal to, okay, x, 1 over x, which is x, but this x here is always greater than this one, which is correct, and the overall is greater always than 0, so this is how you can go with it. contradicting x less than or equal to 1 over n. Thus, the only possible element would be 0. Okay, so hence, this range of 0 to 1 over n would be equal to 0. Archimedean property. Okay, so show that for every x within or amongst the real numbers, there exists n amongst the natural numbers such that n is greater than x. Suppose this were false, then there exists x belonging to the real numbers such that n is less than or equal to x for every n belonging to the natural numbers. For every n, there is always lowercase, for every natural number, there's always a lowercase n definitely less than or equal to x. So we need to prove that this is false for the first one, the first proposition to be true. This means x is an upper bound for n, but the natural numbers are unbounded in R. They are unbounded. This contradicts the completeness properties of the real numbers. Therefore, for whatever x within the real numbers, there exists n among the natural numbers such that n is greater than x. That's why. Okay? You see, this contradicts the completeness properties of the real numbers because the natural numbers are unbounded. They don't have a bound in the real numbers, among the real numbers. That's why we can say that there exists n within the natural numbers such as n is greater than x. Limit of a geometric sequence. Determine limit of 1 divided by 2 to the power of n as n approaches infinity. Let a n be equal to 1 divided by 2 or 1/2 to the power of n. Now, as n increases, this is a repeated multiplication of 1 over 2, which increases the denominator enormously while the numerator remains the same, which is 1, correct? It makes the sequence smaller. Let's claim limit of 1 over 2 to the power of n as n approaches infinity is equal to 0 and go back to the law of limits. Let epsilon, which is an infinitesimally small number, be greater than 0. So, very small, but still greater than 0. Strictly greater. We need 1 divided by 2 to the power of n less than epsilon. Let's take the logarithms of both sides. So, ln of 1 over 2 to the power of n is less than ln epsilon. Now, you know that n here we can multiply it behind the logarithm, so you get n ln 1 over 2 less than ln epsilon. Hence, of course, ln 1 over 2 is ln 1 minus ln 2, which is ln over a over b is equal ln a minus ln b. You know that. So, n times ln 1 minus ln 2 is less than ln epsilon. ln 1 is 0. We know that. So, minus n ln 2 is less than ln epsilon. Let's take this part to the top of the page and process it over there. So, if we multiply by minus, you need to flip the inequality, it becomes greater than. So, n times ln2 greater than ln epsilon. So, n ln2 greater than ln epsilon. N is greater than ln epsilon divided by ln2, which is fairly a great number. Why? Because ln epsilon is a very great number. Remember that ln 0 is equal to minus infinity, correct? So, n is sufficiently large which means that 1 over 2 to the power of n would multiply the denominator to an extent that 1 over 2 to the power of n becomes very small. But still, you know, it's like very small enough to be less than epsilon. Hence, the limit is correct. Limit of 1 over 2 to the power of n as n approaches infinity is equal to 0. Finally, at the end, these exercises illustrate several fundamental principles of real analysis. The structure of the real numbers, rigorous proofs using inequalities, supremum and infimum, formal convergence definitions, monotone sequences, Cauchy sequences, and completeness of R. Module 2. Here we're talking about, or we are analyzing topology of the real line. So these exercises reinforce the core concepts developed concerning topology of the real line. Problems focus on open and closed sets, neighborhoods, interior enclosure, boundary points, compactness, connectedness, Bolzano-Weierstrass theorem, HEINE-BOREL theorem, and each solution emphasizes rigorous mathematical reasoning and the logical structure of proofs used throughout real analysis. Open interval is an open set. Prove that the interval AB is an open subset of R. Of course, A and B are excluded from this interval. To prove that AB is open, we must show that every point inside the interval has a neighborhood entirely contained in the interval. So let X belong to the interval A and B. Now note that A and B are excluded. They are not part of the interval themselves. So B is the upper bound, A is the lower bound of the interval, so to speak, but they are not within the interval. They don't belong to the interval. They are like the barriers outside. Then X is strictly greater than A and strictly less than B. Let's define epsilon equal to the minimum of X minus A and B minus X. In other words, you see, if we move A to the right here, you get 0 less than X minus A. Correct? Now consider that to be epsilon, a value very small and so close to 0. Now, if we move X to the right here, so you get A, actually no, forget about that. So you get B minus X is greater than 0 or epsilon. Hence, epsilon is between these two values. So in other words, you have epsilon is less than X minus A and at the same time less than B minus X. So it is the minimum between these two values. Since we have X greater than A, because remember, X is between A and B, strictly greater than A, strictly less than B, between these two, but A and B are not included. So X greater than A, strictly, and strictly less than B. It's not greater than equal to. We have epsilon, a value greater than 0, positive, very small but still positive. Now consider the neighborhood, X minus epsilon and X plus epsilon. This neighborhood. So because epsilon is less than or equal to X minus A, correct? As we mentioned before, okay, epsilon is actually, X minus A, when we moved A to the right, it's strictly greater than 0, but it can be less than, okay, or greater than or equal to epsilon for X minus A. This is the premise postulated here. Hence, let's move epsilon to the right and A to the left. You get A less than or equal to x minus epsilon, or in other words, x minus epsilon greater than equal to a. Now, again, remember, we started from x greater than a strictly, less than b. If we move b to the right, you get b minus x strictly greater than 0. But if you add epsilon, it can be less than or equal to, okay, or greater than or equal to epsilon. Or if we read it from left to right, epsilon less than or equal to b minus x. So you can move x to the left, you get x plus epsilon less than or equal to b, or b is greater than or equal to x plus epsilon. Therefore, thus x minus epsilon, x plus epsilon is included within interval a and b. So you see, because x plus epsilon is less than b, the upper bound, and x minus epsilon, which is the other page, the previous page, is greater than b. So x minus epsilon, x plus epsilon is included as part of this interval a and b. Therefore, every point of AB is an interior point, hence AB is open. Closed interval is closed. Shows that AB, which is a closed interval, meaning that A and B are actually part of the interval, they are included within the interval, is a closed set in R. A set is closed if it contains all of its limit points. Suppose Xn belongs to AB interval. Again, AB, A and B are supposed to be part of the interval. They are not just boundaries. They are also parts of the interval. They belong to it. And Xn approaches X. So we must show that X belongs to closed interval A and B. Now, since X is greater than, in this case, or equal to A, also less than or equal to B, which is a different annotation to this, to what's written here, meaning that it's part of A, B. It's between A and B, with A and B included. So Xn is greater than equal to A, less than equal to B for all n. Taking limits preserves inequalities. So let's show it. You see, all limit points belong to the set, including A and B themselves. Hence, A, B is closed. Interior of a set. Find the interior of A equal 0, 1. Now, in this case, 0 is part of the set, meaning that it belongs to it, but 1 is excluded. 1 is like an upper bound, but it's not the maximum of the interval. Meanwhile, 0 is the lower bound, but at the same time, it is the minimum. The interior of a set consists of all interior points, every point x with x belonging to interval between 0 and 1. So x is sandwiched between 2, 0 and 1. And it has a small neighborhood entirely contained in 0, 1. However, 0 itself is not an interior point because every neighborhood of 0 contains negative numbers not belonging to the set. Similarly, 1 does not belong to the set. So, therefore, the interior of A is equal to 0, 1, both of them excluded. Without 0, 0 should not be included. Allow me to break it down and explain it in a more different way, from a more user-friendly perspective and approaching from a different aspect. You see, 0, despite the fact that 0 belongs to this interval, is not an interior point because every neighborhood of 0, which is to the left, is a negative value that does not belong to the set. As for 1 is excluded, meaning that it does not belong to the set, and every value above 1 definitely does not belong. So 1 does not belong, 0 is inclusive, but every value left to 0 is not part of the set also. Therefore, the interior of A is 0, 1. Both of them should be excluded. In other words, the interior of this set is almost the same as 0, 1 with 0 included, but the difference is that 0 should be excluded. It is the values or the set of values that are within the set without the boundaries. It's like when you say something is within a room. You cannot include the wall. It is inside the walls. So the walls are excluded from the set. See what I'm saying? Now, 1 is already excluded and acting as an upper boundary, correct? 1 is already excluded. However, for 0, it is included in what we see here in A. So the interior of that would be 0 excluded. So, which is 0, 1, both of them excluded, both of them acting as boundaries and walls, but not included within the set. Find the closure of A equal 0, 1. Now here we are required to get the closure. The closure consists of all points of the set and all the limit points. You see the interval here is 0, 1, which does not contain 0 and 1. So the closure, the boundary, and with 0 and 1 included, that would be the closure. So both are limit points because every neighborhood around them intersects, okay, from 0 to 1. Hence, the closure is the same as the main interval, however, with 0 and 1 included, and this is the symbol. So A bar is equal to 0, 1 with closed brackets. So it's not only the boundaries, but 0 and 1 are part of the set in the closure. Find the boundary of A equals 0, 1. The boundary of a set consists of points where every neighborhood intersects. So we have the set and the complement of the set. For 0, every neighborhood intersects, correct? So also numbers less than 0, similarly for 1, thus 0 and 1 are boundary points. Any point strictly inside 0, 1 is part of the set, okay, but is not a boundary point because sufficiently small neighborhood remains entirely inside the set. Therefore, partial A, this is the symbol, is equal to 0, 1. So the boundary is 0, 1 without the internal. The boundary meaning the walls alone, okay, the upper and lower bounds, without the remainder of the set which is within, because it would be irrelevant. The boundary itself is 0 and 1, which are the walls of the set. Compactness of closed intervals. Show that 0, 1, which are within square brackets, which means that 0 and 1 are part of the set. Show that 0, 1 is compact. Solution. By the HEINE-BOREL theorem, a subset of R is compact if it is, first of all, closed and bounded, both of them. Now the interval 0, 1. First of all, it's bounded because x, for whatever x within this interval, is greater than or equal to 0, less than or equal to 1. So 0 and 1 are the lower and upper bounds respectively. But more than that, 0 and 1 are part of the interval. It's not like the walls on the outside. No, they are part of this set, if you want to call it set. They are part of the interval. So for every x belonging to interval 0 and 1, it is also closed because 0 and 1 are respectively minimum and maximum within the interval itself. Because it contains all its limit points. So the limit points, which are 0 and 1 respectively, are part of this set. That's why. Therefore, 0 and 1 or 0, 1 is compact. So again, 0, 1 is compact, or for every interval for it or subset to be compact, it should be both closed and bounded. And here you have both. Bounded meaning that you have lower and upper bound, 0 and 1 respectively, and closed meaning that these upper and lower bounds are also the minimum and maximum. They are actual values inside the subset. An example of non-compact set, and it should be obvious by now. So determine whether 0, 1 is compact. Definitely it's not. I can tell you from now, because despite the fact that it is bounded, it's not closed. It's not closed. 0 and 1 are not part of the subset. So let's check it out. You see the interval 0, 1 is bounded but not closed. So point 0 is the lower bound. It's a limit point that does not belong to the set itself. Similarly, 1 is the upper bound, but it's not part of the set. It is excluded, just like 0. By the HEINE-BOREL theorem, compactness should meet two criteria, which is both the set should be bound and closed. Here, you only have the bound set. It's only bounded but not closed. Since it's not closed, it's not compact as well. Bolzano-WEIERSTRASS theorem. Show that the sequence xn is equal to -1 to the power of n has a convergent subsequence. You see, xn itself is divergent. Why? Because if n, or whenever n is even, xn would be equal to +1. But when n is an odd number, such as 3, 5, 7, then xn would be -1. So it kind of oscillates between -1 and +1, hence it is divergent. But according to Bolzano-Weierstrass, we can find within that sequence, divergent sequence, a convergent subsequence. Let's check it out. So the sequence itself oscillates, or it kind of swings between -1 and +1. It's divergent. Now let's consider the subsequence of even indices, which is x of 2n. Now x of 2n is always equal to 1. Why? Because whatever number you multiply by 2 becomes even. So let's consider, if we're talking about, you see, if you have -1 to the power of 2n. Doesn't matter what would the value of n be, whether it's odd and even. Okay, so 5, 7, 8. Since it is multiplied by 2, it would always be even. It would always be an even number. Hence, -1 always remains, -1 to the power of 2n always gives us +1. So this subsequence is convergent. Why do we call it subsequence? Because that would be -1, 0, let's say, -1 times 2 times 1, which is times 2, -1 to the power of 6 or 4 first, then -1 to the power of 6, always giving +1. So it's part of the main set. It's a subset, subsequence. Similarly, in the same way, xn plus 1 is always equal to -1. Why? Because given the fact that, let me try to, okay, we kind of lost the pen. Given the fact that for whatever number you have, if you raise it to the power of 2n, it's always even, right? And you add plus 1, so you force it to become odd this time, meaning that whatever n is, let's say n is equal to 3, 2 times 3 is 6, plus 1 is equal to 7. So the power always remains odd in such case, by not only multiplying by 2, but also adding this one. So it always converges to minus 1. So you have two subsequences that are convergent, that are part of the main sequence, which is divergent. These two subsequences are x to n, which always reproduces plus 1, positive value of 1, and x to n plus 1 always gives us minus 1. Connectedness, exercise 9. Determine whether 0, 1 union with 2, 3 is connected. Okay, so a set is connected if it cannot be written as the union of two disjoint non-empty open subsets in derivative topology. The set is 0, 1 union 2, 3 contains a gap between 1 and 2, correct? So thus, it naturally splits into two separate pieces, which is 0, 1 and 2, 3. But we have again a gap between 1 and 2. And remember that the set is connected if it cannot be written as the union of two disjoint non-empty open subsets in this topology. Therefore, the set is disconnected, given the fact that we don't have the values between 1 and 2. It's empty. There's a gap. So 0, 1 union 2, 3 is disconnected. Nested compact sets. So consider Kn equal to the closed interval 0 to 1 divided by n. Find the subset from 1 to infinity of Kn. Okay, the nested compact set. This is what you notice. Since we have 1 over n, this tells us, because as n increases all the way to infinity, 1 over n would decay all the way to 0. It would approach 0. But still, it is greater than 0. It's strictly greater than 0, because it never gets to 0. It becomes so small, but never equal to 0. It's a limit, not an equality. So, as for 0, this is the minimum. Not only the minimum, the lower bound. The lower bound is 0, and this 0 is part of the subset. So it belongs to Kn. 1 over n is a value which is strictly greater than 0, but it's not defined as a fixed value. Okay, so it's a value that as n, actually, yeah, you can consider that it has an upper bound, which is for n equal to 1, 1 over n equal to 1, and that value would be included within the subset. So that would be not only the upper bound, but also the maximum of the set. So anyway, the interval shrinks toward 0. We claim that intersect n equal 1 to infinity of Kn is equal to 0, which is the bound, okay, the lower bound. Clearly, it belongs to every interval. Now suppose x greater than 0 and also x is greater than 1 over n. So, if x is greater than 1 over n, hence, if we flip both of them, you need to flip the inequality also. So, you get the inverse of both the left side and the right side. In other words, 1 over x becomes less than 1 over 1 over n, which is n. Correct? Let's rewrite it. So 1 over x is less than n. N greater than 1 over x. Correct? So 1 over x less than n, another, 1 over n. As for 1 over n, it is less than x. Let's consider also that 1 over n less than x. So x is always greater than 1 over n. And x is greater than 0. X also greater than 0. Hence, the subset, okay, like the subsequence is equal to 0. That would be the subinterval, the subsequence that we can find. In other words, this is the nested compact set. Nested means it's part of the main set. Compact, again, if you remember, it's bounded and it's also part of the set. It's bounded and closed. Only 0 is bounded and closed. 1 over n is not, does not belong. But 0, it is the minimum and the lower bound. The actual minimum, meaning that it's part of the set. And it is the lower bound, so 0 is the compact nested compact subset. 1 over n does not apply. Why? Because it doesn't have a boundary. Open cover. Show that the family minus 1 over n and 1 plus 1 over n between n equal 1 to infinity is an open cover of 0, 1. Now, at first, minus 1 over n does not belong to the set. It's already open to the left. 1 plus 1 over n also does not belong. So it's not part of the set. It's like an external upper bound. Minus 1 over n is an external lower bound, but none of them is either minimum or maximum. So we need to prove that this is an open cover for 0, 1, which is closed and bounded, which is compact, by the way, because 0 and 1 for this subset are both minimum and maximum values belonging to the set itself, and not only that, but they are the lower and upper boundaries respectively. Now each set is open. Let x be a value between 0 and 1. And by the way, if it belongs to 0 and 1, this interval, it can be either a value between the lower and upper bound, correct? And since 0, 1 is closed, it can also be equal to either of them. It can be either equal to 0 or to 1. So you can rewrite it as x greater than equal to 0 less than equal to 1. Now, then for every n, you have minus 1 over n is less than x. So x, in such case, if x belongs to interval 0, 1, then x is between minus 1 over n and 1 plus 1 over n, but without them being included. So x strictly greater to minus 1 over n, strictly less to 1 plus 1 over n. Thus, x in such case belongs to this open interval, open sequence, open subset rather, which is between minus 1 over n to 1 plus 1 over n without either of them being included. Therefore, 0, 1 is part, okay, is included within this entire set, okay, which is from 1 to infinity of minus 1 over n to 1 plus 1 over n. Hence, minus 1 over n, 1 plus 1 over n is an open cover of 0, 1. To say it in more like straightforward, easier words. Okay, let's use some easier expression to portray what's happening here. You see, minus 1 over n and 1 plus 1 over n. This is like an open set that has on the inside of it 0, 1 as a compact, closed and bounded. Basically, compact means both closed and bounded subset. So 0, 1 is within something much bigger. So hence minus 1 over n and 1 plus 1 over n is actually what? Is actually an open cover for interval 0, 1. Dense sets show that the rational numbers Q, meaning every number that has quotient like r over x, like 1 over 2, etc., are dense in R among the real numbers. If every open interval contains a point of A, let A be this open interval with A and B are excluded, be an arbitrary open interval. By the Archimedean property, choose n within the natural numbers such that n times b minus a should be greater than 1. Then there exists an integer m satisfying m is between na and nb. So m is greater than na less than nb. So how do we do that? Let's divide by n. Okay, so you start from this premise and you try to get to the other one. So na less than m less than nb. There should exist an integer m that satisfies this criteria. If we divide by n, you get a less than m divided by n less than b. So now m divided by n belongs to the rational interval, or the rational numbers, correct? Since the interval contains a rational number, hence Q is dense in R. This is how we simply proved it. Closure of the rational numbers. Find Q bar in R. Solution. Since Q itself is dense in R, every real number is either rational or a limit point of rational numbers. Thus, the closure is the entire real number. Correct? So the closure of Q is anything within Q that is actually belonging, okay, that has upper and lower bounds, and that is actually also belonging to the set itself. So the closure of Q is the entire real number scope, is all the real numbers within. Isolated point. Determine whether 0 is an isolated point of the set A equal 0 union. This is, by the way, a compact set, compact subset. So determine whether 0 is an isolated point of the set 0 united with 1 over n, another compact subset, with n being a natural number. So let's check it out. So what is the criteria? A point is isolated if some neighborhood around it contains no other points of the set. Okay, so again, a point is isolated if some neighborhood around that point does not contain any other point of the set. However, the problem is 1 over n goes to 0. tends to 0. Thus, every neighborhood around 0 contains infinitely many points 1 over n. So it's not isolated, okay? Because at its proximity around it, there are many values that are so close to 0, because as n approaches infinity, 1 over infinity approaches 0. Hence, 0 again is not isolated point, okay? 0 cannot be isolated. Finally, these exercises demonstrate the foundational topological structure of R. The key ideas and what we've done in this chapter included open and closed sets, compactness and the HEINE-BOREL theorem, connectedness, dense subsets, closures and boundaries, and sequential compactness. These concepts form the basis for continuity, integration, theory, functional analysis, and modern topology. Third module, continuity. These exercises reinforce the core concepts of continuity developed in module 3. Actually, in this module, the problems focus on continuity of functions, limits of functions, one-sided limit, sequential characterization of continuity, algebra of continuous functions, intermediate value theorem, and extreme value theorem, also uniform continuity. So let's check them out. 1. Continuity using the definition. Prove that the function fx equals 3x plus 2 is continuous at x equal 1 using epsilon delta criteria, which is the definition of continuity. By the way, for a function to be continuous at a point, first of all, the value f1 should exist, meaning that for x equal 1, f should have a value, that's 1. Moreover, the function should have limit as, a finite limit as x approaches to 1. These are the main criteria and conditions for a function to be continuous. So a function f is continuous at x equal a if for every epsilon greater than 0, there exists delta greater than 0, such as x minus a as it approaches delta. When it is less than delta, so x is so close to a, then f of x, an absolute value, which is the distance, by the way, f of x minus f of a, an absolute value, is the distance between x and a, should be less than epsilon. So graphically speaking, let us expand on that. Continuity means that when you have this value here, which is a, and you have a function, and for x equal a, we should have a value of f, which is f of a, correct? So continuity is defined by when you have x, I'm sorry, I cannot draw it, as x approaches a. In other words, when the distance between x and a becomes so tiny, so x is almost confounded with a. So x minus a, the distance between x and a, becomes so small as delta, which is a value that is infinitesimally small, but not equal to 0, strictly greater than 0. So as x approaches a, x minus a less than delta, then f of x approaches f of alpha or f of a in a way that the distance between f of x and f of a becomes so close to 0, meaning less than epsilon, with epsilon is a value strictly positive, greater than 0, but so small. So again, to put it in a more simpler way, hopefully, as x approaches a, f of x approaches f of a. So as both of them approach each other, this means that the limit exists, and also another caveat that f of a should actually exist, should be a value, because you might have at times a function where there is a discontinuity for x equal a. So let's check f of a, if it exists. F of a, which is f of 1, is equal to, you simply replace a equal 1 in x. It is equal to 3 times 1 plus 2, you have it here, which is equal to 5. So the value f of 1 exists. Now we need to check the limit. F of x minus f of 1 is equal to 3x plus 2 minus f of 1, which is 5. Of course, an absolute value is equal to absolute value of 3x minus 3. Actually, we have it here. Now 3, you can pull it to the outside. So it is equal to 3 times x minus 1 in absolute value. We want that 3 times x minus 1 in absolute value should be less than epsilon. So in other words, x minus 1 in absolute value is less than epsilon divided by 3, because we simply multiplied 3 to the denominator of epsilon, correct? So x minus 1 less than epsilon over 3, hence x is less than 1 plus epsilon over 3. Okay, so let delta be equal to epsilon divided by 3. From the former page, remember that we got to the conclusion that x minus 1 should be less than epsilon over 3. Remember? Okay, because f of x minus f of a gave us 3 times x, absolute value of x minus 1. That should be less than epsilon. So if 3 is multiplied to the denominator, you get x minus 1 less than epsilon over 3. Now remember, x minus 1 is simply x minus a, which is less than delta supposedly. Correct? So hence you have x minus 1 less than delta. Since x minus 1 is less than delta, hence f of x minus f of 1 is less than epsilon. Let me break it down a little bit more. So x minus 1 is less than delta, correct? It's also less than epsilon over 3. So if you choose delta equal to epsilon over 3, it all works out, because delta is so small and epsilon over 3 is also a small value. Hence, f of x minus f of 1 is less than epsilon, since x minus 1 is less than delta. As simple as it is, because you know x minus 1 is less than delta. Since x minus 1 is less than delta, delta is definitely less than epsilon over 3. Okay, you simply replace x minus 1 with delta. Delta less than epsilon over 3. So, since the limit exists and the value of f of a also exists, hence f of x equals 3x plus 2 is continuous at x equal 1. 2. Continuity of a polynomial. So the same principle, but for a polynomial function. Show that f of x equal to x squared minus 4x plus 1 is continuous on R. Polynomials are always continuous everywhere on R, because constant functions are continuous. That's one. Plus, the identity function f of x is equal to x is continuous. So, it's always continuous on R. F of x is actually the sum of multiple continuous functions, which is x squared plus minus 4x plus 1. 1 is a constant. Minus 4x is definitely continuous on R, and x squared also is continuous, plus the limit exists. So it is formed using, this function is formed using addition. subtraction, and multiplication of continuous functions. So it is continuous everywhere. Hence, x squared minus 4x plus 1 is continuous on R. That's the conclusion. This continuous function example. Determine whether the function f of x is equal to 1 for x greater than or equal to 0 and 0 for x less than 0 is continuous at x equal 0. Let's at first try to draw this function. So this is x. For x equal or greater than or equal to 0, so this includes 0, and for every value that is greater than 0, hence f of x is equal to 1. For x less than 0, f of x is equal to 0. Let us check if it is continuous at x equal 0. Another important criteria that I should have mentioned by now is that for f to be continuous at a point, let's say the point is x is equal to a. X is equal to a. Limit of f of x as x approaches the left side of a, so as x tends to a minus, should be equal to the limit f of x as x approaches the right side of a, or approaches a from the right, tends to a plus in other words, and also equal to f of a. So f of a should exist, the value of the function f for x is equal to a should exist, but moreover, the left limit, the left-sided limit, should be also equal to the right-sided limit and equal to the value of f at the point itself. Let me try to break it down in a graph. You see, this is a function here, and x is equal to a. So, imagine the function is here. You see, for this function to be continuous, for x is equal to a, f of a should exist, but it's not enough because you might have a split over here. So, not only f of a should exist, but the right side of this point, okay, the right side limit, which is the value of the function to the right of x is equal to a, straightly to the right, one notch to the right, should be the same also as the limit to the left should be also equal to f of a. So let's say the altitude of the function here is 3. Not only you should have 3, which is the value of the function f for x is equal to a, but also the right side value, the limit of the function for a plus, which is to the right of x is equal to a, should be equal to 3, and also to the left side. This is the main important criteria. For x less than 0, f of x is equal to 0. Thus, limit f of x, so you can rewrite it as limit f of x for x approaches 0 minus is equal to 0. Now, let's check the other limit for x approaching 0 plus. Okay. However, for x greater than 0, which is for x strictly after 0, f of x is equal to 1. So, limit f of x as x approaches 0 plus, which is this one here, by the way, is equal to 1. 0 is different than 1. You have two different limits. Okay? Despite the fact that, by the way, for x strictly equal to 0, the limit is equal, the function is equal to 1. So, f of 0, based on the proposal, is equal to 1, according to this proposition, this assumption. Why? Because for x greater than or equal to 0, so you have the equal part, is equal to 1. However, you have a limit which is 0 to the left side of x is equal to 0. Hence, the two one-sided limits are different. Therefore, the limit at 0 does not exist It does not exist. Now for the right hand limit, so for x greater than 0, f of x is equal to 1. Limit f of x as x approaches 0 plus is equal to 1, different than 0. So I might have repeated myself. Hence the function is discontinuous at x equal 0. So f is discontinuous because you have the left-sided limit different than the right-sided limit. Left-sided limit is 0, right-sided limit is equal to 1, and f of 0 for x is equal to 0 is equal to 1. So you have a different value to the left, and the limit does not exist, hence it's not continuous. F is discontinuous at x is equal to 0. Sequential criterion for continuity. Use sequences to determine whether f of x is equal to x squared is continuous at x equal 2. A function f is continuous at a if whenever xn approaches a, f of xn approaches f of a. As simple as straightforward as it can be. So let x of n approaches 2. We need to use sequences here. Then fxn is equal to xn squared. Since limits preserve multiplication, you have xn squared approaching 2 squared. So f of x of n approaches 4. But f of 2 is equal to 4. Correct? Hence, fx of n approaches f of 2, which is 4. Therefore, f of x is equal to x squared is continuous at x equal 2. Intermediate value theorem. Show that the equation x3 minus x minus 1 is equal to 0 has a solution in 1, 2, which is an open set, and it has a lower and upper bound, but 1 and 2, the lower and upper bound, are not respectively the minimum and maximum. They do not belong to the set. So you can say, in other words, that this is an open set. It's not compact. Okay? Plainly put. Since f is a polynomial, it is continuous on 1, 2, on this subset, which is a closed compact subset. Let's compute f of 1 to see if it exists. So f of 1, you simply place 1 in this equation. You get 1 to the power of 3 minus 1 minus 1, so which is minus 1 equal to minus 1 because these cancel out. F of 2, let's compute f of 2. It is 2 to the power of 3 minus 2 minus 1, which is 8 minus 3 or 5. Now remember the interval, which is 1, 2, the closed interval that we are working on. You see, we have f of 1 less than 0 and f of 2 greater than 0. Because f is continuous, the intermediate value theorem guarantees the existence of a value c within 1, 2 open set such that f of c is equal to 0. And this is why it holds. This is why the theory holds. You see, for f of 1, okay, so you have an interval from 1 all the way to 2, correct? F of 1 is a negative value. F of 2 is a positive value, correct? Since this function between 1 and 2 is continuous, it definitely cuts the x-axis at a specific point and it becomes 0. So there exists a value c for which f of c is equal to 0, where there's an intersection between the function and the x-axis, where it goes through a 0 point, 0 level. Again, why is that? Because the left bound, for the left bound, which is the 1 within the subset, f of 1 is negative. For the right bound, it is positive. For it to transition from a negative to positive value, it should definitely clip the x-axis at a 0 level. Okay? So once the function cuts through the x-axis, then it definitely has a 0 value. So x3 minus x minus 1 equals 0 has a root in 1, 2. And we can actually get that root. Extreme value theorem. Find the maximum and minimum values of f of x is equal to x squared minus 2x over the closed interval 0, 3, which is compact and closed, meaning you have lower upper boundaries, and these are respectively the minimum and the maximum of the interval, so they belong to the set. To get the maximum and minimum values of a function, we need to get the derivative, because the derivative would give us the slope or the angle of the tangent to different points throughout the curve, which gives us an idea whether the curve or the function is rising or plunging. So how the curve is actually behaving, whether it rises or it dives. And this is captured through the derivative calculation, because the derivative would give us where you have the minimum or where you have a settlement of the function, meaning that when the derivative is equal to 0, this is where you would get either a low point or a high point, because at this point the tangent, the slope of the tangent would be 0. In other words, the tangent in a maximum or minimum would be parallel to the x-axis. To give you a picture, so you have a function like this. You see, these are the minimum and maximum, and these minimum and maximum are actually the points where the slope of the tangent is parallel to the x-axis. So the slope would be 0, or the derivative, the value of the derivative would be 0 at these points. And these are the points at which you either have a minimum of the function, which is the lowest value, or a maximum, which is the highest value. Let's compute the critical points. So f prime of x, which is the derivative, is equal to 2x minus 2, simply deriving the function. Okay, critical points is where, again, the derivative is equal to 0, which is, in other words, where the slope of the tangent against the curve is 0. So it is where the curve, the tangent to the curve, stabilizes, it becomes parallel to the x-axis, and this is strictly when you have either a minimum or a maximum. Either at the peak of the mountain, because it rises, then it starts to descend. At this point, the tangent would be parallel to the x-axis, or at the lowest point, which is the trough. Like in a wave, it's either the peak or the trough. So we need to get f prime of x is equal to 0 to find for which x values you have a minimum or a maximum. Hence, 2x minus 2 equal 0, or 2x equal 2. So x equal to 1. For this value, you either have a maximum or a minimum. So, step 2, let's evaluate endpoints and critical points. Critical points meaning the values of f for both sides of the boundaries, or for both sides of the interval, which are respectively 0 and 3. Let's see for 0. So, f of 0 is equal to 0. You simply place 0 in the equation, you get 0. F of 1, which is the value for x, is equal to 1. This is the main critical point we got from the derivative, is equal to 1 minus 2. So 1, we placed it in the main function, not in the derivative here, which is equal to minus 1. And f of 3 is equal to 9 minus 2 times 3. So 9 minus 6 equal 3. Hence, what is the minimum value? The minimum value is equal to minus 1. As for the maximum value, it should be 3. This minimum occurs for x equal to 1. Why? Because f of 1 is equal to minus 1. That's the lowest value you can get. As for the maximum value, it is equal to 3, occurs at x equals 3. Why? Because f of 3 is equal to 3. Hence, the minimum value of f is equal to minus 1, and the maximum value is equal to plus 3. Uniform continuity. Determine whether f of x is equal to x squared is uniformly continuous on R, the real numbers interval. A function is uniformly continuous if delta depends only on epsilon and not on the point x. So consider x squared minus y squared is equal to x minus y, absolute value, times x plus y in absolute value. Suppose x, y happen to be very large. Even if x minus y is small, the factor x plus y may become arbitrarily large. We choose x of n is equal to n, and y of n is equal to n plus 1 over n. Hence, x of n minus y of n is equal to n minus n plus 1 of n, correct? In absolute value, it gives you 1 over n, because minus 1 over n absolute value is equal to plus 1 over n. And it approaches 0 as n approaches infinity. But x of n squared minus yn squared is, okay, where's the pen? Okay, x n squared minus yn squared is equal to n squared, given this premise, minus n plus 1 over n squared. As we expand, you get n squared minus n squared plus 2 plus 1 over n squared equal to an absolute value equal to 2 plus 1 over n squared, which is strictly positive, which tends to 2 as n approaches infinity. Thus, arbitrarily close inputs do not force outputs arbitrarily close. Therefore, x squared is not uniformly continuous on R. Now let us try it for a simpler example, exercise. Uniform continuity on closed intervals. Shows that f of x is equal to x squared is uniformly continuous on the closed set 0, 1. You see, 0, 1 is not only bounded but closed, so it is a compact set. So, a fundamental theorem states that every continuous function on a compact set is, by default, uniformly continuous. The interval 0, 1 is closed, given that 0 and 1 are not only the lower and upper boundaries, but actually they belong to the set itself, to the interval, and at the same time bounded, meaning that the lower bound is 0 and the upper bound is 1. So since x squared is continuous, it follows that it is uniformly continuous on 0, 1, on the subset or subinterval, the closed interval 0, 1. Hence, x squared is uniformly continuous on 0, 1. Determine whether the function f of x is equal to 1 divided by x minus 2 is continuous. Now, I think you should have noticed by now that there's a problem that this function cannot exist for a zero denominator. So when the denominator is equal to 0, this function would blow up to infinity. And it wouldn't have a limited value, a finite value. Actually, it won't even be defined. It won't have a limit. Hence, it cannot be continuous at certain points. Let's check it out. A rational function is continuous whenever the denominator is different than 0. This is the only criteria that should be avoided, because once the denominator becomes equal to 0, whatever is divided by 0 blows up to infinity. And the limit in such case does not exist. You have an asymptote, not a limit. So let's check where this function should avoid, or at which point this function would not be continuous. So for a denominator different than 0, you would have x minus 2 different than 0. Hence, if you move minus 2 to the right, you get x should be different than plus 2. Because for x is equal to, you get f of x equal to 1 over 2 minus 2, which is 1 over 0, which blows up to infinity. And it's not defined. Therefore, f is continuous for all x, for all values except for x equal 2. Let me rewrite it in a different style. So, f is continuous for x belongs to the following interval. From minus infinity, of course, minus infinity not included, all the way to plus 2, 2 also excluded, union, plus 2 all the way to infinity. Again, minus infinity plus infinity are not numbers, they are the external bounds, correct? So all values from minus infinity, whatever value, fill in the blank, all the way to plus infinity, these are all the values for which the function is continuous, except for x is equal to. So this is simply another way to write the continuity interval, the continuity scope. 10. Removable discontinuity. Determine whether the function f of x equal to x squared minus 1 over x minus 1 for x different than 1 and is equal to 0 for x equal to 1 is continuous at x equal 1. Let's start with the premise for x different than 1. So let's factor out the numerator. Okay, let's factor the numerator. So you have f of x for x different than 1 equal to x squared minus 1 divided by x minus 1, which is equal to x minus 1 times x plus 1 over x minus 1. You factor out both of these components, so you end up with f of x is equal to x plus 1 for x different than 1. Now compute the limit of f of x as x approaches 1 is equal to limit of x plus 1 equal to. Why? Because for x approaching 1, it's not equal to 1 exactly. That would be the case for f of x equal to x squared minus 1 divided by x plus 1. So limit f of x as x approaches to 1 is equal to limit x plus 1 for x approaching or tending to 1 equal to. However, f of 1 is equal to 0 based on the main proposition. So the function, since limit f of x as x approaches 1 is different than f of 1, again, f of 1 is equal to 0. Meanwhile, the limit of f of x as x approaches 1 is equal to. They are completely different. Hence, the function is not continuous at 1. due to this fact, because you have two different, actually you have a different limit than the actual value of f at x equals 0, at x equal 1. However, f of 1 is equal to 0 based on the main proposition, because it says in the exercise, in the question itself, for x equal to 1, f of x, or f of 1, in other words, is equal to 0. Since limit f of x as x approaches 1, which would be limit of x squared minus 1 over x minus 1, or x plus 1 after factoring out, this is equal to, which is different than f of 1, which is equal to 0. Hence, the function is not continuous at 1, at x equal 1. So the discontinuity is removable, because if we redefine within the question f of 1 is equal to, meaning that here, instead of 0, if you replace it by 2, you fix the problem, so the function become continuous, so hence f has a removable discontinuity at 1. So by removing this value, which is 0 for x equal 1, you solve the problem and you get a continuous function at x equal 1. Lipschitz continuity problem shows that f of x is equal to 5x minus 3. This function is Lipschitz continuous on R. So let's see what are the different criteria or the condition that would satisfy Lipschitz continuity. A function is Lipschitz continuous if there exists a limit L greater than 0 such that absolute value of f of x minus f of y should be less than or equal to L times absolute value of x minus y. So let's compute it. F of x minus f of y means that for the second part, you replace x by y. As simple as that. So let us see where we get to with this. F of x, an absolute value, minus f of y is equal to 5, of course, absolute value to the outside, 5x minus 3 minus 5y minus 3 equal to the following, to the absolute value of 5x minus 3 minus 5y plus 3. 3 minus 3 here cancel out, so you are left with absolute value of 5x minus 5y, which is, by the way, equal, because you can take 5 to the outside, correct? Equal to 5 multiplied by absolute value of x minus y. And in such case, by comparison to this theorem, so we restored this shape actually. We got to this shape. Hence, L in this case is equal to 5. So thus, the Lipschitz continuity or the Lipschitz condition holds true with L equal to 5. Therefore, f of x equal to x minus 3 is Lipschitz continuous. Continuity image of compact sets. So find the image of the closed interval 0 to under the function f of x is equal to x squared. First of all, the function x squared is continuous on 0, 2, which is a closed interval where 0 and 2 are part of this interval. They're not excluded. They constitute the lower and upper bounds, but also these values exist within the interval. Now, since 0, 2 is compact, meaning that 0-2 interval, not only it has an upper and lower bound, but also it is like expressed, or 0 and 2 are actually part of the interval. So it is bounded and closed. Closed is the word. Closed means that 0 and 2 are actually parts of the interval. Hence, the image itself is compact, meaning that also the image is bounded. It has upper and lower bound. And not only that, it is also closed, meaning that f has an upper value and lower value, given the fact that it's continuous throughout the interval 0-2. So let's compute f of 0 and f of 2. So you see that f of 0, you simply replace x squared by 0, which is 0 squared, equal to 0. F of 2 is equal to 2 squared, or 4. Lower and upper value. Hence, you notice that x squared is increasing within the interval 0-2. So 0-2 as an interval is climbing or increasing from 0 to 2. Also, the image itself is increasing from 0 to 4. Hence, f02 is equal to 0, 4. And that would be the image. That would be the definition of the image. Image of f02 is simply 0, 4. Continuous, bounded, and closed. Again, bounded and closed, both of them constitute the compactness principle. Continuous image of connected sets. Show that the image of 0, 1, compact interval, bounded and closed, under f of x is equal to x to the power of 3 is connected. Connected means that there is no gap. There are no gaps. It is completely continuous and has values throughout the interval. So f of x is equal to x3. This function is continuous and having all values between 0 and 1. It's connected. There's no split. There's no gap. The fundamental theorem states that the continuous image of a connected set is also connected. Again, the continuous image of a connected set is connected. The interval 0, 1 is connected. There is no split from 0 to 1. Now, an example of a disconnected set would be something like, for instance, 0, 1, union 1, 2. In such example, you have a gap between 1 and 2. So you have two sets, two intervals, but there's a gap between them, so it's not connected. However, in our case over here, 0, 1, this interval is actually connected altogether. Hence, x3 would give us an image also connected. So, since 0, 1 is connected, x3 happens to be continuous. Hence, continuous means that it is defined on the interval 0 and 1, because 0 and 1 have values on that function. More than that, continuous means that the limit exists on both 0 and 1, and all the values connecting from 0 and 1. And also, not only that the limits exist, the values actually exist, and for each point, the limit is equal to the value. So, for x approaching 0, or for f of x approaching, for x approaching 0, f of x, which is x3, would be also approaching 0. The limit would be equal to 0. Not only that, but f of 0 would be equal to 0. So, in other words, for x equals 0, limit f of x as x approaches 0 is equal to f of 0 equal 0. Same thing for x equal 1. Limit f of x as x approaches 1 is equal to f of 1 equal to 1. Hence, since you have continuity, the image of the function, which is x3, must also be connected. Hence, f of 0, 1, if we compute it, and we just did, is equal to 0, 1, because f of 0 is equal to 0, and f of 1 is equal to 1, which is indeed connected. Therefore, f0, 1 is connected indeed. Finally, so these exercises demonstrated the major principles of continuity in real analysis as a tour de force over what we did in this chapter. So we covered the formal continuity theorem or validation test, so to speak, sequential continuity, one-sided limits, intermediate value theorem, extreme value theorem, meaning maxima and minimum, which is very important. Intermediate is again when the function splits the x-axis at a zero value, so when it zeroes out, and this would be indicated when you have a positive then a negative value on a specific interval. It definitely means that this function had severed or clipped the x-axis and it has a zero value. Also, uniform continuity, continuity of algebraic operations, behavior of continuous images, and continuity forms the bridge between topology and calculus. It's very important and it's fundamental throughout higher analysis. For differentiation, so these exercises or practices reinforce the major concepts of differentiation. The topics include definition of the derivative, differentiability, which means how differential the function is, can it be derivated, rules of differentiation, the chain rule, mean value theorem, Rolle's theorem, Taylor's theorem, higher order derivatives, critical points, and convexity. Let's start with the first exercise, derivative from first principles. Using the definition of the derivative, compute f prime of x, for f of x is equal to x squared. So what is the definition of the derivative? The derivative is actually the slope of the tangent applied against the curve. In other words, this is the tangent of the angle between the tangent to the curve and the x-axis or the horizon, the horizontal line, which is parallel to the ground. So if we want to sketch it, let's assume that you have a curve like this one here, and I'm evaluating the derivative at this point. Okay, so that would be the tangent at this point is like this, and tan alpha is the tangent of the angle formed between the tangent to the curve and the x-axis, which is, or the line parallel to the x-axis basically. That would be tan alpha, or the derivative of the function for actually whatever x, that would give you all the tangents throughout the curve, or if we're talking about a specific x value, that would be the tangent at a specific point. But how to evaluate it? You see, if we look at a magnified image of the curve, if we zoom in, okay, so let's assume here is x. I'm sorry, I'm trying to make it a little bit neat. So here you have x, and you have another step forward, which is basically x plus h. So the distance from here to here is the adjacent segment, the segment adjacent to the angle alpha within the triangle. And for x, you have f of x is the point over here. For x plus h, it is the point over here. That's the height of x plus h, which is the value of the function f at point x plus h. What is tan alpha? As a reminder, tan alpha is equal to the opposite side, which is the length of the opposite side, divided by the adjacent side length, which is this segment over here. So, in other words, f prime of x is equal to tan alpha equal to the opposite side, which is simply this distance from here to here, or fx plus h minus f of x, right? Like when you have a ruler here, and you have 1, 2, 3, 4, okay? So you have 1, 2, 3, 4. What would be the distance from here, from this point to this point? It would be 4 minus 2. This is 2 over here, correct? You subtract. The same thing for our case. So the distance of this segment, or the length of this segment between fx plus h and f of x, is given by fx plus h minus f of x, divided by the length of the segment, the adjacent segment. So the one in the numerator was the opposite segment. The adjacent segment is simply x plus h minus x, which is h, because x cancel out. And we see it in this equation. Now, to be more accurate, so f prime of x, the derivative, is the limit, okay? Because it might not necessarily give you a specific value. It is the limit of fx plus h minus f of x divided by h as h approaches 0, meaning that as you get so close. Why? Why is that? Because you see, if I go too far off, you might not, I might not get an accurate slope. You see, if I go a step too far from x, you might get another, it's no longer a tangent, it might clip through the curve. No, the tangent is strictly close to the curve. That's why h needs to be approaching 0 for you to get an accurate slope. Let's substitute f of x is equal to x squared. Okay, so f of x plus h is equal to x plus h squared. You replace x by x plus h and you evaluate it, which is equal to x squared plus 2xh plus h squared minus f of x. So you get x squared plus 2xh plus h squared minus x squared. This cancels out, by the way, and h, most of it cancels out. You are left with 2x plus h. So as we simplify, equal to xh plus h squared divided by h equal to x plus h. Now h is approaching 0. So basically, f prime of x is equal to 2x, which is the derivative. You see how we get the differential or the derivative? Hence, the derivative of x squared in respect of x is equal to x. Differentiability implies continuity. In other words, when a function is differentiable, it's definitely continuous. But let's prove that. Show that if a function f is differentiable at a, then it's also continuous at a. Assume a function f is differentiable at a. What does that mean to begin with? Then f prime of x is equal to, or f prime of a equal to, limit as x approaches a of f of x minus f of a divided by x minus a. Okay, f of x minus f of a divided by x minus a, that would be the derivative. Let's rewrite it. So if we simply, let's check, okay, f of x minus f of a is equal to f of x minus f of a divided by x. Okay, so we placed both of them. Okay, this is what we did. We simply wrote f of x minus f of a divided by x minus a is equal to f of x minus f of a also divided by x minus a. Then we multiplied this part here in the numerator. We kind of multiplied the extremum. So let's check the limit in such case. Limit f of x minus f of a as x approaches a is equal to the limit as x approaches a of f of x minus f of a divided by x minus a multiplied by limit of x minus a, correct, as x approaches a. We simply place the limits. So, since f prime a exists, and not only it exists, the limit of x minus a as x approaches a is equal to 0, correct? Why? Because x minus a, when a approaches x, the value of x, you get a minus a. So that limit becomes 0. We obtain also that limit f of x minus f of a is also 0. Thus, limit f of x as x approaches a is equal to f of a also. Therefore, f is continuous at a, at x equal a. Hence, differentiability implies continuity as well. Now, let me try to break it down in simpler manners in a moment. Let's at first start from the simple premise that f of x minus f of a divided by x minus a equal to f of x minus f of a over x minus a. Then we multiply x minus a to this side, which is the extremum. So we are left with f of x minus f of a equal f of x minus f of a divided by x minus a times x minus a. Now it will make sense why we have repeated them twice. Okay, to the left equal to the right. Then you place the limit to the left. So limit f of x minus f of a as x approaches a is equal to, so limit of a product, okay, is equal to the product of limits. So limit ab is equal to limit a times limit b. In other words, this is equal to limit of f of x minus f of a divided by x minus a as x approaches a multiplied by limit x minus a as x approaches a. Now we know that this part over here is actually the derivative. This is f of prime of x for x equal a, correct? This is the derivative of the function f of x for x equal a. And we know that it exists. Hence, this is a valid value, a valid component. So this f prime of x for x equal a, or in other words, you can rewrite it as f prime of a is multiplied by limit of x minus a as x approach a. Now limit x minus a as x approaches a is equal to 0. Why is that? Because as x approaches a, you get a minus a, which is 0. So this 0 is multiplied by f prime of a. Let me rewrite it. So limit f of x minus f of a as x approaches a. Let us clean it a little bit. Is equal to f prime of a multiplied by limit as x approaches a of x minus a, which is equal to 0 again. So equal f prime of a times 0 equal to 0. Hence, or therefore, f is continuous at a, and this is how you can conclude that differentiability implies continuity also. Product rule. Differentiate f of x is equal to x squared sine x. Now you know from the formula that u v prime, where u and v are two different components, okay, a product of two different functions. So the derivative of the product is equal to u prime times v, the derivative of the first function times the second, plus uv prime, the first function multiplied by the derivative of the second function. So we're going to prove that with f of x is equal to x squared sine x. So fg prime, as if uv prime, is equal to f prime g plus fg prime, using the product rule, where f is the first function, which is x squared, and g is the second function. So what we have here is a product of two functions. The first one, f, is equal to x squared. Second one is gx equal to sine x. Now, f prime of x is equal to x. G prime of x, which is the derivative of sine x, is equal to cosine x. Thus, derivative of x squared sine x in respect of x is equal to f prime g, which is 2x times sine x, plus fg prime, which is x squared times g prime x, which is cosine x. Hence, d, or derivative of x squared sine x in respect of x, is equal to x sine x plus x squared cosine x. From an analytical perspective, let's prove that fg prime is equal to f prime g plus fg prime. In other words, the derivative of the product, which is f multiplied by g, is equal to derivative of the first function f multiplied by the second, plus the first function multiplied by the derivative of the second function, where f is equal to x squared and g is equal to sine x. Let's at first apply the law of derivation to get the derivative of the first function. So f prime of x, and f here is x squared, okay? Forget about this bigger function. F is considered only x squared, is equal to the limit as x approaches h of f of x plus h minus f of x divided by x plus h minus x. Of course, x and minus x cancel out in the denominator, so it is equal to f x plus h minus f of x divided by h. So f prime of x is equal to limit as x approaches h of fx plus h is simply equal to x plus h squared. So you replace x in this function by x plus h, and this is how you evaluate it. So x plus h squared minus f of x, which is minus x squared divided by h, equal to x squared plus 2hx plus h squared minus x squared divided by h. Now x squared minus x squared cancels out, so it is equal to limit as x approaches h of 2hx plus h squared divided by h. You can also factor out h here, so you are left with limit x approaching h of 2x plus h. Now h is negligible, so truly the real value for the derivative is equal to x. That's why derivative of x squared is equal to x. Let's do the same thing for g. So derivative of x squared so far is equal to x. Let's prove that the derivative of g, which is sine x, is equal to cosine x. How did we get there? Again, let's apply the formula. So g prime of x is equal to the limit as x approaches h of gx plus h minus gx divided by h equal to sine of x plus h minus sine x divided by h. Now mind you that if you remember the trig equations, sine of a plus b is equal to sine a cosine b plus cosine a sine b. So here sine x plus h is equal to sine x times cosine h plus cosine x times sine h minus sine x. Okay, so let us place that in the equation. Limit as x approaches h of sine x plus h is equal again to sine x cosine h plus cosine x sine h minus sine x over h as x approaches h. So how do we solve this limit? I have intentionally cleaned up this upper area so that we can fit in the result. Now let's rewrite it. Limit as x approaches h of sine x times cosine h plus cosine x times sine h minus sine x over h. Now bear in mind that h is a very small value. Hence, as x approaches h, sine x approaches x, okay? Or sine h approaches actually h. So it becomes equal to h. So again, as x approaches h, sine h becomes so close, almost the same value as h itself. So sine h can be replaced by h. So we can remove sine x here and replace it by h. All right. Let us rewrite it. So sine x to the left, we can replace it by h times cosine h. By the way, cosine h, since h is very small, very close to 0, so it's equal to 1 plus cosine x times sine h is close to h, so it can be replaced by h, minus sine x as x approaches h is equal to h divided by h. H minus h is factored out, so we are left with limit as x approaches h of cosine x times h divided by h. H over h equal 1, so equal to cosine x. This is why the derivative of sine x is equal to cosine x, which is again the derivative of g. Now let's evaluate the derivative of this function, which is the main f, which is x squared sine x. So according to the law of the limit of the derivative, it is limit as x approaches h of f, or main, let's write it as capital F, of x plus h minus capital F of x divided by h equal, you simply replace x with x plus h. So it is equal to x plus h squared times sine of x plus h minus f of x, which is minus x squared times sine x divided by h. Now, mind you that f prime small, f prime is equal to x, and g prime is equal to cosine x. So keep that in mind, because we're going to use that to prove this equality. So g is equal sine x, g prime is equal cosine x, f prime is equal to x, and f is equal to x squared. Let us develop that. Limit as x approaches h. So x plus h squared is equal to x squared plus 2hx plus h squared multiplied by sine of x plus h minus x squared sine x divided by h equal limit as x approaches h of x squared sine x plus h plus 2hx sine x plus h plus h squared sine x plus h, okay, minus x squared sine x divided by h. Again, let us remember the trigonometry equations. So sine a plus b is equal to sine a cosine b plus cosine a sine b, because it will come in handy. So going back to this limit down below as x approaches h, so it is equal to x squared times, actually, yeah, let us keep it from the outside, x squared plus 2hx plus h squared multiplied by sine x cosine h plus cosine x sine h minus x squared sine x divided by h. Remember, as we mentioned before, h is so small that cosine h is like saying cosine 0, so it's equal to 1, and sine h is so close to h, is actually equal to h, so it's replaceable by h. Hence, the limit as x approaches h is that of x squared plus 2hx plus h squared multiplied by sine x times 1, because cosine h is like cosine 0 as we mentioned, plus cosine x times h, because sine h is equal to h in such case, minus x squared sine x divided by h. Great. So let us develop that. It is limit as x approaches h of x square sine x, we're multiplying from left to right, plus x square cosine x times h plus 2hx times sine x plus 2hx times cosine x h plus h square sine x plus h square times h, so h to the power of 3 cosine x minus x square sine x divided by h. So let us factor out h from the equation. Limit as x approaches h, because you have h in the numerator and the denominator. So we remove h. We divide by h both from above and from below. You end up with x square cosine x plus 2x sine x plus 2hx cosine x, because we removed one of the h's, plus h sine x plus h square cosine x divided by 1, since the h in the denominator we got rid of. We divided both by h, the numerator and the denominator. Now, remember that h is a very small value, so anything multiplied by h cancels out. It becomes 0. So we end up with x squared cosine x plus 2x sine x. Let us arrange that or rearrange that. It is equal to 2x sine x plus x squared cosine x, which is f prime g, correct? This is f prime g plus x squared cosine x, which is f g prime, x squared times cosine x, f g prime. We have proven that f g prime is equal to f prime g plus f g prime. Quotient rule. So let's differentiate a function f of x which has a quotient, numerator and a denominator. How can we get the derivative for that function? Now, of course, it has been proven using the same methodology as we've seen before. This is how we got that f g prime is equal to f prime g plus f g prime. Okay, so f times g prime, the derivative of this product is equal to f prime times g plus f times g prime. Here we're gonna get straightforward to the solution. So again, the derivative for the quotient, if you have u over v prime, the quotient's derivative is equal to u prime times v minus u times v prime divided by v squared. So the derivative of the numerator times the denominator minus numerator times the derivative of the denominator divided by denom squared. In f g terms, f over g prime is equal to f prime times g minus f times g prime divided by g squared. Let f of x be equal to x squared plus 1, which is the numerator. G of x is equal to x minus 1, which is the denominator. Then f prime of x is equal to x, and g prime of x is equal to 1. So f prime of x is equal to f prime times g, which is 2x times x minus 1, minus f g prime, which is x squared plus 1 times 1, divided by the denominator, which is g squared, which is x minus 1 squared. So you develop it, it's equal to 2x squared minus 2x minus x squared minus 1 divided by x minus 1 squared equal to x squared minus 2x minus 1 divided by x minus 1 squared. Hence, the derivative of this quotient in respect of x is equal to x squared minus 2x minus 1 divided by x minus 1 squared. The chain rule, which is when you have a function nested within another function. So f rho g prime, derivative of such function having a nested function on the inside, is equal to f prime of g of x multiplied by g prime of x. So let us check it out. You have f of x is equal to sine x squared. We propose that u is equal to x squared, which is the inner function, the nested function. Hence, f of x is equal to sine u, and then we differentiate or derivate sine u in respect of u. So, derivative of sine u in respect of u is equal to cosine u, with u equal to x squared, of course. Then we multiply that by the derivative of u, which is u is equal to x squared, in respect of x, which gives us 2x. Hence, the final answer is cosine u, which is cosine x squared multiplied by 2x. This is the derivative of sine x squared. So, derivative of sine x squared in respect of x is equal to cosine x squared, which is u again. U is equal to x squared, multiplied by the derivative of u in respect of x, which is 2x. So it is equal to 2x times cosine x squared. Let us now try to prove it based on the differentiation theorem, which is f prime of x is equal to limit as x approaches h of fx plus h minus f of x divided by x plus h, or x plus h minus x, which is simply h. So let's see what we can get. This is equal to limit as x approaches h of sine x plus h squared minus sine x squared divided by h, equal limit x approaching h of sine x2 plus 2hx plus h squared minus sine x squared divided by h. Now, if we take x squared plus h squared as being a and 2hx as being b, okay, so we know that sine of a plus b, according to or based on trig equations, is equal to sine a cosine b plus cosine a times sine b. So again, let's rewrite it. Limit x approaching h of sine x squared plus h squared plus 2hx minus sine x squared divided by h, with x squared plus h squared is a and 2hx being b. So this is equal to limit x approaching h of sine x squared plus h squared times cosine b, which is cosine 2hx plus cosine a, or cosine x squared plus h squared times sine b, which is sine 2hx minus sine x squared divided all by h. Let us now update the values of a and b, because if you notice here, you have also the form of sine a plus b. So let a be x squared and b h squared. The same thing for cosine x squared plus h squared. By the way, the formulas, okay, so you have sine a plus b is equal to sine a cosine b. plus cosine A sine B, but also cosine A plus B is equal to cosine A cosine B minus sine A sine B. So keep it in mind. So limit x approaching h of sine A plus B. This time A is x square and B is h square. So sine A cosine B plus cosine A times sine B, which is sine h square, I'm sorry, multiplied by cosine 2hx plus cosine A plus B is cosine A cosine B cosine h square minus sine A sine x square times sine B, which is sine h square, times sine 2hx minus sine x square. All of that divided by h. Now, h is negligible, so cosine 2hx as if saying cosine 0. So it becomes 1. And here also cosine h square becomes 1. But meanwhile, sine h square approaches h square, because you know that when sine x, when x is so small, okay, sine x becomes equal to x. Hence, let's rewrite the limit of the entire equation as x approaches h, okay, of sine x square cosine h square is 1 plus h square cosine x square times 1 plus cosine x square minus sine x square times h square times 2hx, because you have times 2hx, yeah, because 2hx approaches sine 2hx approaches 2hx minus sine x square divided all by h. Sine x square minus sine x square, this cancels out, so you are left with limit x approaching h of h square cosine x square plus 2hx multiplied by cosine x square minus sine x square h square divided all by h. After that, we can factor out h, because you have h multiplying both the numerator and the denominator. So limit as x approaches h of h times cosine x square plus 2x times cosine x square minus sine x square h square, all divided, and by the way, h square here is multiplied, it's not part of the sign, all divided by 1, because h has been slashed, it has been factored out. So limit x approaching h of h cosine x square plus 2x cosine x square minus 2x sine x square times h square. Remember that h is so small, it's so close to 0. So anything multiplied by h becomes 0. This is 0, and this becomes 0. And we are left with this term, which is 2x cosine x square, which is the derivative of sine x square. This is how we came up with the formula that it is equal to the derivative of the inside of the cosine, the inside of the function, the nested function, multiplied by the derivative of the function itself. Rolle's theorem. Verify Rolle's theorem for the function f of x is equal to x squared minus 4x plus 3 on the closed interval, which is also compact because it's bounded and closed, 1, 3. First, what is Rolle's theorem? Rolle's theorem states that if f is continuous on the closed interval a, b, meaning that it has all the values between a and b, with a and b included, plus if f is differentiable also on a, b, which is the open set a and b, without a and b being necessarily included, and f of a happens to be equal to f of b, then there exists a value c between a and b such that the derivative of the function at c should be equal to 0. Such that derivative of the function at x equals c is 0. In other words, the tangent against the function has its slope 0, or it happens to be parallel to the x-axis. So the curve is neither ascending at that point nor descending. It's leveled, just like a leveled flight of an airplane, which means that tan alpha is equal to 0. Let's check the conditions. First of all, f is a polynomial equation, so it's definitely continuous on the interval 1, 3. It is actually continuous throughout R. And also it's differentiable anywhere on R, including the interval 1, 3. Now let's compute f of 1. So f of 1 equal, we simply replace x by 1. It's 1 minus 4 plus 3, which is 4 minus 4, or 0. F of 3 is equal to 3 squared minus 12 plus 3. So 9 plus 3, 12, minus 12 equal also 0. Thus, f1 is equal to f of 3. Step 2, let's compute the derivative. Now the derivative gives us the set of equations, or the equation of different tangents against the curve for each point. Now when you get the value of the derivative for a specific x point, you get the slope of the tangent against the curve on that point. So if it's positive, it means that the curve is ascending and the tangent would be like that. It would be positively angled. If it's descending, if the curve is descending, then instead of the tangent being sloped upwards, it would be downwards. Okay, it would be inclined downwards, indicating a negative slope, a negative angle, which indicates that the curve is descending instead of rising. So what is the derivative for this function? F prime of x is equal to x minus 4. Okay, 2x minus 4. Let's find at which point, and here is our point of interest, at which point, in order to prove Rolle's theorem, does the curve level up? So it stops going upwards or descending downwards. It stops rising or climbing or descending. That would be where the tangent or the derivative of the function equals to 0. Let's find that point and see if it exists within the interval 1, 3. So you simply place f prime of x is equal to 0 to find at which x point the slope of the tangent is 0 and the curve levels up. Or in other words, the tangent against the curve becomes parallel to the x-axis. You solve 2x minus 4 equals 0, hence 2x equal 4 and x equal plus 2. Since 2 belongs to the interval 1, 3, hence Rolle's theorem is verified. And c is equal to, where f prime of c equals 0. And c belongs to this interval. Mean value theorem. Okay, what is the mean value theorem? For f of x equal x squared on the closed compact interval 1, 4. Now the mean value theorem states the following, that there exists a point C within the interval, the open interval between 1 and 4, so it's neither 1 nor 4. It is between the two, such that f prime of C is equal to f4 minus f1 divided by 4 minus 1. So it is literally the mean value, the average value between these two boundaries. Let's check it out. So first of all, f of x is equal to x squared. You know that the derivative f prime of x is equal to x. And we need to find that x in a way that it exists between 1 and 4, such that f prime of c, okay, f prime of this value is equal to f of 4 minus f of 1 divided by 4 minus 1. First, f of 4 is equal to 16 because we simply replace x by 4 and we compute. So f of 4 is equal to 4 squared equal 16. F of 1 is equal to 1, which is 1 squared equal to 1. Now f of 4 minus f of 1 divided by 4 minus 1 is equal to 16 minus 1 divided by 3, which is 15 divided by 3, or 5. The derivative again is equal to x. So we need to find for what or for which x value you have the mean value is equal to 5. You simply place 2x or 2c is equal to 5. Hence, c is equal to 5 over 2, which is around 2.5. Is it included within the interval 1 to 4? Correct. 5 over 2 exists within the bounds of 1-4 interval. Why? Because it is strictly greater than 1 and strictly less than 4. Hence, the theorem holds and c is equal to 5 over 2. Critical points. Find the critical points of f of x is equal to x3 minus 3x squared plus 2. First of all, the critical points are the points on the graph where the curve is changing direction, and whenever the curve changes direction, meaning that if it's plunging, it comes up, it starts rising, or when it's rising and it starts plummeting, at these critical points, the slope is equal to 0, the tangent to the curve. At these specific points, when you have an inflection, the slope is equal to 0. In other words, the tangent would be parallel to the x-axis. So what does it mean? The tangent would be parallel. It means that the slope is equal to 0, or the derivative of the function at these points is equal to 0. Again, critical points occur where f prime of x is equal to 0, or f prime does not exist. Let's differentiate at first. So the derivative of x3 minus 3x squared plus 2 is simply 3x2 minus 6x. Okay? 3x2 minus 6x. Let's factor out. So f prime of x is equal to 3x times x minus 2. We place that equal to 0 and we find 2 points. The first one being 3x is equal to 0. Hence, x is equal to 0. The second is x minus 2 equal to 0, or x equal plus 2. These are the 2 points. Hence, the critical points are x equals 0 and x equal plus 2. Increasing and decreasing intervals. Determine whether or where f of x equal x3 minus 3x is increasing and decreasing. So increasing means that the slope of the tangent would be positive. Decreasing would be the opposite, when the slope of the tangent would be negative. In other words, when the derivative to the function is negative, is less than 0, this is when the function would be descending. Let's at first differentiate. So the derivative of f of x is equal to 3x squared minus 3. Great. Which is, by the way, can be broken down into 3. You can leave it outside. So 3 times x squared minus 1, or 3 times x minus 1 times x plus 1. So what are the 2 critical points at first? These are x equal 1 and x equal minus 1. You simply solve these 2 equations. So x minus 1 is equal to 0, hence x is equal to 1. When x is equal to 1, it zeroes out the entire equation. Or for x plus 1 equals 0, x is equal to minus 1. So for x equal minus 1 or plus 1, this entire derivative becomes 0, is annihilated. So we need to check what would be the behavior of the function between these 2 critical points. When the derivative is increasing, the function would be increasing. It would be climbing. When the derivative is, when the derivative is positive, the function would be increasing. When it's negative, it would be decreasing. And at these 2 points, which are x equal minus 1 and x equal plus 1, you have a 0 slope. So the function is leveled up. It's neither increasing nor decreasing, and the tangent is parallel to the x-axis. Let's check behind minus 1. To the left of minus 1, if we take values such as x is equal to minus 2, what would happen with the function? So you would get 3 times minus 2 squared, which is plus 4, minus 1. So 3 times 3 equal 9, greater than 0. F prime of minus 2 equal 9 greater than 0. So the function would be increasing to the left of minus 1. For the second interval between minus 1 and plus 1, as a reminder, f prime of x is equal to 3x2 minus 3. And the 3 intervals we are talking about are from minus infinity to minus 1, then between minus 1 and plus 1, then the third interval is between plus 1 and plus infinity. So 3 intervals. Interval minus 1 to plus 1, let's choose x is equal to 0, and you place it in the derivative. You get f prime of x is equal to minus 3 less than 0. So it is decreasing. As for the interval between 1 and plus infinity, you choose x equal to, let's check it out. For x equal to, f prime of x is equal to 3 times 2 squared, which is 4, minus 3, equal 2 squared is 4 times 3, 12, minus 3, 11, 10, 9. 9 greater than 0. So from minus infinity to minus 1 and from plus 1 to plus infinity, the function is increasing. Meanwhile, between minus 1 and plus 1, the function is decreasing. And remember that all of these replacement we've done to the derivative, not the function itself. But the derivative is the one indicating where the function is increasing, where it's decreasing. Actually, there's a way to write it as a table. So f prime of x equals 3x2 minus 3. This is a in the equation, the part multiplying x squared, and it is positive, okay, because you have plus 3 times x squared. So you place within the table x, you have minus infinity, minus 1. Minus 1 is the critical point, plus 1, critical point, and plus infinity. Between minus 1 and plus 1, the sign of change of f prime of x is contrary to a, okay? Meaning that a is positive, the part multiplying multiplying x squared is positive. Hence, the sign of f prime of x between these 2 critical points is contrary to a, so it is negative, and outside of this interval is positive. Hence, the function f of x is increasing between minus infinity minus 1 and plus 1 plus infinity, which is outside of the critical points interval. But meanwhile, within or on the inside of the critical points interval, the function is decreasing. This is how you can get it. And of course, we can evaluate the limits between minus infinity, minus 1, plus 1. You will see that the function is changing this way. Concavity and inflection points. Concavity determines whether the function has its mouth opened up or down. So let's say you have a curve. Okay, so is the curve open downwards if its mouth is open downward or upward? Okay, so this would be another concavity opening upward. As for the inflection point, this is what the inflection point. The inflection point is the point at which the function would change its direction. So let's say it was going down, it will start going up. That would be the inflection point, the point at which there's a change in direction. Now, concavity is obtained using the second derivative, not the first. The first won't be enough. If the second derivative is positive, it means that the concavity of the function is upwards. It is positive, meaning that the mouth of the function, the mouth of the curve, is opened up, like this one. If it's negative, it would be concaved down, meaning that the mouth would be turned downwards. Let's obtain the first derivative. So f prime of x is equal to 3x squared minus 12x. Second derivative, f second of x is equal to 6x minus 12. Actually, you already have them down there. So let me erase them. Second derivative again is equal to 6x minus 12. Let's check where this second derivative is 0. Okay, let's solve it. Let's see where it concaves up and it concaves down, and also let's get the inflection point. So we set f second of x is equal to 0. So you solve 6x minus 12 equal to 0. Hence, this x is equal to 12 and x equal to 2, which is 12 divided by 6. For x less than 2, we choose x equal 1. First, let's rewrite the value of the second derivative equal to 3x2. Actually, yeah, the first derivative was 3x2 minus 12x. So second derivative is 6x minus 12. If we choose, okay, for x less than 2, we choose x is equal to 1. If you place it back in this equation, you find out that f second of 1 is equal to 6 minus 12, which is minus 6, less than 0. Hence, before 2, the function is concave downwards. In other words, it has a shape like that. Its mouth is open downwards. For x greater than 2, we choose x equals 3. So, f second of 3 is equal to 6 times 3 minus 12, which is 18 minus 12, or plus 6, greater than 0. Hence, it's concaved upwards after 2. So, we can draw it like this. For x equal to, you have no concavity. Now, for x before 2, the concavity is downward, meaning that the function would be something like this. And for x greater than 2, the concavity would be upwards. Its mouth would be opened upwards. Something like that. Since concavity changes at x equal 2, you have already concluded that x equal 2 is an inflection point, but we need to find its y coordinate. Okay, so the x of that point is equal to f of 2 is equal to, now you place 2 in the original equation, 2 to the power of 3 minus 6 times 2 to the power of 2, which is 8 minus 24, because 4 times 6, 24, equal minus 16. Hence, 2 minus 16 is an inflection point. Find the second degree Taylor polynomial of f of x equal to exponential of x centered at x equal 0. Now, Taylor series development is given by, let's say this is f of x, which is equal to ex, and the center is equal to x equal a. So how do we develop it? This is how. F of x is equal to f of a plus first derivative of f at a times x over 1, which is times x, plus second derivative of f at x equal a times x squared over 2. Plus, you can keep going. F third, meaning the third derivative at a times x to the power of 3 divided by 3 plus f4 fourth derivative at a times x4 over 4, etc. all the way, okay? Plus fn at a, so nth derivative times x to the power of n divided by n. This is basically the formula. So, at first, here we need only the second order derivative, okay? So, developing Taylor series to the second order only. In this exercise, we need f of x, Taylor series of f of x, centered at x equals 0, with f of x equal ex. The polynomials formula to the second order is given by p2 of x is equal, by the way, 2 means to the second order, equal f of 0 plus f prime 0 times x to the power of 1 divided by 1 plus f second derivative at 0 of f times x squared divided by 2. All derivatives are equal to ex, remember, okay? Because it doesn't matter how many times you derive ex, you still get ex. f0 is equal to 1. f prime 0 equal 1. f second 0 is equal to 1. Because e of 0 is equal to 1. Because if you remember the graph of the exponential, it is a function that actually at x is equal to 0, it is equal to 1. Correct? So it is like this. It starts from minus infinity, passes by 1 at x equals 0, and goes to infinity. Therefore, p2 of x is equal to f0, which is 1, plus f prime of 0 times x, which is x, plus f second of 0 times x squared divided by 2. All the derivatives at x equals 0 are equal to 1. Hence, p2 of x is equal to 1 plus x squared divided by 2. L'Hopital rule. Compute limit of sine x divided by x as x approaches 0 using L'Hopital rule. This is what L'Hopital rule implies. By the way, L'Hopital is a name for the one who found it out, who figured it out. When we cannot evaluate the limit and you have a quotient, the limit of such quotient is equal, it can be equated to the limit as x approaches 0 of the derivative of both parts of this quotient. Or in other words, the derivative of the numerator divided by the derivative of the denominator. And we will see why this would be needed, because the limit in this case is undetermined using the classical method. Now here's the problem. So limit of sine x divided by x as x approaches 0 is equal to limit as x approaches 0 of sine 0 divided by 0, which is 0 over 0, or undetermined, indeterminate form. So there is no answer. We cannot achieve the answer using the classical method. That's why we need to apply the L'Hopital rule. The L'Hopital rule is simply limit of sine x divided by x as x approaches 0 is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. So in other words, limit sine x over x as x approaches 0 is equal to the limit of cosine x, which is sine x prime, okay, divided by x prime, which is derivative of x in respect of x, equal 1 as x approaches 0, equal to cosine 0 over 1, correct, as x approaches 0, which is 1. By the way, it makes so much sense because analytically, this is what happens. You see, when x approaches 0, and we've spoken about that before, when x approaches 0, so it becomes very tiny and very small, sine x becomes equal to x. That's why sine x can be replaced by x. So you get limit of x over x as x approaches 0, but x over x gives us 1. Hence, the answer of the limit is 1. Convexity shows that f of x equal to x squared is convex on R. A function is convex on R when it's twice differentiable. In other words, the second derivative of x on R should be greater than or equal to 0. Let's check it out. The function f of x as given is equal to x squared. The first derivative of f of x is equal to 2 times x. Second derivative is equal to. Since 2 is greater than 0 for all x, the function is convex everywhere. Hence, x squared is convex on R. As a final summary for chapter 4 of differentiation, we illustrated the central ideas of differentiation. This includes derivatives from the first principles, differentiability and continuity, product, quotient, and chain rules, Rolle's theorem, mean value theorem, Taylor polynomials, convexity and concavity, critical points, and optimization. Differentiation is fundamental in analysis, geometry, optimization physics, and also differential equations. Chapter 5, Riemann integral. Here in chapter 5, we're going to introduce the following concepts: Riemann sums, integrability, upper and lower sums, properties of the integral, fundamental theorem of calculus, mean value theorem for integrals, improper integrals, and applications of integration. Computing a Riemann sum. Evaluate limit as n approaches infinity of the sum from k equal 1 to n of k divided by n times 1 over n. As a first note, n is a constant. Only k is changing because k is moving from 1 to n, and each time it increases, we add it to the previous number. In other words, this part here, like forget about 1 over n, and here k is divided by n. Actually, we can break it down into, you see, 1 over n times 1 over n times k. In other words, if n is multiplied here in the denominator, you get sigma, of course, limit as n approaches infinity, of k over n square. Then we move, of course, sigma from k equal 1 to n. Then 1 over n squared is moved to the outside of the sigma of the sum, since it is a constant. It doesn't change anything. So you end up with limit n approaches infinity of 1 over n squared sigma k from k equal 1 to n. Going again through what we spoke about. So sigma from k equal 1 to n of k over n times 1 over n. This is equal to sigma k equal 1 to n of k times 1 over n squared, which is to be removed outside of the sum. We end up with 1 over n squared times sigma k equal 1 to n of k. Using the formula. Now, remember that here you have a sequence, correct? Which ends up having the form of n times n plus 1 over 2. So, sigma k from k equal 1 to n has a formula which is equal to n, the end number, times n plus 1 over 2. This is how you evaluate it. So, we obtain, because it is multiplied by 1 over n squared, so you multiply this by 1 over n squared. N can be factored out from the numerator and denominator, so we end up with n plus 1 over 2n. Let's evaluate the limit. So all of that, which is 1 over n squared, sigma k resolves into n plus 1 divided by 2n. Taking the limit of n plus 1 over 2n as n approaches infinity is 1/2. That's why, actually, because it is the limit. You can break it down into limit as n approaches infinity of n divided by 2n plus 1 over 2n. As n approaches infinity, this becomes 0. So we end up with n over 2n, which is 1/2. And this is the answer of the limit. Hence, this sum is a Riemann integral that has the value of 1/2. It can be rewritten as integral from 0 to 1 x dx equal to x squared over 2 between 1 and 0 equal to 1/2. One more thing I would like to do with this exercise is expanding or attempting at least to clarify this part here, where you've seen a formula that we don't know where it came from to begin with. However, you don't need to actually figure out how sigma of k from k equal 1 to n is equal or can be equated to n times n plus 1 over 2. But let's try to find it on our own, okay? You see, someone had put in the work and kept trying until he figured out this pattern. However, remember that sigma k, because it's like a sequence, k equal 1 to n is equal to 1 plus 2 plus 3 plus 4 plus 5 all the way to n plus 1. Correct? Let's evaluate it up to n equal 4. So that would be sigma of k equal 1 to 4 of k, which is equal to 1 plus 2 plus 3 plus 4. Adding them up, you get 10. 4 plus 3, 7, 9, plus 1, 10. How can we get it from a more dynamic, clever way without having to add all the numbers up from 1 up to 4? So, okay, so the upper bound is 4. Let's try 4 times 4, 16, divided by 2, which is 16 over 2, is equal to 8. Not enough. Let's try something else. So, and this is how they figured it out, okay? Meanwhile, if you place, instead of n plus 1, so n equal 4 this time, okay? But once you figured it out for 4, it would work for all other values. So 4 times n plus 1, which is 4 plus 1, divided by 2, that would be 4 times 5, 20 divided by 2, equal 10. And this works for all values of n. This is how we came up with the formula sigma k for k equal 1 to n is equal to n times n plus 1 divided by 2. Integrability of continuous functions. Show that f of x is equal to x squared is Riemann integrable on the closed interval, which is closed and compact, or compact means closed and bounded. So bounded from 0 to 1 or between 0 and 1, but also closed, meaning that 0 and 1 are parts of the interval. Fundamental theorem of integrability: for f to be integrable on the interval 0, 1, it should be continuous on that same interval. Again, according to the fundamental theorem, every continuous function on a closed bounded interval is Riemann integrable. So, for the function f of x is equal to x squared. F of x equal to x squared is continuous everywhere on R. Now, by the way, when we talk about closed bounded interval, 0, 1 is closed and bounded at the same time. Why? Because 0 and 1 exist, are parts of the interval itself, but more than that, that's why it's closed, more than that, 0 and 1 are respectively the lower and upper bounds. Again, f of x is continuous everywhere on R, so whatever x would be on R among the real numbers scope, you have f of x valid. F of x for whatever x on R has a value on all R. Hence, it is continuous on all R, including the closed interval 0, 1. That's why we can say that x squared is Riemann integrable on 0, 1. Computing a definite integral. Compute integral between 0 and 2 of 3x squared plus 1 dx. Let's integrate term by term. So integral of 3x squared plus 1 dx is equal to integral of 3x squared dx plus integral of dx, or 1 dx. Okay, let's forget about the boundaries of the integral until the end. So this gives us 3x squared, the integral of that is 3 times x to the power of 3 over 3 plus integral of dx gives us x plus a constant c. Hence, the answer is, because 3 factors out, x3 plus x plus c, if you have no bounds. As for the bounded integral, you need to remove the constant and it becomes bounded from 2 to 0. So you get x3 plus x between 2 and 0, which is equal to, okay, first you place 2 within this equation, you replace x by 2, so you get 2 to the power of 3 plus 2 minus the lower bound, so you replace the lower bound, which is 0 to the power of 3 plus 0, and you get 10 as the final answer. Hence, the integral from 0 up to 2 of 3x squared plus 1 dx is equal 10. Let's solve the same integral analytically. At first, what does it mean, an integral? So consider integral of f of x dx between boundaries a and b. This is actually the area between the curve and the x-axis from a to b. Let me break it down. Let's consider this to be the curve, which is f, the f function, and you have an interval here from a to b, or let's say from 0 to a. Okay, doesn't matter. Okay, let's consider from 0 to a. In such case, the boundaries would change from 0 to a. Basically, the area is given by, actually, you cannot evaluate the area of the curve, but you have to break it down into small rectangular areas. So what do we mean by that? If we take small dx steps, a small chunk, this dx distance, we multiply it by the height of the function at this point, which is f of x. So f of x times dx at this point would give us the area of the rectangle. Of course, as we minimize dx to a much smaller distance, that would give us a smaller rectangular area, which would be more accurate. So the resolution would be much better. Why? Because if the step is bigger, let's say the step is this much, okay? In this case, the area of the rectangle would be like this, but you have missed an entire part here. But when you minimize the steps, you get rectangles that are, very close to each other, and the gap of error would be much smaller. How do we solve that? At first, we need to break down the interval 0 to into n equal subintervals. So delta x for each subinterval should be equal to, which is the entire distance, because from 0 to 2 it's 2 minus 0, divided by n, which is the number of subintervals, the number of chunks, number of rectangles also. The right endpoints are xi is equal to 2i divided by n. Using the definition of the Riemann integral, so integral from 0 up to 2 of 3x squared plus 1 dx is equal to the limit. Here we go to definition of Riemann integral. Limit as n approaches infinity of sigma I equal 1 to n of 3xi squared plus 1 times delta x. Then you substitute xi with 2i over n and delta x with 2 over n, which is the step size. You get limit as n approaches infinity, sigma I equal 1 to n of 3xi, remember, which is 3x squared. So instead of x, you place 2i over n squared plus 1 times delta x, which is 2 over n. As a reminder, you have xi equal 2i divided by n, and delta x, which is dx, equal 2 over n. After you replace, you end up, after simplification, with limit as n approaches infinity of sigma I equal 1 to n, 12i squared over n squared plus 1 times 2 over n. Let's distribute it so you can break it down into 24 limit n approaching infinity of 24, because we multiplied by 2 over n, correct? 24 over n to the power of 3 sigma I equal 1 to n I squared plus 2 over n sigma I equal 1 to n of 1. Remember the formula of sigma k for k equal 1 to n, the formula of the sequence. This is equivalent to n multiplied by n plus 1 over 2. And this is what we're going to apply here also. There is another formula for sigma I squared, which is part of what we've seen, because the constant values don't need to get them within the sequence, within the sum. But for sigma I square, for I equal 1 to n, it has a different formula than what we've seen before, which is n multiplied by n plus 1 multiplied by 2n plus 1 over 6. And it works. And for sigma I equal 1 to n of 1, this is another sequence, is equal to n. As simple as that. Okay? After that, you replace the equivalency of the sequences within the equation. So sigma I squared from I equal 1 to n is equivalent to n times n plus 1 times 2n plus 1 divided by 6. So you place this equation back in the formula here, or this formula back in the equation. And as for sigma of 1 from I equal 1 up to 2, it is equal to, correct? Because sigma I equal 1 to n of 1 equal n. Now, let's factor out 24 and 6. You divide by 6, both in the numerator and denominator. Here you are left with 1, here with 4. Also, we can factor out n. So, you divide by n, both in the numerator and denominator. You get here n squared. Now, the numerator can also be expanded. So, limit n approaching infinity of 4 times n plus 1 times 2n plus 1 over n squared plus 2. n plus 1 multiplied by 2n plus 1 gives us 2n squared plus n plus 2n plus 1, which is equal to n squared plus 3n plus 1. You take that and you place it back over here, and we break down this fraction. So it is equal, this part I mean, is equal to n squared divided by n squared plus 3n divided by n squared plus 1 over n squared. N squared is removed here. Here you have a removal of 1n, and what is left is 1 over n squared, which is this value here. So limit n approaching infinity of 4 times 2 plus 3 over n plus 1 over n squared plus 2. Let's solve the limit of the equation as n approaches infinity. So this part, as n approaches infinity, 3 over n approaches 0. So does 1 over n squared. We are left with 4 times 2 plus 2, which is 8 plus 2 equal 10. Hence, the integral from 0 of over 2 of 3x squared plus 1 dx is equal 10. So we demonstrated using the fundamental real analysis equation. Integral of an odd function. Evaluate integral from minus 2 to plus 2 of x3 dx. At first, what is an odd function to begin with? An odd function is a function that is symmetric in respect of the origin, which is this point here, the origin of the axis, where x is equal to 0 and y equal 0. For example, sine x is an odd function. Why? Because it is symmetric in respect of x equal 0, x, y equals 0, both of them. In other words, the area that is positive after the y-axis, that is the y-axis, is equal to the negative area before the y-axis. So they cancel each other out. Now, what is the criteria for a function to be odd analytically? It should respect f of minus x equal to minus f of x. For instance, let's consider f of x equal to sinus x, sin x. F minus x is equal to sin minus x, which is equal to minus sin x, or minus f of x. Hence, sin x is an odd function. Let's check it out for x3 dx. So does it respect this criteria? Let's check it out. F of minus x is equal to minus x3 because the power is odd, which is equal to minus f of x because minus f of x is also minus x3, hence the function is odd. Since the function is odd, the integral, which is the area, the overall area of that function should be 0, given the fact that a part of that area is positive and it's equal to the other part, which is negative. So the sum of both would give us 0. Let's verify it. So actually, yeah, you can simply say that the integral in such case is 0. But let's prove it. So integral minus 2 to plus 2 x3 dx is equal to x4 divided by 4 between 2 and minus 2 equal 16 over 4, which is 4, minus 16, okay, which is minus 2 to the power of 4 is also 16 over 4. So equal 4 minus 4 equal 0. And you can simply say it immediately given the fact that this function is odd and also integrable on the interval minus 2 to plus 2. So the theorem briefly is when a function is odd and integrable on an interval minus a plus a, hence integral from minus a to plus a of f of x dx would be automatically equal to 0 because it is an odd function and integrable on that domain, on that interval. Now let's compute the integral of an even function. What is an even function? An even function is a function that is symmetric in respect of the y-axis. What do I mean by that? So let's consider a function like this one. So you notice a pattern. It is symmetric in respect of the y-axis, not the origin. So this function would satisfy the criteria of f of x equal to f minus x. So whether x is positive or negative, it would have the same altitude or the same value on y, on f, from both sides. Let's compute integral from minus 1 to plus 1 of x squared dx. First of all, let's check if f is an even function. So for it to be even, it should satisfy the criteria of f minus x equal f of x. F minus x is equal to minus x squared equal to x squared, which is the same as f of x, hence it is an even function. Now for an even function, and this is the theorem, because as we've seen in the previous graph, for an even function, it would have the same area because it's symmetric according to the y-axis, so it will have the same area between minus a and 0, just as between 0 and plus a. So instead of evaluating the integral or the area of the curve from minus a to plus a, we simply can evaluate the area or the integral from 0 to a of f of x dx and multiply it by 2 since it is a double portion from left to right. Okay? So given that it is symmetric and we have the same area to the left and to the right, we can simply evaluate the right area, which is from 0, x equals 0, to plus a. And once you get that area, if you multiply it by 2, you get the entire area from left to right. So thus, integral from minus 1 to plus 1 of x squared dx is equal to 2 integral from 0 to 1 x squared dx. if you evaluate it, so it is integral 0, 1 x squared dx equal x3 over 3 between 1 and 0 equal 1/3. So, yeah, and you multiply it by 2, you get 2 over 3. Let us evaluate from -1 to +1 to prove that it is equal to 2/3 of f of x dx. So it is equal to x3 divided by 3 between +1 and -1, which is equal to 1/3 minus -1/3 equal 2 over 3. So we've gotten the same answer. Hence, this theorem or this concept holds. Upper and lower sums. Consider f of x is equal to x on the closed and bounded interval, which makes it compact, since 0 and 1 are not only the minimum and the maximum existing within the interval, they are the lower and upper bounds, with partition p equal 0, 1/2, 1. Compute the upper and lower sums. This partition can be broken down between 0 and 1 into 0 to 1/2 and 1/2 up to 1, correct? We simply split the interval at its middle. Since f of x is equal to x is increasing, so the first interval, m1 is equal to 0, m1, capital M1 is equal to 1/2, correct? Meaning that the values, because for x equals 0, f of 0 is equal 0, f of 1/2 is equal to 1/2. The length of the interval itself is equal to 1/2 minus 0. This is the step over here, which is 1/2. For the second interval, between 1/2 and the +1, again, f of x is equal to x. So, f of 1/2, which is m2 by the way, is equal to 1/2, and capital M2, which is f of 1, that's the upper bound, is equal to 1, equal M2. Delta x2 is also the distance between 1/2 and 1, which is 1 minus 1/2 or 1/2. The lower sum is given by LPF is equal to M1 times delta x1 plus M2 times delta x2, correct? From the previous page, which is 0 times 1/2 plus 1/2, okay, times 1/2 equal 1 over 4. The lower is lowercase m1 and lowercase m2. These are the ones we are evaluating. Each one of them you multiplied by delta x1, which is 1/2. As for the upper sum, here you get capital M1, the upper bound, correct? The value of f on the upper bound. The upper sum is given by m1 times delta x1 plus m2 times delta x2. If you remember, m1 was equal to 1/2, m2 was equal to 1. So it is equal to 1/2 times. Now delta x1 and delta x2 happen in this case to both be equal to 1/2. This is the step distance, the distance of the interval itself. So equal 1/2 times 1/2 plus 1 times 1/2 equal to 1/4 plus 1/2 equal 3 over 4. Hence, the lower sum is equal to 1/4 and the upper sum is equal to 3/4, 3 over 4. The mean value theorem for integrals. Verify the mean value theorem for integrals for the following: f of x is equal to x squared on closed interval and bounded 0, 2. The theorem states the following, that there exists a point C between A and B. Now, it belongs to the closed interval A, B, such that C is either a value between those two or equal to one of them. It can be either of that, such that integral from A to B of f of x dx, which is the area, by the way, of the function, or enclosed by the function, and the x-axis between A and B, between x equal A and x equal B, is equal to f of c, which is the height of the function at x equals c, multiplied by b minus a, the distance between b and a. Now, what does that give us? It simply gives us the area of a rectangle that has the segment, lower segment is b minus a. This is one of the sides, multiplied by the height of the function at x equal c, which gives us the average value of the integral to the left, which is integral from a to b, f of x dx. Let's compute the integral. So integral from 0 up to 2, x squared dx is equal to x3 over 3 between 2 and 0 equal 8 divided by 3. Now let's place it here, and next to it equal f of c times b minus a, which is 2 minus 0. You can factor out 2 because when you multiply it in the denominator, you divide 8 by 2, so you are left with 4 over 3. Hence, f of c is equal to 4 divided by 3. Now, f of c is equal to c squared, because you simply replace x by c, so you get c squared. Let's solve it for c. So you replace f of c with c squared, you end up with c squared equal 4 over 3. Hence, c is equal to the square root of 4 over 3. Now, you can remove 4 to the outside, so c is equal to divided by square root of 3. And this value belongs to the interval, to the closed interval 0, 2. Therefore, c is equal to divided by square root of 3. Define f of x is equal to integral from 0 to x, d squared dt, and find f prime of x, which is the derivative this time. The fundamental theorem of calculus states the following, that if f of x is equal to integral from a to x f of t dt, and f is continuous, then f prime of x is equal to f of x. Here, f of t is equal t squared. Thus, f prime of x would be x squared, as simple as that. Okay, so the derivative of the integral is equal to the function on the inside, given that the function itself should be continuous. Hence, f prime of x is equal to f of t for t equal x, which is equal to, because f of t is t squared, remember. So you replace t by x, and you end up with f prime of x is equal to x squared. Hence, f prime of x is equal to x squared. Area between curves problem. Find the area between y equal x and y equal x squared on 0, 1, which is a bounded and closed interval. At first, let's plot these two functions. So, y is equal to x is simply the first bisectors. It is this line here where y is always equal to x. It kind of splits this quadrant and the lower one also to two completely equal areas. Now, so this is y equal x. As for y equal x squared, it is the formula of the parabola, starting from 0, and it goes up like this. And they do intersect at x equal 1. And this is the area we're talking about. by the way. This is the area we're trying to evaluate. And the scope of this area is indeed from 0 up to 1 as a closed interval. To evaluate the area, in such case, you simply evaluate the integral of the top function minus the bottom function between 0 and 1 in such case, or between the bounds in general. So the area between curves is again integral from 0 to 1, in our case, of the top function minus bottom times dx. Again, y equal x is above the parabola, as we stated before, because the graphs are the following. Y equal x is this one, so it is above y equal x squared, which is coming from beneath. This is y equal x squared. So we have x greater than x squared, hence a equal integral from 0 to 1, x minus x squared dx, which is equal to x squared over 2 minus x3 over 3 between 1 and 0, equal 1/2 minus 1/3, okay, because the other part is 0, equal 1 over 6, and this is the area, 1 over 6. Improper integral. Determine whether integral from 1 to infinity of 1 divided by x squared dx converges. So in such case, how do we solve it? Integral between 1 and infinity of f of x dx is equivalent to the limit as b approaches infinity of integral from 1 to b of f of x dx. So you swap these two. You replace integral from 1 to infinity f of x dx by limit from b going to infinity of integral 1 to b f of x dx. Let's check it out. So integral from 1 to infinity 1 over x squared dx is equal to limit b approaching infinity integral from 1 to b of x to the power of minus 2, which is, by the way, x squared, but removed from the denominator up to the numerator. So we did not actually change anything here, multiplied by the x. Let's integrate. So the integral is x minus 2 plus 1 divided by minus 2 plus 1. That would be the answer for the integral, which is x to the power of minus 1 over minus 1, or minus 1 over x, because x to the power of minus 1 is simply 1 over x. So this is equal, let me clean this slate, equal to limit b approaching infinity of minus 1 over x between b and 1, equal to minus 1 limit b approaching infinity of minus 1 over b plus 1. As b approaches infinity, this component becomes 0, correct? It approaches 0. So we obtain equal 1. That would be the answer for that improper integral. Hence, the integral converges to a finite value. Hence, it is a convergent integral. So integral from 1 to infinity of f of x dx is equal to 1. Divergent improper integral. Determine whether integral from 1 to infinity of 1 over x dx converges. Let's apply the same concept, the same formula, so to speak. So this is equal to the limit as b approaches infinity of integral from 1 to b 1 over x dx, which is, by the way, 1 over x is interesting because it becomes ln x. Let's check it out. So integral from 1 to infinity 1 over x dx is equal to limit b approaching infinity integral from 1 to b 1 over x dx, which is ln x. So it's limit of b approaching infinity ln x logarithm between b and 1. which is limit of ln by, because ln1 is equal to 0. Okay, so it is originally ln b minus ln1, but ln1 becomes 0. You are left with ln b. ln infinity goes to infinity. That's why it's divergent, because there's no finite limit. Hence, the integral diverges. Integration by parts. Let's compute integral of x ex dx. The concept here is to try to find or to reshape the integral to the form of integral of u dv, which gives us uv minus integral of v du. So, what would be dv in such case? dv would be ex, because v then would be integral of ex dx, and it reproduces ex. As for u is x, the first part of the integral, because du becomes 1 dx. And you simply fill in the blank. So integral x ex dx is equal to integral of u dv, where u is x and dv is ex. It becomes equal to uv, so x times ex, minus integral of v du. What is v? v is ex times du, which is 1 dx. Hence, this would be equal to x ex minus ex, as simple as that. So this is the full solution. U is equal to x, then du equal dx, which shows dv is equal to ex dx. V is equal to ex, as we've seen in the former example. So integral of x ex dx is equal to, with u equal x, again du equal 1 dx, dv equal ex, then v is equal to integral of dv, integral of ex, which is also ex. Great. So integral x ex dx is equal to uv x times ex minus integral of v du, which is ex dx, equal x ex minus ex plus c. Ex can be factored to the outside, times x minus 1 plus c. Substitution rule. Compute integral of 2x times cosine x squared dx. Here you have to kind of play another trick in order to solve this integral. If we suppose that u is equal to x squared. Okay, by the way, another name for that is the change of variables. U is equal to x squared, du is equal to x. So what do we notice? Okay, by the way, du would be 2x dx, because it is the derivative of u in respect of x. So don't forget about dx. All right, so how does it fit in this integral? You see, you have integral of 2x times cosine x squared dx. What is 2x? 2x and dx, by the way, this entire product is simply du. So you remove 2x dx and you swap it with du. As for cosine x squared, okay, u is equal to x squared, correct? So this is cosine u. That is equal to integral of cosine is equal, by the way, it is like the opposite of the derivative. Derivative of cosine is equal to minus sine. Integral is equal to plus sine. Hence, integral of cosine u du is equal to sine u plus c, which is sine x squared, because you need to reinstate the value of u, plus c. Let's check it out. again, u equal x squared du is equal to 2x dx. So you remove 2x dx and replace them by du. As for cosine x squared, since u is equal to x squared, is cosine u. So this is equal to integral of cosine u du. After we integrate, you get sine u plus c. You substitute it back, so you get back sine x squared plus c. Integral comparison problem. Show that integral from 0 to 1 of x squared dx is less than integral from 0 to 1 of x dx. How can we prove that? For x between 0 and 1, we know that whatever value is below 1, once you square it, it decays. Okay, so always for the values that are less than 1, x squared is less than x, given the fact that below 1, when you have, for example, 0.01 and you square it, it becomes 0.0001. Okay, so it decays, it depletes instead of increasing. The only values that increase when you square them are those that are above 1, such as 2 square 2 is 4, 3 square 3 is 9, etc. Hence, we know that x squared is always less than x for x between 0 and 1. So, starting from this premise, let's add the integral, or let's integrate left and right. Okay? So, given that x squared is less than x for the closed interval 0, 1, hence, integral of x squared dx is also less than integral of x dx between 0 and 1. So this preserves the inequality and the concept holds. Let's compute integral from 0 to 1 of x squared dx. This gives us x3 over 3 between 1 and 0 equal to 1/3. As for integral of x dx between 1 and 0 gives us x2 over 2 between 1 and 0 equal 1/2. So 1/3 is lesser than 1/2, which proves the inequality. The result is verified. Finally, as a wrap up for this chapter, so these exercises had covered the following concepts: construction of integrals using Riemann sums, integrability of continuous functions, definite and improper integrals, fundamental theorem of calculus, integration techniques, geometric interpretation of integrals, area computations, and symmetry properties. Integration forms one of the central pillars of real analysis and provides the foundation for advanced analytics or analysis, probability, differential equations, and mathematical physics. 6. Infinite series. Now, this part covers the following: convergence of series, geometric series, harmonic series, comparison test, ratio test, root test, alternating series, absolute and conditional convergence, power series, radius of convergence, and Taylor and MACLAURIN series. Determine whether the series sigma n equals 0 to infinity of 1/2 to the power of n converges and compute its sum. First, this is a geometric series of the form sigma n equals 0 to infinity of a times r to the power of n, where a in this case is 1, which is the multiplier of the component raised to the power of n. R is the component itself, which is 1/2, correct? To the power of n, this is n. So this is r, which is equal to 1/2, and a equal to 1. The geometric series converges when and only when r, an absolute value, is less than 1. We know that r is equal to 1/2. This is r. It is less than 1. Actually, it is equal to 0.5. Hence, the series converges. Now, the sum is given by the following formula: a divided by 1 minus r. with a being 1, over 1 minus r, which is 1/2, equal 2. Okay, 1 divided by 1 minus 1/2 equal 2. So this sum ends up being equal to divergence of the harmonic series. Determine whether sigma n equal 1 to infinity of 1 over n converges. This is a harmonic series, which develops, by the way, into 1 over 1 plus 1/2 plus 1/3 plus 1/4 all the way to plus 1 over n. Now, to solve it, we need to use the grouping method. We group terms as follows. So 1 plus 1/2 plus 1/3 plus 1/4 together plus 1/5 plus all the way to 1/8 together, etc. Let's observe something. 1/3 plus 1/4 to the left is greater than 1/4 plus 1/4. Why? Because this term is divided by 3 instead of 4. And by the way, 1/4 plus 1/4 is equal to 1/2. So, similarly, 1 over 5 plus all the way to 1 over 8, okay, is greater than 1 over 8 added 4 times, which is 4 times 1 over 8, which gives us 1/2 also. So in other words, the term keeps increasing above 1/2. Hence, the series diverges. It diverges to infinity. It keeps adding up. Determine whether sigma from n equal 1 to infinity of 1 over n squared converges. This is called the p-series test. The form of a p-series is the following. That form would be sigma of 1 over n to the power of p, where p is the power. Now, if p is greater than 1, then it converges. Why is that? Because when the power is a greater number than 1, it means that this number that you're dividing becomes lower and lower. It starts decaying all the way to 0. So it converges to a finite value. Here, p is equal to, which is greater than 1. Hence, since 2 is greater than 1, this series converges. In fact, sigma of n equal 1 to infinity 1 over n squared is equal to pi squared over 6. Hence, sigma n equal 1 to infinity of 1 over n squared converges. Comparison test. Determine whether the series sigma n equal 1 to infinity of 1 over n squared plus 1 converges. The comparison test works in this way. You need to compare it to a series that we are already familiar with, which is sigma of 1 over n squared, which is a p-series. We already know that for this one, it converges because the power of n is 2. So, since n squared plus 1 is greater than n squared, it won't make any difference. It's almost the same. You added 1 to the denominator that's already becoming big, and which will make the quotient decay all the way to 0. We have 1 over n squared plus 1 would be less than 1 over n squared. Because sigma 1 over n squared converges, the comparison test implies that sigma of 1 over n squared plus 1 also converges. Divergence test. Determine whether sigma n equal 1 to infinity of n divided by n plus 1 converges. The necessary condition for convergence is an approaching 0. Here, an is given by n divided by n plus 1. Let us check the limit of an as n approaches infinity. Limit n over n plus 1 as n approaches infinity can be reduced into limit of n over n as n approaches infinity, because in such case, 1 would be negligible or insignificant. So, n over n gives us 1. Since it does not approach 0, hence the series diverges. So this is a divergent series. Ratio test problem. Determine whether sigma n equal 1 to infinity of n factorial divided by 2 to the power of n converges. What is the ratio test, by the way? It is the evaluation of the limit as n approaches infinity of an plus 1 over an, with an is the term here. An equal n factorial divided by 2 to the power of n. Again, an is given by n factorial divided by 2 to the power of n. So what is an plus 1? An plus 1 is equal to n plus 1 factorial divided by 2 to the power n plus 1. Now 2 to the power n plus 1, which means, in other words, 2 to the power of n multiplied by 2. As for n plus 1 factorial is equal to, it's like when you have 6 factorial is equal to 6 times 5 factorial. It is equal to n plus 1 times n factorial, correct? Because it is 6 times 5 times 4 times 3, etc. All right. So n plus 1 factorial, let's place it. So an plus 1 is n plus 1 times n factorial divided by 2n over 2. Let's divide it by an. So let us leave it actually n plus 1 factorial divided by 2 to the power of n times 2, as we mentioned, all the way divided by an, which is n factorial divided by 2 to the power of n. Now this factors out. Again, n plus 1 factorial is n plus 1 times n factorial. So this reduces to n plus 1 times n factorial divided by 2 divided by n factorial. This is removed, so we end up with n plus 1 over 2. Limit as n approaches infinity of n plus 1 over 2 is equal to infinity. Hence, since the limit exceeds 1, the series diverges. So this is a divergent series. I felt that I should go back here to make the factoring a little bit more simpler in case it was complicated. At first, again, an plus 1, because we should get the limit of an plus 1 over an as n approaches infinity. This is the ratio test. An plus 1 is given by, given of course that an is n factorial divided by 2n. You replace n by n plus 1. So it is n plus 1 factorial divided by 2 times n plus 1. And an, we already have it. Now an plus 1 is equal to n plus 1 times n factorial divided by 2n times 2, because simply you have added 1 to the power of 2, meaning that it's multiplied once again by itself. Now, how can we say that n plus 1 factorial is equal to n plus 1 times n factorial? This is why. Imagine we are evaluating 6 factorial. 6 factorial is equal to 6 times 5 times 4 all the way to 1, right? So this can be written as 6 times 5 factorial. Doesn't change anything. This is what gives us the right to break it down like this. Now, an plus 1 divided by an is equal to n plus 1 times n factorial divided by 2 to the power of n times 2 over n factorial divided by 2 to the power of n. Now, when we are dividing two quotient, we can multiply them together by flipping the second quotient. So, in the second quotient, the denominator becomes the numerator and numerator the denominator, vice versa. So, this can be rewritten as n plus 1 times n factorial divided by 2 to the power of n times 2 multiplied by 2 to the power of n divided by n factorial. So you remove n factorial, 2 to the power of n, and this is how we are left with n plus 1 divided by 2. This is the one that we've gotten the limit for, and it turns out to be infinity. That's why the series diverges. Root test. Determine whether sigma n equal 1 to infinity of 3 divided by 4 to the power of n converges using the root test. The square root test is actually computing the limit as n approaches infinity of the nth root of an being an absolute value. An is equal to 3 divided by 4 to the power of n, so the nth root of an, an absolute value, is equal to 3/4. Hence, the limit as n approaches infinity of square root, actually nth root of an, is equal to 3/4 less than 1. Hence, this series converges. Absolute versus conditional convergence. Determine whether sigma n equal 1 to infinity of minus 1 to the power of n divided by n converges absolutely or conditionally. Let's consider the absolute value series, which is sigma n equal 1 to infinity of absolute value of minus 1 to the power of n divided by n. This gives us sigma n equal 1 to infinity of 1 over n. This is a harmonic series which diverges. We already know that. However, the alternating series itself converges. Correct? Thus, the convergence is conditional. Why? Because it is at times minus 1, at times plus 1. So it kind of cancels out each other, okay? Hence, the convergence is conditional. Therefore, sigma n equal 1 to infinity of minus 1 to the power of n divided by n converges conditionally. You see, minus 1 to the power of n by itself without being divided by n is alternating. It keeps flapping or swapping from minus 1 to plus 1 all the time. So it is divergent. For 1 over n alone also is divergent. But for minus 1 to the power of n divided by n, this gives us minus 1 over 1 for n equal 1, then plus 1 over 2, then minus 1 over 3, plus 1 over 4, etc. Okay, so let's try to kind of sum up these things. Here you have minus 1 plus 1/4 is equal to minus 3 over 4. Plus 1/2 minus 1/3 gives us, okay, you have 6 over 2, 3 minus 2 over 6. So it is 1 over 6. So minus 3 over 4 plus 1 over 6. So terms start cancelling out each other. Okay, let's evaluate how much would that be. 24 over 4, 6. This would be minus 18. Then here over 6, 4. So minus 14 over 24. It starts decaying all the way to 0. That's why it is convergent. Find the radius of convergence of sigma n equals 0 to infinity of x to the power of n. To find this radius, we use the ratio test. What is the ratio test? It's simply computing an plus 1 divided by an in absolute value. So, given that an is equal to x to the power of n, an plus 1 over an in absolute value is x to the power of n plus 1 divided by x to the power of n. Now, x to the power of n plus 1 can be rewritten as x to the power of n times x over xn. You can factor out xn and we are left with x in absolute value. The series converges when x is less than 1, correct? When this x is less than 1 based on the ratio test. Hence, the radius of convergence is r equal 1. Interval of convergence. Find the interval of convergence of sigma n equal 1 to infinity, x to the power of n divided by n. Again, we use the method of the ratio test by computing the absolute value of an plus 1 divided by an, with an being x to the power of n divided by n. So let's find it out. An plus 1 over an is equal to x to the power of n plus 1 over n plus 1 divided by xn over n. Let's flip the denominator and the second quotient. So it is equal to xn plus 1, which is also equal to xn times x, divided by n plus 1, multiplied by n over xn. So we flipped this quotient. Now, xn can be factored out, and we are left with nx divided by n plus 1. So, equal x in absolute value times n over n plus 1, because n is always positive, taking the limit of x as x multiplied by n divided by n plus 1 as n approaches infinity is equal to x. Why? Because limit of n over n plus 1 would be negligible, is equal to n over n equal 1. Multiplied by x, so we are left with x, which should satisfy the condition of x being less than 1. Hence, r equal plus 1. Okay, now, given that the absolute value of x is less than 1, which means that x plus x is less than 1, and minus x less than 1, which means that x should be greater than minus 1. Hence, the scope of convergence is minus 1 being included, all the way to plus 1 excluded. At x equal 1, you have, and that's why, 1 to the power of n divided by n. 1 to the power of n is simply 1 over n. This series diverges. That's why for x equal 1, it should be an open side. Okay? Why? Because there is no limit. The series diverges. Meanwhile, for x equal minus 1, sigma of minus 1 to the power of n over n, as we've seen in former examples, it converges. Hence, the interval of convergence is from minus 1 included, closed from one side, all the way to plus 1, but plus 1 is open. Plus 1 is excluded. Why? Because for x equal 1, the series blows up to infinity. It diverges. Taylor series of Ex. Find the Taylor series of Ex centered at 0. First, all derivatives of Ex give us Ex as a reminder of Taylor series. So when we develop a function as a Taylor series, that would be the development. F of x, when the function is centered around 0 for x equals 0, is equal to f of 0 times x to the power of 0, which is 1 by the way, divided by 0 factorial, which is also 1, plus first derivative of f at 0 times x to the power of 1, which is x, divided by 1 factorial, plus second derivative of f around 0 times x squared divided by 2 factorial, plus third derivative of f around 0 times x to the power of 3 divided by 3 factorial, which is 6, etc. This is how we develop as Taylor series. Now, again, all derivatives of Ex give us Ex, thus Fn times Fn of 0 is equal to 1. So, because e to the power of 0 in all the cases would keep giving us 1. The Taylor series centered at 0 is the following. Sigma n equals 0 to infinity, Fn 0 over n factorial times x to the power of n. This is the main formula. Therefore, let us develop Ex in such case. So, Ex is equal to e to the power of 0 times x to the power of 0 over 0 factorial, which is 1, by the way, plus e0 again times x to the power of 1 over 1 factorial plus e0, because all of the derivatives are e around zeros, that would be e0, times x squared over 2 factorial plus e0 x3 over 3 factorial, which would give us 1 plus x squared over 2 factorial over 2 plus x3 over 3 factorial, which is 6, etc. This is the Taylor series development of Ex centered at x equals 0. MACLAURIN series for sin x. Find the MACLAURIN series for sin x. By the way, for MACLAURIN series, when you are centered at x equals 0, it becomes just like Taylor series. What are the derivatives, first, second, third, etc. of sin x? That would be the alternation of sin x, then cosine x, then minus sin x, minus cosine x, again plus sin x, cosine x, etc. You see, there's an alternation. Around 0, this would give you sin 0, 0, cosine 0, 1, 0, minus 1, and you keep going. 0, 1, 0, minus 1. So, you have the sequence 0, 1, 0, minus 1. And you simply start setting, okay, so again, the MACLAURIN or Taylor is given by f equal f0 times x to the power of 0 over 0 factorial plus first derivative at 0 times x over 1 factorial plus second derivative 0 times x squared over 2 factorial plus f third 0 times x3 over 3 factorial, etc. So sin x is developed as, okay, 0 times 0. Okay, so 0 is the first term, then 1, the second term, which is x, correct? 1 times x, then the third term, that would be 0. 0 times x squared, so this cancels out. Minus 1 times x3 divided by 3 factorial. Then the fourth, so you notice that always the even numbers keep cancelling out. Why? Because they would be multiplied by 0. Okay, however, the odd numbers are available. So x5 divided by 5 factorial. I will rewrite it more neatly. So sin x is equal to x minus x3 over 3 factorial plus x5 over 5 factorial. And it keeps alternating between positive and negative term. Now let's try to figure out the formula. So sin x is at first a sum, sigma from n equal to 0 all the way to infinity. Now, first you have the alternating term that keeps swapping or oscillating from a negative to a positive value, but its first value is positive. So the term being multiplied by x here is positive, which is minus 1 to the power of n when n starts with 0, because anything to the power of 0 is plus 1, multiplied by x to the power of 2n plus 1. With n equals 0, this becomes x. Okay? Divided by, also for n equals 0, this remains 1. Okay? Over 2n plus 1, which is the term here, and factorial. So, for n equal 1, what does it become? Of course, for n equals 0, this would be x. For n equal 1, for example, test the validity. N equal 1 gives us minus 1 times x to the power of 2 times 1, 2 plus 1, 3, over 2n plus 1, which is also 3 factorial, and giving us a negative term. So this becomes minus x3 over 3 factorial. Right after it, so minus 1 to the power of 2, it becomes plus 1, correct, times x to the power of 2 times 2, which is 4 plus 1, 5, over 5 factorial. Convergence of a sequence of functions. Determine whether f n x is equal to x over n converges pointwise on R. First, x belongs to our scope, which is the real numbers. F n x equal x of n. As n approaches infinity, it approaches 0. Now, it is important to establish that x is a real number so that it can be divisible by n. Okay? N approaching infinity, x over n approaches 0. Hence, fn approaches 0 as well for every x. That's why fnx approaching 0 converges pointwise on R. Let's determine whether the same function converges uniformly on 0, 1, which is a compact interval. In other words, it's closed from both sides, 0 and 1, and it is bounded. We compute fnx minus 0, which is the first bound, is equal to x, an absolute value, divided by n. So, x belongs to the closed interval 0, 1. Both 0 and 1 are included. We have x in absolute value is less than or equal to 1. Thus, fnx in absolute value is less than or equal to 1 over n, given the fact that x in absolute value is less than or equal to 1, correct? Taking the supremum of fnx equal 1 over n, correct? X belonging between 0 and 1. Since 1 over n approaches 0, the convergence is uniform. Hence, fnx equal x over n converges uniformly on the entire interval 0, 1. So, in this chapter, we covered the following topics: geometric and harmonic series, comparison, ratio, and root tests, alternating series, absolute and conditional convergence, power series and radius convergence, MACLAURIN, Taylor expansions, pointwise and uniform convergence. Infinite series are fundamental throughout real analysis. Differential equations, mathematical physics, probability theory, and functional analysis. Hope you enjoyed the chapter. Module 7, multivariable analysis. In this part, we cover, of course, through practice and exercise, the following topics: functions of several variables, partial derivatives, directional derivatives, gradient vectors, differentiability, chain rule, Jacobian matrices, Hessian matrices, critical points, optimization, multiple integrals, and change of variables. Find the first order partial derivatives of fxy equal x squared y plus 3xy squared. First, we start by treating y as a constant and we differentiate in respect of x. So, partial derivative of f in respect of x is equal to partial in respect of x of x squared y plus 3xy squared, equal to simply 2xy plus 3y squared. Why is that? Because y is regarded as a constant. So we kind of ignore it. And that would be the partial derivative in respect of x. In respect of y, x is considered or treated as a constant. So partial derivative of f in respect of y is equal to partial in respect of y of x squared y plus 3xy squared equal to x squared plus 6xy. Remember, x is treated as a constant. Hence, these are the partial derivatives. Fx is equal to xy plus 3y squared. Fy, lowercase fy, is equal to x squared plus 6xy. Second partial derivatives is when we derive twice. Find all second order partial derivatives of fxy equal x to the power of 3 times y squared. At first, we compute the first order derivatives, which are, first in respect of x, fx is equal to 3x squared times y squared. Y squared is constant in such case. Fy, which is deriving in respect of y, is equal to x to the power of 3 times 2y. Correct? So 2 has been simply translated here to the left. So it is the same as saying x to the power of 3, x did not change in this case, times 2y. We simply derived in respect of y. Now compute the second derivatives. The annotation of the second derivative is given by fxx, meaning that we are deriving in respect of x for the second time. You simply derive the original derivative again in respect of x. So this gives us derivative of 3x squared y squared equal 6xy squared. Fyy, which is the second derivative in respect of y, is equal to 2x3 because y has disappeared. Mixed partials, so now you have also the second derivative of fx in respect of y, correct? So fx, which is 3x squared y squared, we are deriving it in respect of y. It gives us 6x squared y. And also fyx, meaning the second derivative of fy, which is the first derivative in respect of y, we are deriving it, but this time in respect of x. So it is the partial derivative of 2x3y in respect of x, which is 6x squared y. Now you notice something, by the way, that fxy is equal to fyx. This is very important. fxy is equal to fyx, hence fxx is equal to 6xy squared, fyy to x3, and fxy is equal to fyx equal 6x squared y. It means that the curve is closed, as I remember. I will try. This is used in the divergence, okay, in Green's theorem, by the way. So, but we will check it out. I will fact check it afterwards. Gradient vector, find the gradient of fxyz is equal to x squared plus y squared plus z squared. What is the gradient? Gradient f is the partial derivative of f in respect of x plus partial derivative of f in respect of y plus partial in respect of z. And you place it as a vector, or you multiply it by I, j, k, which are the three coordinates of a 3D space. The annotation of the gradient is nabla. Nabla f is equal to, again, it is either partial derivative of f in respect of x times I, which is the x coordinate, plus partial unitary vector of the x-axis, partial f in respect of y times j, unitary vector, plus partial f in respect of z times k. Or you place it as a vector annotation, which is partial f in respect of x, partial f in respect of y, in respect of z. Compute partial derivatives. Fx is equal to 2x, because all the others are considered as constants, so they zero out. The same thing for fy, which is partial derivative in respect of y, is equal 0 plus 2y plus 0. And f of z, partial derivative in respect of z, is equal to 0 plus 0 plus 2z, because in respect of z, x and y are constants. Therefore, nabla f is equal to x, 2y, and 2z, the three components we just evaluated. Directional derivative problem. Find the directional derivative of fxy equal to x squared plus y squared at 1, 2. In the direction u equal 3 over 5, 4 over 5. First, we need to evaluate the gradient, which is the equation of the plane tangent against the curve. Now, when you get it at a specific point, that would become the vector tangent to the curve at that point. So the directional derivative is simply the dot product between the gradient of the function at that point with the unitary vector. First, we compute the gradient. So nabla f is equal to fx, fy, which are respectively the partial derivative of f in respect of x and of f in respect of y, equal partial derivative in respect of x, that would be 2x because y would be constant, and in respect of y, 2y. At 1, 2, you simply plug in 1 in x and 2 in y, which gives you 2, 4. Now compute the dot product. So it is 2, 4, which is nabla f at 1, 2, dot 3 over 5 and 4 over 5, which is the direction u of this unitary vector, is equal to 2 times 3 over 5 plus 4 times 4 over 5, which is 6 over 5 plus 16 over 5, equal 22 over 5. That is the directional derivative duf at 1, 2. Okay? In the direction of u, of course. 22 over 5. Tangent plane problem. Find the tangent plane to z equal x squared plus y squared at point 1, 1, 2. Now, as a side note, when I was referring before to the gradient being the tangent, it wasn't exactly a tangent. So it might need a little bit of correction or more accurate adjustment over what I've said to be more accurate or to be more precise and clear, rather. The gradient of a function is not the equation of the tangent, nor the tangent itself, but rather it is the slope of the tangent against the curve. So just like in simple variable calculus, when you have a simple variable calculus function, the derivative of that function at a point would indicate whether the curve of the function is rising, if the derivative is positive, or if it's descending or diving when it is negative, or if it's leveled to the x-axis, meaning that in such case the slope would have an angle of 0 against the x-axis. So the tangent against the curve in such case would be parallel to the x-axis. As for the tangent plane formula, it is given by z minus z0 is equal to fx, which is the derivative of f in respect of x, x0, y0 times x minus x0 plus fy x0, y0 times y minus y0. The function is fxy equal x squared plus y squared. First derivative in respect of x is equal to x, in respect of y equal to y. At 1, 1 for x and y, f11 equal to fy11 equal to as well. We substitute also z0 by 2, so you end up with z minus 2 equal 2 times x minus 1. We're simply plugging back the values, by the way, plus 2 times y minus 1. So z equal 2x plus 2y minus 2, and that would be the equation of the tangent. Clear? Hopefully it's straightforward. Let us go about it again to make it clearer. So the formula is z minus z0 is equal to derivative of x in respect of x times x minus x0 plus derivative of x in respect of y times y minus y0. Note here that x0, y0, and z0 are simply the coordinates of the point. So x0 equal 1, y0 1, and z0 equal 2. F of x is the derivative of f. By the way, f is simply z here. So if it is, actually, it can be expressed as fxy equal x squared plus y squared. This is the same thing as z equal x squared plus y squared. Derivatives of f in respect of x and y give us fx equal 2x, fy equal 2y. And then you replace x and y by 1 and 1 respectively, which are also the coordinates of the point. So f1 is equal to, and for x equal 1, and fy for y equal y0, which is 1, is equal to. Then you plug it back in the equation. So z minus z0, which is 2, equal to derivative of f in respect of x for x equal x0, which is 2, times x minus x0, which is 1, plus fy0, which is 2, multiplied by y, minus y0, which is 1. So z equal 2x minus 2 plus 2y minus 2 plus 2. We moved the 2 from the left to the right. These cancel out, and you end up with the equation z equal 2x plus 2y minus 2. And this is the equation of the plane at this point that is tangent to the curve or to the function. Chain rule. Suppose z equal x squared plus y squared, where x equal t squared and y equal sine t or sin t. Find dz over dt, which is the derivative of the function in respect of t. Here we have to use the chain rule as well, just as we did it in the simple variable calculus. The formula is the following. Derivative of z in respect of t is equal to dz in respect of x, partial derivative of z in respect of x, times partial derivative of x in respect of t, plus partial derivative of z in respect of y, times partial derivative of y in respect of t. So this is the formula. Let us now apply it. So partial derivative of z in respect of x is simply 2x, because z is equal to x squared plus y squared, correct? So dz over dx equal 2x. dz over dy, partial derivative of z in respect of y, is equal to y. Now, partial derivative of x in respect of t, what is x? We know that x is equal t squared. So partial derivative of x in respect of t is 2t, and partial derivative of y in respect of t is equal to cosine t. Then you multiply them together. Now you plug them back into the main equation. So this is what we get. dz over dt is equal to 2x, which is dz in respect of x, times 2t plus 2y times cosine t. We need to replace or substitute x and y by their values in respect of t. We know that x is equal to t squared and y equal sin t. So you simply place t squared at the place of x and sin t at the place of y, we end up with dz over dt equal 2 times t squared times 2t, which is 4t3, plus 2 sin t cosine t. Hence, dz over dt is equal 4t to the power of 3 plus 2 sin t cosine t. Jacobian matrix. Find the Jacobian matrix of fxy equal x squared minus y xy. This is how we form the Jacobian matrix. J is equal to partial derivative of f1. f1, by the way, fxy is broken down into two subfunctions, so to speak, which are f1 and f2. So it is partial derivative of f1 in respect of x, partial of f1 in respect of y. This is the first row of the matrix. The second row, made of two elements, of course, is partial derivative of f2 in respect of x, which is xy in this case, partial derivative of f2 in respect of y. So, two rows, two columns. Let's evaluate it. So, f1 is equal to x squared minus y, which is the first component of fxy. Partial derivative of f1 in respect of x is equal to x, given that y is considered a constant in such case. Partial derivative of f1 in respect of y is equal to minus 1, because x is constant in this time, okay, in such case. Carrying over from the previous slide, here you have partial in respect of x equal to x in respect of y equal minus 1. Both for f1. Now, for f2, which is equal to xy, partial derivative of f2 in respect of x is equal to y, because x would be y would be constant. We derive in respect of x. Partial derivative of f2 in respect of y is equal to x. Hence, if you place them back within the Jacobian matrix, so here for xy, which is f2 partial derivative in respect of x, gives us y. In respect of y, gives us x. Kind of confusing a little bit. Let's place them within the matrix. So J is equal to, again, partial f1 in respect of x, f1 in respect of y, partial f2 in respect of x, f2 in respect of y, equal to the following: 2x, then minus 1, and y x. Find the critical points of fxy equal x squared plus y squared minus 4x minus 6y. Now, as a reminder, and we are carrying that over from simple variable calculus, a critical point is where the tangent slope at the curve is 0. In other words, where the tangent is parallel to the x-axis. So practically or technically what's happening, it is the point at which the curve would be going down, then it changes direction and starts going up. And this is when it achieves either a minimum or a trough, which is among the minimums. And vice versa also for, like, when it's going up, it's climbing up, okay, you would have a positive slope. Then once it starts going down at a specific point, which is the point of change of direction, the tangent against the slope would be parallel to the x-axis. So that actually the tangent against the curve would be parallel, so the slope would be 0. Hence, that would also be another critical point. In such case, it would be among the maximums or a maximum or the maximum point, the highest point of the curve, which would be a peak. In multivariable calculus, we apply the same concept, but this time on different axes, on different dimensions, or on different variables, so to speak. The same concept. So critical points occur where fx, the partial derivative of the function fxy in respect of x, would be equal to 0, and fy, or partial derivative of fxy in respect of y, would be equal to 0. Let's compute the derivatives. So fx is equal to partial derivative of fxy in respect of x. So y would be considered a constant in such case, would be annihilated on 6 minus 6y and on y square. So we only derive x squared and minus 4x, which begets us 2x minus 4. Fy, derivative of fxy in respect of y, you derive y squared and minus 6y, because x in such case is a constant. It becomes 0. So you get 2y minus 6. Now, we need to find the points at which the slope of the tangent, which is fx, becomes 0. So, and for fy, the same thing. So you set fx and fy equal 0 to get the critical point, which is on x and y, both. So fx equals 0, you simply set 2x minus 4 equals 0. Hence, 2x equal 4, x equal 4 divided by 2, which is 2. This is the first coordinate of the point. And for the second coordinate, and apparently it's 1 point, 2y minus x, which is fy, equals 0. 2y minus 6 equals 0. So 2y equal plus 6, and y equal 6 divided by 2, which is 3. Hence, the critical point is 3. This is the point at which the slope of the tangent against the curve would be 0. So the tangent would be parallel to the reference axis, or axis system, which is xy in such case. This will be at a point where the function was going up, then it starts coming down, or vice versa. It was going down, then it climbed. So either a maximum or a minimum, respectively. Now for the same exercise, let's get the second derivative. By the way, second derivative gives us the concavity, which is whether the mouth of the curve is opened up. In such case, it would be that the second derivative would be positive, or if it's opened down, meaning that the concavity would be negative. The function is going downwards. So let's compute the second derivatives. First, the first order derivatives are the following. Fx is equal to x minus 4 from the previous example. Fy equal 2y minus 6. Second derivative is equal to, in respect of x, in respect of y, it's equal to also. Now fxy, which is the second derivative of fx in respect of y, is equal to 0. And fyx, which is second derivative of fy in respect of x, is equal to 0. Compute the discriminant. So d is equal to fxx times fyy minus fxy squared, which is 2 times 2 minus 0 equal 4. That's the discriminant. Now, the discriminant d is greater than 0. That's the discriminant. It's important. And fxx is also greater than 0. So the critical point is a local minimum. Hence, 2, 3 is actually a local minimum. How have we come up with this solution? To make it a little bit clear and to clarify the conclusion that we got to, which is that we have a local minimum and a, so to speak, you have a local minimum, so you have a positive concavity. So how did we get there? And what is the discriminant to begin with? At first, the discriminant is simply the determinant of the following. You have on the first row, it's like a determinant of the matrix. What are the different elements of the matrix? They are simply the second derivative of fx in respect of x, then second derivative of fx in respect of y, which is second derivative in respect of y of the first derivative in respect of x. Then second derivative of fy in respect of x, second derivative of fy in respect of y, equal to fxx times fyy minus fxy times fyx, which is, by the way, the same thing here. So it is equal to fxx times fyy minus fxy squared. Once we get the value of d, let's check how it is relevant in finding if there are either local minimums or maximum for the function, and when we don't have neither minimum nor maximum, which is called in such case a saddle point, just like the saddle of a horse. Okay, that would be a point on the curve where the tangent would be parallel to the ground, parallel to the axis system, okay, to the xy plane, so to speak. First case, if d is greater than 0, we check fxx, which is the second derivative of f in respect of x. If it's greater than 0, it means that the concavity of the function is upward. Its mouse, the mouse of the curve, is upwards. So in other words, you have a local minimum. Why is that? This is given the fact that at this point the function had stopped dropping or diving downwards and it started climbing upwards. This change of direction means that you have a trough in such case, since the concavity is opened upward. Now, if fxx is less than 0, it means that the concavity is turned downward. The mouse of the curve is opened downward. So you have a local maximum. In other words, the curve at that point had stopped climbing and started diving. So you have a peak instead of a trough. By the way, for the first case, this is what we have in our own problem, in our own example. If d is negative, less than 0, doesn't matter what the value of fxx would be. In such case, you would have a saddle point. What is a saddle point? It means that the function is neither climbing nor diving. So you won't have neither minimum nor maximum. It's like a saddle of a horse. The saddle of a horse is like parallel. It doesn't have minimums or maximum. It's a flat surface in that area. Finally, if d is equal to 0, then it is undetermined, meaning that we don't know. Okay, it's unsolvable. Double integral. Compute double integral on a surface R of x plus y dA, where R equal the interval from 0 to 1 and from 0 up to 2. Okay, where of course 0 to 1 is the scope on the x direction on the x-axis, and 0 to 2 is the scope on the y direction. So 0 to 1 and 0 up to 2. This is the area where we are evaluating this integral. How do we solve it? You start with the outward integral, which is dx. By the way, whenever you have dx or dy at the end, which is at the outer boundary, that would be solved last. So you would solve the inner integral first, then you would solve the outer integral. Let me explain what do we mean by that. At first, it is integral from 0 to 1, which is on the x-axis, of integral from 0 up to 2. On the y-axis, x plus y, dy dx. You notice something? Dy is for the inner integral that would be solved first. Then the solution of that would be solved in respect of dx at the outer integral. Let us start with the integration of x plus y in respect of dy. Of course, this is the interval on the y-axis, which is the scope from 0 up to 2. Integrating in respect of y, so it is equal to integral from 0 to x plus y dy equal to xy, and again, in such case, x is considered as a constant, plus y squared over 2 between 2 and 0. You see? So we solve that, you get for y equal to, this is 2x plus 2 squared over 2, which is 4 over 2, or 2, minus 0 plus 0. So for the lower bound, doesn't matter, it cancels out anyway. So you end up with 2x plus 2 for the inner integral. Then you solve it in respect of the x, so which is this one here. Integral from 0 to 1. 2x plus 2 dx is equal to 2x squared over 2 plus 2x between 1 and 0, correct? Which is 2x squared plus, over 2. We factor out 2, so you end up with x squared plus 2x between 1 and 0. 0, the lower bound, it will cancel out anything, so it doesn't matter. But the upper bound is 1, so this renders into 1 plus 2, which is 3. Hence, the value of this integral is 3. Change of variables. Use polar coordinates to compute double integral over d, where d is a unitary disk, of x squared plus y squared dA. Now, when we are working with a circular pattern or like a disk space, the classical Cartesian coordinates can no longer work the same way. It becomes more complicated in order to evaluate the integral. Hence, we need to transfer into the polar coordinates, where you have x is equal to r cosine theta, y equal r sine theta, and dA, which is dx dy, becomes r dr d theta. And we are about to understand how we moved from the Cartesian coordinates into polar coordinates. At first, imagine the unitary disk like this. So you have, this is x and this is y, correct? So, and what is that? This is the radius of the circle. Now, cosine theta is equal, theta is the angle, and r is the radius of the circle again. Cosine theta is equal to the adjacent segment, which is x, divided by the hypotenuse, which is r. Hence, x is equal to r cosine theta. Now, for y, sine theta is equal to opposite side length, which is y, divided by the hypotenuse, which is r. Hence, y equal r sine theta. This is how we came up with the values of x and y in terms of r and theta. Now, as for the transfer or transformation from dA into dr d theta, okay, r dr d theta. How? have we come up with that? This is called the Jacobian transformation. So it is simply the derivative of x and y in respect of r and theta on two lines. Let me break it down. So, and we evaluate the determinant, by the way. This is how you come up with the Jacobian. So, J is equal to first derivative of x in respect of r, derivative of x in respect of theta, then of y in respect of r, y in respect of theta, equal to the following. Derivative of x is equal to r cosine theta in respect of r, so it becomes cosine theta. Then derivative of x in respect of theta, it is r times minus sine theta, correct? So minus r sine theta. Now derivative of y in respect of r, y equal r sine theta, so it becomes sine theta. Derivative of y in respect of theta, it becomes r cosine theta. Let's evaluate the determinant. So you simply multiply cosine theta by r cosine theta. So it becomes r cosine square theta minus multiplying sine theta by minus r sine theta. So minus r sine square theta, which is equal to r cosine square theta plus r sine square theta equal, we factor out r, or we place r as a common factor, common multiplier, times cosine square theta plus sine square theta. And you know that cosine square theta plus sine square theta is equal to 1. Hence, this becomes equal to r, and the transformation of dA into dr d theta is equal to r dr d theta, and r being the Jacobian of the transformation. Let's evaluate the integral. At first, what is x squared plus y squared? Remember that x equal r cosine theta, y equal r sine theta, and dA equal r dr d theta. X squared plus y squared is equal to r squared cosine square theta plus r squared sine square theta, which is r squared times cosine square theta plus sine square theta, which is 1. So we end up with r squared. dA is equal to r dr d theta. Now, double integral over the disk of x squared plus y squared dA. This is, now, remember, dA becomes r dr d theta. So, first, d theta is the change of the angle. The angle is on a disk, so from 0 all the way to 2 pi, correct? It's a full round, full circle. And for r, the radius is from 0 to r, which is r equal 1 here, because it's a unitary circle. So, integral from 0 to pi, integral from 0 to 1 of x squared plus y squared, it is equal to r squared times r dr d theta, which is the second r here is for the transformation of the Jacobian. So you end up with integral from 0 to pi, from 0, 1, r to the power of 3 dr d theta. Remember, the outermost differential is for the final integration, and the innermost, we start integrating from the innermost to the outermost. The innermost is dr. So you solve for dr, this internal integral, then the solution of that, you solve it in respect of the theta. So we had on the inside integral between 0 and 1 of r3 dr, which becomes r to the power of 4 divided by 4 over or between 1 and 0, which is 1/4. So this is 1/4 minus 0. Okay, now then integral between 0 and 2 pi, 1 over 4 d theta. This is equal, now 1/4 is a constant, so you can remove it to the outside. So you get 1 over 4 integral 0 to pi d theta, which is theta between 2 pi and 0. Okay, this is 1 over 4 times theta between 2 pi and 0, which is 2 pi times 1/4 equal pi over 2, because you factor out or you divide by 2 both numerator and denominator. Hence, the value of this double integral is pi over 2. Find the Hessian matrix of fxy equal x to the power of 3 plus xy plus y squared. Now, in case I still remember, the Hessian matrix is the following. It is fxx, second derivative of f in respect of x, second derivative of f in respect of y, which is derivative of fx in respect of y, then second derivative of f y in respect of x, and derivative of fy in respect of y. Let's start with the first derivative of f in respect of x. This is equal to 3x squared plus y plus 0, because y is considered a constant. Then derivative of f in respect of y, and by the way, here you have the same result, but I'm trying to solve them manually. So fy is equal to derivative of fxy in respect of y. It gives us x plus 2y. x3 becomes 0. Now fxx, which is second derivative of fx in respect of x, this is equal to 6x. fxy is equal to second derivative of fx in respect of y, 1, and fyx, so derivative of fy in respect of x, that would be 1. fyy, derivative of fy in respect of y, that would be 2. So let's place them in the matrix. So again, 6x to 1, and the final one should be 2. Okay, so fxx is 6x, fxy 1, fyx 1, and finally fyy 2, which is correct. This is the Hessian matrix. Optimization with constraints. Find the maximum and minimum values of fxy equal to xy, subject to the circle x squared plus y squared equal 1. We use what is called the Lagrangian multipliers. What are Lagrange multipliers? So we define the function gxy such that it is equal to x squared plus y squared minus 1, which is, we moved this one here to the left. We set nabla f, which is the gradient of f, is equal to lambda gradient of g. Correct? So what is the gradient of f at first? Gradient of f is the set of derivatives of f in respect of x and y respectively. So it's simply fx, fy. Derivatives of f in respect of x for the first component of the vector or the function. Then derivative of f in respect of y. It gives us in respect of xy, in respect of yx. Now, nabla g, which is the gradient of g, is equal to gx also, so derivative of g in respect of x, and that of g in respect of y equal for gxy. Okay, so gx is equal to x, the rest is 0. gy is 2y, the rest is 0. So 2x, 2y. Now, y equal to lambda x, correct? So, y, what is y? Y is equal, because nabla f is equal to lambda nabla g, according to the formula, okay? The Lagrangian multipliers. So this is how we get the maximum and minimum. Y is equal to lambda times 2x, okay? Why is that? Because x of nabla f should be equal to x of nabla g, okay? So these two quantities are equal to each other, but one of them happens to be a y value in the position or the locale, so to speak, of x. So y is equal to lambda x. As for x is equal to lambda to y, correct? So x equal lambda times 2y, or x equal to lambda y. Given what we have observed from the previous slide, you have y equal to lambda x and x equal to lambda y. Let's multiply x and y together. You get 2 lambda times 2 lambda, or 2 lambda squared, which is 4 lambda squared, times x, y. Now, this observation also leads to the fact that x is equal to plus minus y. Now, using the constraint x equal to plus y, if x equal to y, then in the equation above, x squared plus y squared equal to 1 leads to x squared plus x squared equal 1. Hence, 2x squared equal to 1. And x squared would be equal to 1/2. So x equal to plus minus 1 over the square root of 2. Thus, f equal to xy is equal then to x squared. So you multiply x by itself. This gives us 1 over square root of 2 times 1 over square root of 2, or 1/2. Now, if x is equal to minus y, then f is equal to x times minus y, or times minus x, multiplied by minus x, which is then 1 over square root of 2 times minus 1 over square root of 2. So this becomes minus 1/2, which is the same as the f in the above, except the difference is you have a negative sign. Hence, f max is equal to 1/2 and f min is equal to minus 1/2. Differentiability. Determine whether function fxy equal to x squared plus y squared is differentiable everywhere. For a multivariable function to be differentiable, it should have continuous partial derivatives. So a function with continuous partial derivatives is differentiable anywhere on R. Let's compute the partial derivatives. So f of x, which is the partial derivative in respect of x, or partial of fxy in respect of x, as a more professional annotation, is equal to x. Then partial derivative of y, which is partial fxy over y, is equal to y. Both of them exist and they are continuous on R squared. Therefore, f is differentiable everywhere. Hence, fxy is equal to x squared plus y squared is differentiable on R squared. Finally, these exercises have demonstrated and covered the following topics: partial and directional derivatives, critical point classification, multiple integrals, gradient vectors, tangent planes, Jacobians and Hessians, polar coordinates, transformations, optimization under constraints, and multivariable chain rule. Multivariable analysis extends the ideas of single variable calculus into higher dimensional spaces and forms the foundational of differential geometry, optimization theory, mathematical physics, and advanced analysis. Module 8, Metric Spaces and Topology. Here we cover metric spaces and topology concerning the following topics: metric spaces, open and closed sets, convergent sequences, compactness, completeness, continuity in metric spaces, connectedness, dense sets, Cauchy sequences, and topological properties. Verifying a metric shows that dxy is equal to absolute value of x minus y defines a metric on R. First of all, what does it mean, a metric? The metric is a distance measurement. As we know already that any absolute value is actually a measurement of distance. So this means it doesn't matter whether x or y is the greater among the two components. X minus y in absolute value gives us the distance between x and y. So to verify that D is a metric, we check the metric axioms. First, non-negativity. So for all x, y within R, within the real numbers, x minus y should be greater than or equal to 0. This is the first criteria. Thus, the distance from x to y is greater than or equal to 0. Second, identity of indiscernibles. So distance between x and y equal to 0. Therefore, x minus y in absolute value is equal to 0. Or in other words, x is equal y. Third criteria, symmetry. So distance of xy should be equal to x minus y in absolute value or y minus x in absolute value, giving back distance from y to x. Or to put it in a different way. So if we measure the distance from x to y, it should reproduce the same value as if we are measuring the distance from y to x. From x to y, it is x minus y in absolute value. That should be equal to y minus x in absolute value. 4, triangle inequality. So x, y, z belong to R. For all x, y, z belong to R, x minus z in absolute value should be less than or equal to x minus y in absolute value plus y minus z in absolute value. So there exists a value between x and z such that x minus y in absolute value, the distance between x and y, plus the distance between y and z, which is y minus z in absolute value. Between x and y, it is x minus y in absolute value. So the sum of these two distances should be greater than or equal to x minus z in absolute value. In other words, the distance from x all the way to z. Therefore, distance from x to z should be less than or equal to distance xy plus dyz. Okay? Hence, all metric axioms hold, and distance xy is equal to x minus y is a metric on R. Let's go over the required criteria and conditions for dxy to be a metric again. And this time, we will list them as a checklist, starting at first from the first required criteria, which is non-negativity. Non-negativity states that dxy is always positive, always greater than or equal to 0. In other words, the distance, which is the distance, okay? So, which is absolute value of x minus y, always greater than or equal to 0, but never negative. A distance, a metric, is never negative. Second criteria, identity of indiscernibles, which means that if the distance between x and y is equal to 0, then this can be written as x minus y, an absolute value, equal 0, or in other words, it leads us to the conclusion that x is actually equal to y. Third criteria, which is symmetry. Okay, so symmetry means that the distance from x to y, which is equal to the absolute value of x minus y, is equal to y minus x, or in other words, is equal to the distance from y to x. So, geometrically, if we are measuring the distance from x to y, it should give us the same value as when we do the inverse, okay? So, in reciprocity, if we measure the distance from y to x, it should give us the same value. For triangle inequality, by the way, I placed the acronym for each point to the left of its dot. So here you have symmetry, here identity of indiscernibles, and here non-negativity. For triangle inequality, what does it mean? Let's say you have 3 points, x, y, and z, within the R space. So these are 3 real numbers, such that y is between x and z. So x minus z in absolute value, or in other words, the distance between x and z, is always less than or equal to distance between x and y, which is x minus y in absolute value, plus distance between y and z. So y minus z absolute value. Therefore, dxz is less than or equal to dxy plus dyz. And this is how you prove that this is a metric axiom. Open balls. Describe the open ball B 2, 1 over 2 in R and this interval. So what is an open ball? An open ball is defined by BAR equal value x within or existing in R, this is the system, such that the distance from x to A should be less than R. Once again, VAR is designated by x among the real numbers belonging to the real numbers scope, such that distance from x to A should be less than R, with A equal to, and R, which is like the radius, is equal to 1/2. What is the distance from x to A? It is simply x minus 2 in absolute value, and that should be less than R, which is 1/2. Now, x minus 2 in absolute value can either give minus x plus 2 or plus x minus 2. For minus x plus 2, and by the way, remember that x minus 2 in absolute value is less than R, which is 1/2. This is the main criteria. But we have two options, either minus x plus 2 or x minus 2. These both can translate into the absolute value of x minus 2. For minus x plus 2, so it gives us minus x plus 2 less than 1/2, hence minus x less than minus 2 plus 1 over 2, minus x less than minus 4 plus 1 over 2 minus 3 over 2. Now we need to multiply by minus to get rid of the sign, so this would flip the inequality into greater than. Hence, it becomes x greater than 3 over 2. then plus 3 over 2. As for the second criteria, which is x minus 2. So you place x minus 2 less than 1/2, which means x less than 2 plus 1/2, which is equal to 5, because 2 times 2, 4 plus 1, 5 over 2. Hence, x is less than 5 over 2. So, x is between 3 over 2 and 5 over 2. X greater than 3 divided by 2 less than 5 over 2. Therefore, the ball is 3 over 2 and 5 over 2. Open sets show that the interval 0, 1 is open in R. A set U is open if for every x within U there exists epsilon, a very small number but still greater than 0, such that bx epsilon is included within the set U. And x, given that x is within the open set between 0 and 1, strictly greater than 0 and less than 1. Let's break it down a little bit. X exists within the open interval 0, 1. Now remember, given that it is an open interval, x can be neither of these two values of the lower and upper bound. So it cannot be equal to 0 and 1. Hence, x should be strictly greater than 0 and less than 1. What else is between 0 and 1? It is epsilon, which is a very small value, positive but still very small, which means that epsilon is also between 0 and 1. We need to choose two values such that one would be greater than 0, the other would be less than 1. So if we consider x minus epsilon, despite the fact that epsilon is a positive value, it is very small. X minus epsilon would still be greater than 0. As for x plus epsilon, if you add epsilon to x, epsilon again very small, tiny positive value, x plus epsilon should remain less than 1. Now, if we go over it again, so you have x greater than 0, less than 1. So epsilon should be here, okay? And if you move x to the right, so you get 0 less than epsilon less than 1 minus x. So epsilon should be the minimum value between x, whatever that is, and 1 minus x, okay? Here you can add x to the left, and here you remove x, okay? So epsilon between x and 1 minus x basically, which leads us to x minus epsilon greater than 0, x plus epsilon less than 1. Thus, bx epsilon is included within the open set 0, 1, hence 0, 1 is open in R. Let's break it down in a more simpler manner. So consider that we have 0 and 1 being respectively the lower and upper bounds of the open set 0, 1, and they are not included. So since it is an open set, 0 and 1 are not part of the set. They are lower and upper bound, but not minimum and maximum values. Now x is between them. So x is somewhere between 0 and 1. So we need to choose epsilon such as it is at the minimum distance. So it's either from 0 to x, because epsilon would be a very small value. Okay, if x is very close to 1, then the distance from x to 1 would be 1 minus x. Okay, and the distance from 0 to x is x, correct? So let me try to simplify it. The distance from 0 to x is x again, but the distance from x to 1 is simply 1 minus x. Depending on the position of x, it can be either that the x distance from 0 to x is the smaller one, or that between 1 and x would be the smaller one. If x is all the way to the right, very close to 1, then 1 minus x would be much smaller than x, which is the distance from 0 to x. Hence, epsilon, which is a very small value, positive but still very small, is equal to the minimum value possible between x and 1 minus x. This is how we choose epsilon. Now remember that epsilon, despite the fact that it is a very small number, it's always greater than 0. Strictly greater than 0. And doesn't matter where you are within the interval, this open set between 0 and 1, remember that 0 and 1 are not included, and x minus epsilon should always be greater than 0. Because you can never get to 0. 0 does not even belong to the set. It is the lower bound, but not the minimum. In the same way, x plus epsilon can never reach 1. So x plus epsilon is always less than 1, no matter where x is. And given that, again, epsilon is a very small number, greater than 0 or positive, but still very small. Hence, bx epsilon is always included within the 0-1 interval, and 0-1 is open in R. Closed sets show that 0-1 between two square brackets is closed in R. A set is closed if it contains all its limit points. Let xn be a sequence in the interval 0-1, such that xn approaches x. Since xn is between 0 and 1, and in a way that xn greater than or equal to 0, less than equal to 1 for all n, taking limits preserves inequalities. So you have x itself is greater than or equal to 0, less than or equal to 1, just like xn. Thus, x exists within the closed interval, within the interval 0-1, and 0-1 contains all its limit points. So in other words, 0 and 1 are not only lower and upper boundaries, they are included within the set itself. Hence, 0-1 is closed, and actually it is also compact because you have lower upper bounds and also minimum and maximum. Convergence in metric spaces determine whether xn equal 1 over n converges in R. Let's examine the distance from xn to the origin in absolute value, of course. That's the distance. So it is the absolute value of xn minus 0 or that of xn, which is absolute value of 1 over n, equal to 1 over n. Since 1 over n approaches 0 as n approaches infinity, that would be the limit. So limit of 1 over n as n approaches infinity equal 1 over infinity equal to 0. We have xn approaching 0, therefore 1 over n approaches 0 in R. And of course, this means that it converges. Show that xn equal 1 over n is a Cauchy sequence. A sequence is Cauchy if for every epsilon greater than 0, there exists a value n such that mn greater than or equal to capital N, then the distance between xn, so x in function in respect of n, minus xm in absolute value, or the distance between xn and xm, is less than epsilon, which is a positive value but very small. Now, let's check xn minus xm in absolute value, which is the distance between xn and xm. This is equal to absolute value of 1 over n minus 1 over m, as you see over here. And this is definitely less than or equal to 1 over n plus 1 over m. Why? Because the absolute value would either give you 1 over n minus 1 over m, or you flip the sign. So, or minus 1 over n plus 1 over m. Okay, because it's a distance. So now mn is greater than or equal to capital N. If we assume that, then we can take capital N as a lower bound for these two numbers. Hence, 1 over lowercase n minus 1 over lowercase m in absolute value should be less than or equal to 2 over capital N. Why is that? Because it is 1 over n plus 1 over n. If n equal m equal capital N. Given that n has been chosen as lower value, 2 over n would be greater than or equal to 1 over n minus 1 over m in absolute value. Because as you decrease the denominator, the entire fraction or quotient increases. Just like when n approaches 0, the entire limit blows up to infinity. Hence, we get 1 over n minus 1 over m less than or equal to 2 divided by n. Remember that absolute value of 1 over n minus 1 over m is simply absolute value of xn minus xm. And this should be less than epsilon. So 2 over n should be less than epsilon. Let's start with that premise in order to be able to choose the value of n correctly. So 2 over n less than epsilon. You multiply n to the right side and you remove epsilon downwards. So 2 over epsilon should be less than n. Or, in other words, if you read it from right to left, n greater than 2 over epsilon. So, as we choose n value like that, and of course you can choose it like that, correct? Because n is so large. Hence, xn minus xm, an absolute value or distance between xn and xm, should be less than epsilon. So 1 over n is a Cauchy sequence. Completeness. Show that every convergent sequence in a metric space is Cauchy. First, as a reminder, what is a Cauchy sequence? A Cauchy sequence states that let there be a value epsilon greater than 0. There exists a number n, capital N, greater than 0, such that for m n, lowercase n, greater than n, xm minus xn, which means the distance between the sequence in respect of m minus the sequence in respect of n should be less than epsilon. Suppose xn approaches x. Let epsilon be greater than 0. Since xn is approaching x, there exists capital N, such as n greater than or equal to capital N. Hence, the distance between xn and x, which can be rewritten as the absolute value of xn minus x, should be less than epsilon divided by 2. Similarly, m greater than or equal to n, hence distance from xm to x is less than epsilon over 2. Using the triangle inequality, which states that the distance between xn and xm is less than or equal to distance from xn to x plus distance from x to xm. Given that x is somewhere between xn and xm. So distance from xn to xm is less than or equal to distance xn to x plus distance x to xm. Thus, distance from xn to xm is less than epsilon over 2 plus epsilon over 2 equal to epsilon. That's why you have epsilon over 2 there. Hence, xn is Cauchy, therefore every convergent sequence is Cauchy. Therefore, it was a mindful decision to pick the distance between xn and x, also the distance between xm and x, as less than epsilon over 2, so that the sum of those distances would be less than or equal to epsilon, or epsilon over 2 plus epsilon over 2. Determine whether 0, 1, the interval, is compact in R. The HEINE-BOREL theorem states that for a subset in R to be compact, it should be both bounded, meaning having a lower and upper bound, and also it should have the limits on these two bounds. It should be, in other words, closed. So, for it to be compact, both criteria should be met: boundedness and closeness. The interval 0, 1 is at first closed. Why? Because the boundaries, or like the lower and upper values, are included within the interval itself. Moreover, it is bounded because 0 is the lower bound and 1 is the upper bound. But also 0 is the minimum value and 1 is the maximum value. So 0 is minimum and infimum, which means the lower bound, and 1 is maximum and also supremum, or upper bound. Hence 0, 1 is compact. Determine whether 0, 1 is compact in R. First, as a reminder, for a set to be compact, it should be both closed and bounded. Now, is it closed? It is not closed, definitely. Why? Because 0 and 1, which are, by the way, the lower and upper bounds, they are not part of the set. So 0 is not a minimum and 1 is not a maximum. They are boundaries, so it is bounded, meaning that you have a lower bound, which is 0, which is the infimum, in other words, and 1 is the supremum, which is the upper bound. However, they do not belong to the set. So it's open and bounded, but still open, hence it's not compact. Let's consider the sequence xn equal 1 over n. It belongs to the open set 0, 1. So it can be sandwiched between 0 and 1. And 0 and 1, remember that they are not, they do not belong to the set. So xn approaches 0, however, never reaches 0, meaning that the limit of xn as n approaches infinity is equal to limit 1 over n approaching infinity, which is equal to 0. The limit is equal to 0, but the function never is. So xn approaches 0, but never is actually equal to 0, never gets there. Hence, 0 does not belong to the open set 0, 1. Thus, 0, 1 does not contain all its limit points. Therefore, it is not compact. Hence, 0, 1 is not compact. This is how we've proven that. Continuity in metric spaces shows that f of x equal x squared is continuous on R using sequences. A function f is continuous if, as xn approaches x, fxn approaches f of x. Suppose xn approaches x. Then, in such case, fxn would be xn squared. So, since multiplication preserves limits, as xn squared approaches x squared, so we can say fxn, which is in such case xn squared, approaches f of x, which is x squared. Hence, fx is equal to x squared is continuous. Let's consider the continuity, or checking the continuity for a function f of x is equal to 1 divided by x minus 1. At first, the denominator cannot be 0, which means that x should always be different than 1. Let's consider x is equal to a being a value different than 1, because for a equal 1, the denominator becomes 0 and the function blows up to infinity. Let's start with proving the continuity for any a different than 1 using sequences. So as xn approaches a, f of x should approach f of xn, which is f of a. Now, f of xn is equal to 1 over xn minus 1. With xn approaching a, so the limit of f of xn as xn approaches a is equal to limit 1 over xn minus 1, xn approaching a, equal 1 over a minus 1. A minus 1 different than 0, since a is different than 1. Hence, the limit exists, and f of xn is continuous also. Therefore, f of x would be continuous for every a value different than 1. When x approaches 1, we want to use either of two values, meaning that either x is approaching 1 from the left, so it is a value a little bit less than 1, or x approaching 1 to the right, so it is a little bit greater than 1. Let's use the two sequences. So for x approaching 1 from the left, the sequence would be xn is equal to 1 minus 1 over n as n approaches infinity, meaning that it is a value so close to 1 but a little bit less than 1. So limit fxn, at first fxn is equal to choosing the pen, okay, fxn equal to 1 divided by xn minus 1 equal 1 divided by xn is 1 minus 1 over n minus 1, which is 1 minus 1 is 0. We are left with minus n. So limit fxn as n approaches infinity is equal to limit of minus n approaching infinity equal minus infinity. So it blows up to minus infinity. Again, this is the case where you have xn approaching 1 from the left. So it is a little bit less than 1. As for when we are approaching 1 to the right, so we have a value a little bit greater than 1. xn is equal to 1 plus 1 over n. So fxn in such case is equal to 1 divided by 1 plus 1 over n minus 1. These cancel out and you are left with n. Limit fxn as n approaches infinity is equal to plus infinity. So it blows up to the right. Hence, the continuity of the function or the definition domain is given by x is within the scope of minus infinity, 1 excluded, union 1 also excluded, plus infinity. Okay, let me actually rewrite it. So x is, or the function f is defined for x is between minus infinity included to 1, minus infinity excluded to 1 excluded, union plus 1 to plus infinity. So it is continuous in this scope and this scope, but there's a discontinuity at x equal 1. This, by the way, can be rewritten as it is continuous for x is within R minus the singleton 1, the single element 1. Shows that Q, the quotient, is dense in R. A set A is dense in R if every open interval contains an element of A. Take any interval AB where A is less than B. By the Archimedean property, there exists n within the natural numbers, such that 1 over n is less than b minus a. Let's choose m within the scope such that a is less than m over n, less than b, so m over n is between a and b. Okay? M over n is a quotient, so it belongs to Q, hence it is scoped within R, so it is dense in R. It is part of real numbers. Let's try to rephrase it and attempt to make it a little bit simpler to understand. Let's say you have an open set A, B, which belongs to the R scope among the real numbers, such that A is less than B. Now you have a value between A and B such that that value is very small, okay? It is equal to 1 over n. So 1 over n is greater than A and less than B, correct? Now, this value 1 over n would depend, of course, on the value of n. So as n increases, this value depletes and goes all the way to 0. But we are supposing that 1 over n is between a and b. So a is a very small lower bound and b is a very high upper bound within R. As you multiply by m, this 1 over n, okay? As you multiply by m, 1 over n, so m times 1 over n. And m being a value that is in z, okay? Hence, m over n would stay between a and b. So m over n would always be greater than a, which is the lower bound, and always less than b. Doesn't matter what the value is, okay? Because even when you divide by a very small value, that would remain a value close to b, but not actually b. It won't blow up completely. Hence, m over n, which is a quotient, so m over n is within Q, the rational numbers. This would be included also among the real numbers, hence Q is dense in R. Connectedness problem show that the interval 0, 1 is connected. First, by just looking at 0, 1, you notice that 0 and 1 are respectively the lower and upper bounds. More than that, so it is bounded, plus it is a closed set given that 0 and 1 are part of the set itself. So 0 is the minimum and 1 is the maximum. And again, 0 is the infima, which means the lower bound, 1 is the suprema, the upper bound. And there are no gaps. So there are no splits. All the elements exist within the set. There is no gap between, like you don't have multiple sets connected together, hence it should be connected. Assume 0, 1 is disconnected. Then there exists non-empty disjoint open sets U, V, such that 0, 1 is included within U union V. 0 belongs to U. Define X within 0, 1, 0x within U. Let C be the supremum of A, which is the upper bound, using completeness of R. One derives a contradiction by analyzing whether C belongs to U, okay, or C is within V. Thus, such a separation cannot exist, okay? You cannot separate between these two. Hence, 0, 1 is connected. In other words, U and V are the same set. There is no split between them. Continuous image of compact sets shows that the continuous image of a compact set is compact. First, let F having X approaching Y be continuous, and let K being a part of X. It is like a subset included in X. Let it be also compact. Take any open cover of F of K. Say F of K is included also within the set U alpha. Now, since F is continuous, F minus 1 U alpha, which is the reciprocal function, the inverse function of f. Okay, let's take that. Since it is open in X and K belongs to the subset of the inverse function f minus 1 u alpha. Okay, now compactness of K gives a finite subcover. K is included in f minus 1 u alpha union f minus 1 u alpha n. So applying f yields fk is included in u alpha 1, u alpha n, etc. Now, the reciprocal function, by the way, means that x becomes f and fx. So we are reversing the image, and like the reflection becomes the image itself and the image the reflection. So in other words, in terms of a function f of x, let's say it's equal to x plus 1. Okay, x becomes y, so to speak. So the image, okay, so y is equal to x plus 1. Hence, x is equal to y minus 1. And x becomes f minus 1 of y. Okay, so it's inverted. Hence, fk would be included in the different images. Therefore, continuous images of compact sets are compact. Show that the continuous image of a connected set is connected. Let f of x lead to an image y. Be continuous, and let C be included in X, in the scope of X. Let it also be connected. Assume f of C is disconnected. So in such case, f of C would be included within two subsets that are disjoint, that are disconnected. So f of C is equal to U union V, with U and V are two disjointed subsets, where U and V are non-empty, disjoint open sets. Now, since f is continuous, f minus 1 of U, which is the inverse function at U, and f minus 1 of V are open in C. They are non-empty, disjoint, and cover C. But they cannot cover C. Why? Because this would contradict the connectedness of C itself. Because C is not disconnected. C is connected. Therefore, f of C cannot be disjointed at U and V, at two disjointed subsets. Therefore, continuous images of connected sets are definitely connected. Closure of a set problem. Find the closure of 0, 1, which is an open set, in R among the real numbers. And as a note here, 0 and 1 are respectively lower and upper bounds, infima and suprema. However, 0 and 1 do not belong to the set itself. So they are not minimum and maximum. The closure of a set consists of all points of the set and all the limit points. The interval 0, 1, which is an open interval, has limit points that are 0 and 1. Thus, 0, 1 bar is equal to 0, 1 within square brackets, with 0 and 1 included in the set. Finally, metric spaces and topology have covered the following topics: metrics and open bows, open and closed sets, convergent and Cauchy sequences, compactness and completeness, connectedness, dense sets, continuity in abstract spaces, topological properties preserved under continuous mappings. Metric spaces and topology provide the abstract framework underlying modern analysis, geometry, differential equations, and functional analysis. 9. Functional analysis. Here we're going to cover normed vector spaces, orthogonality, Banach spaces, Fourier coefficients, HAHN-BANACH theorem concepts, completeness, inner product spaces, Hilbert spaces, linear operators, boundedness and continuity, and operator norms. Verifying a norm. Show that absolute value, double absolute value, which is a norm, equal to absolute value of x, which is a distance metric, defines a norm on R. To verify that this is a norm, we check the norm axioms. First, positivity, which means for all x in real value scope, or for any real value x, absolute value of x should be greater than or equal to 0. And if absolute value of x is equal to 0, hence x is equal to 0. Second, homogeneity. So for alpha being a real number, alpha x in norms is equal to alpha x absolute value equal to absolute value of alpha times absolute value of x equal alpha and absolute value times norm of x. Third, triangle inequality, which means that norm of x plus y is equal to absolute value of x plus y is less than or equal to absolute value of x plus absolute value of y. Why? Because any or either of x or y can be negative, correct? Equal to norm of x plus norm of y. Hence, all norm axioms hold. Therefore, x, norm of x is equal to absolute value of x is a norm in R. So as a wrap up, first, positivity, which means that absolute value of x should always be greater than or equal to 0, or if absolute value is equal to 0, hence x is equal to 0. Second, homogeneity, which means that alpha x in norms is equal to alpha x in absolute value, or alpha times x norm, correct? And equal to alpha in absolute value times x in absolute value. Finally, triangle inequality. So norm of x plus y is equal to x plus y in absolute value, which is the distance between y and x, less than or equal to x in absolute value plus y in absolute value, and equal to norm of x plus norm of y. Hence, it is a norm in R. Compute the Euclidean norm of x equals 3, 4 in R square. The Euclidean norm is like measuring the distance of a vector. So it is given by norm of x is equal to square root of x1 squared plus x2 squared. x1 being 3, x2 is equal to 4. So norm of 3, 4 is equal to square root of 3 squared plus 4 squared, or square root of 9 plus 16, which is square root of 25, equal plus 5. Hence, it is the distance from 3 to 4 equal to 5. Inner product verification show that xy as a vector is equal to x1 y1 plus x2 y2 defines an inner product on R2. To verify the inner product axioms, you need to prove symmetry, linearity, and definiteness. Starting with symmetry. So xy is equal x1 y1 plus x2 y2, which can be rewritten as equal y1 times x1 plus y2 times x2 equal yx. So it is reflective. It is symmetric. Second, linearity for scalars a, b. So ax plus by z is equal to a times xz plus b times yz, which follows from distributivity. Let's clarify linearity because we kind of scraped over it a little bit swiftly. Ax plus by z can be rewritten as axz plus by z, just like you multiplied x times y in the original set. So axz can be broken down into a times xz plus b times yz. So the linearity and the distributivity holds. 3, positive definiteness. So let's say y equal to x, then instead of xy equal to x1 y1 plus x2 y2, since y equal to x, you get xx equal x1 times x1 or x1 square plus x2 times x2, which is x2 square greater than or equal to 0. And xx equals 0 gives us x equal 0, 0. Thus, all inner product axioms hold. Hence, xy is equal to x1 y1 plus x2 y2 is an inner product. Orthogonality. Determine whether the vectors u equal 1, 2 and v equal 2 minus 1 are orthogonal. Two vectors are orthogonal if uv is equal to 0, if the scalar product between u and v gives us 0. Now, uv is equal to xu times xv plus y of u times y of v, which is practically here 1 times 2 x of u times x of v plus 2 times minus 1 y of u times y of v. So equal 2 minus 2, which is 0. Hence, u and v are orthogonal. Cauchy-Schwarz inequality. Verify the Cauchy-Schwarz for u equal 1, 2, v equal 3, 4. Cauchy-Schwarz inequality states that the absolute value of the scalar product between u and v is less than or equal to norm of u multiplied by norm of v. Let's compute the scalar product between u and v. This is given by xu times xv plus yu multiplied by yv, which is 1 times 3 plus 2 times 4 equal 3 plus 8 equal 11. The absolute value gives us also 11. Now compute the norms. Norm of u is equal to the square root of x of u square plus yu square, which is equal to the square root of x of u is 1. 1 square plus y of u is 2 square, which is square root of 5. Norm of v is equal to square root of xv square plus yv square, or 3 square plus 4 square. 9 plus 16 equal square root of 25, which is plus 5. Hence, norm of u times norm of v is equal to 5 square root of 5. Since 11, which is the absolute value of the scalar product between u and v, is less than or equal to 5 square root of 5, hence uv in absolute value is less than or equal to norm of u times norm of v, which actually verifies or confirms Cauchy-Schwarz inequality. Triangle inequality in normed spaces. Verify the triangle inequality for u equal 1, 1 and v equal 2, 3 using the Euclidean norm. What is the triangle inequality? It means that norm of u plus v should be less than or equal to norm of u plus norm of v. Let's at first compute u plus v. So u plus v is simply equal to the vector of xu plus xv and yu plus yv, which is 1 plus 2 and 1 plus 3, 3, 4. The norm for that vector, or norm u plus v, is equal to 5, which is square root of 3 square plus 4 square equals square root of 9 plus 16, or square root of 25. That's why it is 5. Let's compute individual norms. Norm of u is equal to the square root of xu square plus yu square, which is square root of 1 square plus 1 square, or 1 plus 1 equal square root of 2. Norm of v is square root of xv square plus yv square equals square root of 2 square plus 3 square, 4 plus 9, or square root of 13. So norm of u plus norm of v is equal to square root of 2 plus square root of 13. Numerically, 5 is less than or equal to square root of 2 plus square root of 13. Therefore, the triangle inequality holds. Linear operators shows that for the transform r squared to r squared defined by txy equal to x plus y, x minus y is linear. To prove linearity, t of u plus v should be equal tu plus tv. Second criteria is that t alpha u should be equal to alpha tu. Alpha is a multiplier, a constant. Let's take two vectors u and v with u equal x1, y1 and v equal x2, y2. Tu plus v is equal t x1 plus x2, y1 plus y2. Because remember, t was xy, correct? So instead of x, you place x of u plus x of v, and to the right, yu plus yv, which is x1 plus x2, y1 plus y2. Now remember, just like x is equal to x plus y in the original vector, x1 is equal to x1 plus y1, x2 is equal to x2 plus y2. The same thing for y1, okay? So y1 is equal to x1 minus y1, and y2 is equal to x2 minus y2. So it is 2 times x1 plus x2, correct? We add x1 and x2 together. It is 2x1 plus y1 plus 2x2 plus y2. So 2x1 plus x2 as a factor plus y1 plus y2. And to the second side, it is x1 plus x2 minus y1 minus y2, correct? So it is x1 plus x2 minus y1 plus y2 in two parentheses. Then we simplify. So 2x1 plus y1 and x1 minus y1, which is for the first vector, and 2x2 plus y2, just like here, the first element of the second vector, first coordinate, and x2 minus y2, okay? So x2 minus y2, the element of the second vector, which is equal to tu plus tv. Second step, we should prove that t alpha u is equal to alpha tu. Let's consider, instead of u being x1 and y1, let's say that u is equal to xy, simply, which is the original content of the vector here. Okay, what is t alpha u? What does it mean? T alpha u is equal to t of alpha times 2x plus y and alpha times x minus y. So it is equal to alpha times 2x plus y, alpha times x minus y, but alpha is a common multiplier. It can be removed to the outside. So it is equal to alpha times 2x plus y, x minus y, which is simply tu. It is equal to alpha times t xy, or tu. So hence, it has been proven as a linear. So t is a linear operator. Find the operator norm of tx equal to x on R. The operator norm is given by norm of t equal sup tx. So it is the superior boundary of tx with the norm of x equal to 1. For x being a real number with absolute value of x equal to 1, we have tx in absolute value is equal to x. Absolute value equal to, because x is equal to 1, the metric distance of x. Thus, the norm of t equal to shows that every bounded linear operator is continuous. Suppose Tx has an image y is bounded. Then there exists m greater than 0 such that Tx in norm of Tx is less than or equal to mx. Let xn approach x, so xn minus x will approach 0. Using boundedness, Txn minus Tx is equal to the norm of Txn minus x, less than or equal to m of the norm xn minus x, with the norm xn minus x approaching 0. We obtain Txn minus Tx also approaching 0. Thus, Txn will approach Tx. Hence, T is continuous. Therefore, every bounded linear operator is continuous. Completedness of Banach spaces. Define a Banach space. A Banach space is a normed vector space that is complete, and completeness means that every Cauchy sequence converges to an element of the space that is within the space itself, that belongs to the space. So, if xn is Cauchy in X, then there exists X within capital X such that xn approaches X. Hence, a Banach space is a complete normed vector space. Hilbert spaces explain why R to the nth dimension with the Euclidean inner product is a Hilbert space. A Hilbert space is an inner product space that is complete with respect to the norm induced by the inner product. The Euclidean inner product is given by xy is equal to sigma I equal 1 to n xy times yi for all the different elements. The induced norm is given by norm of x is equal to square root of x, okay, in the space Rn. So, the space Rn is complete under this norm, therefore Rn is a Hilbert space. Orthogonal projection. Find the orthogonal projection of V equals 3, 4 onto the vector u equal 1, 0. First, what is the formula of the orthogonal projection? This is orthogonal projection of V over u, which is Vu in scalar product divided by scalar product of u times u. Vu is equal to 3 times 1 plus 4 times 0 equal 3. U scalar u is simply 1, 0, scalar 1, 0 or dot 1, 0, which is equal to 1. So the projection of V over u is 3 over 1 times u vector, which is 3 times 1, 0 equal 3, 0. This is the projection of V over u. Fourier coefficients. Find the first Fourier coefficient of f of x equal x on minus pi plus pi corresponding to cosine x. Now the formula of a Fourier term is the following. An is equal to 1 over L integral from minus L to plus L f times cosine npx over L dx. Now, first of all, n is equal to 1, hence n is irrelevant. L is pi, so you end up with cosine x, and here you have plus pi and minus pi, the two bounds of the integral. And at the beginning you have 1 over pi, so a1 is equal to 1 over pi, integral from minus pi to plus pi, x cosine x dx, because it is the first term. Now x is an odd function, which means f minus x is equal minus f of x. So which is equal to minus x. As for cosine x is an even function, which means f minus x is equal to f plus x. Why? Because cosine alpha is equal to cosine minus alpha. In this case, it would be equal to cosine x. Thus, x cosine x itself is odd. Since it is odd and the integral is between minus pi to plus pi, therefore the integral would be 0. Why? Because one side is positive, the other side is negative, and both of them are symmetric in respect of the origin of the axis. Hence, a1 is equal to 0. Orthogonality of functions shows that sine x and cosine x are orthogonal between minus pi and plus pi. With respect to the inner product, fg equal integral from minus pi to plus pi fx gx dx, which should give us 0. Let's compute sin x cosine x. So this is equal to integral between minus pi to plus pi sin x cosine x dx. Now, based on the trig formulas, sin a plus b is equal to sin a cosine b plus cosine a sin b. Sin a minus b gives us sin a cosine b minus cosine a sin b. So we simply add these two equations together. You end up with 2 sin a cosine b, and these cancel out, equal sin a plus b plus sin a minus b. Now a and b are the same. A equal b equal x in this case. So 2 sin x cosine x is equal to sin 2x plus sin 0, which is 0. Hence, sin 2x is equal to 2 sin x cosine x, and sin x cosine x equal to 1/2 sin 2x. We place it back in the integral, so we obtain 1/2 integral minus pi to plus pi, because this is a constant, you can remove it to the outside, sin 2x dx. Since sin 2x is odd, the integral is 0, hence sin x and cosine x are orthogonal. In other words, what you have here is that sin x is symmetric in respect of the origin, so the integral is 0, definitely. Hence, sin x and cosine x are orthogonal. Parseval type computation. Compute norm f square for f of x is equal to x in L square between -1 and +1. The L square norm satisfies norm of f square is equal to integral from -1 to +1 absolute value of f of x square dx. Thus, norm f square is equal to integral between -1 and +1 of x square dx. Since x square is even, so you get, we can recalculate it as 2 integral between 0 and 1 x square dx. Okay, so we split the interval between 0 and 1 and we multiply it by 2. Why? Because given the fact that f of x is equal to f of minus x equal x squared, so x squared is symmetric in respect of the y-axis. So the area to the right is equal to the area to the left. Hence, you split the interval and you compute the integral from 0 to 1. You multiply it by 2, so you get the total area, since the area is the same to the right and to the left. So this gives us 2 times integral of x2 is x3 divided by 3 between 1 and 0, which is 2 over 3. Finally, this chapter, which is functional analysis, covered norms and inner products, boundedness and continuity, operator norms, orthogonality, Hilbert and Banach spaces, orthogonal projections, Fourier analysis concepts, and linear operators. Functional analysis provides the mathematical framework for quantum mechanics, partial differential equations, harmonic analysis, optimization theory, and infinite dimensional geometry. Chapter 10, Measure Theory. In measure theory, we're going to cover sigma-algebras, null sets, measures, almost everywhere convergence, LP spaces, Lebesgue measure, measurable functions, simple functions, Lebesgue integration, convergence, theorems. Show that the following function f is a sigma algebra on R. A sigma algebra must satisfy the following. R should exist in F, it should be closed under complements, and closed under countable unions. At first, clearly R exists within F, because F contains the entire space of R. Second, complements. The complement of empty space is R. So is the complement of R is empty space. Both belong to F. Third, countable unions. Any countable union of elements of F is either empty space or R. Both exist in F. Hence, F is a sigma algebra. Properties of measures. Let mu be a measure. Show that mu empty is equal to 0. Mu of empty space. Since phi union phi gives us phi, which is empty space, and the union is disjoint, countable additivity gives us mu phi is equal to mu phi plus mu phi. You subtract mu phi from one side, so you move it to the left, for example. Hence, you end up with 0 is equal to mu phi. Find the Lebesgue measure of 2, 5. Lebesgue measure is simply the length between 2 and 5, which is absolute value of 2 minus 5 equal 3. So m to 5 equal 5 minus 2 equal 3. Show that a singleton set A has Lebesgue measure 0. For any value epsilon greater than 0 strictly, the singleton A is contained in the following interval. A minus epsilon over 2 and A plus epsilon over 2. Because epsilon is a very tiny, small value, but strictly greater than 0. Whose length is epsilon. Since epsilon can be arbitrarily be small, so m of A is equal to A minus epsilon over 2 minus A plus epsilon over 2, which is equal to A minus A 0 and minus epsilon over 2 plus epsilon over 2 equals 0. Hence, m of A would be equal to 0. As a clearer representation, so let's say this is A. A would be moving, it would have a degree of freedom between A minus epsilon over 2, which is a little bit to the left, quantity so close to A, but a little bit to the left of A, and A plus epsilon divided by 2, which would be the value right after A, to the right. So A would be contained again between A minus epsilon over 2 and A plus epsilon over 2. M of A, the singleton A, the measurement, is equal to A minus epsilon over 2 minus A plus epsilon over 2, which gives us 0. Show that f of x equal x squared is measurable on R. If function f is measurable if for every A within R, A being a real number, the set x, f of x greater than A is measurable. Now, x here is has the image x squared within the function. That should be greater than A, and this depends on the value of A. If A is less than 0, we know that f of x is equal to x squared would always be greater than or equal to 0. In such case, f of x always greater than A. Hence, the set would be equals to R. If A is greater than or equal to 0, and we want that f of x would be greater than A, hence the set would be anything before, you see, because in such case x square is greater than A, so x would be greater than plus minus square root of A. So it would be the set from minus infinity to minus square root of A, and minus square root of A should not be included because x should be strictly greater than that, union plus square root of A also excluded, it is an open set, all the way to plus infinity, and again, of course, plus infinity is excluded also. So it is all the real numbers between minus infinity to minus square root of A without minus square root of A, and after plus square root of A, so a value strictly greater than plus square root of A, all the way to infinity with infinity excluded. Hence, f of x is equal to x squared is measurable. Simple functions shows that phi of x equal 1 for x greater than or equal to 0 all the way to 1 excluded, and 2 for x greater than or equal to 1 all the way up to 2 excluded is a simple function. First, the definition of a simple function, it has only a finite number of values. If we want to draw it, so for x strictly greater than or equal to 0 all the way to 1, it will have a value of 1. Then from 1 for x greater than or equal to 1 all the way up to 2, the value is 2. Basically, this is the plot of the function. Given the fact that phi takes the values of only 1 and 2, 1 from 0 to 1, 1 excluded, and 2 from 1 all the way up to 2. So it can be written as phi is equal to 1 for x0 between 0 and 1, 1 excluded, plus 2 for x between 1 and 2, 1 included and 2 excluded. Thus, phi is a simple measurable function. Integral of a simple function. Compute integral of phi dm, where phi of x is equal to 1 for x between 0 and 1, and 2 for x between 1 and 3. So this is simply the area for the first interval, between the first interval and the function, which is from 0 to 1, the distance is 1. This is the measurement of the distance between 0 and 1 excluded, multiplied by the height of the function, which is 1, plus the distance or measurement of distance between 1 and 3, so it is 1, 2, 3, that should be equal to, multiplied by the height of the function, which is 2. So it should be equal to 4. Approximately 4 plus 1. That would give us 5. Let's check it out. So integral phi dm is equal to sigma ai times the measurement of the distance for which you have the height of the function equal to ai. Thus, this is equal to 1, which is the height, multiplied by the measurement from 0 to 1, plus 2, multiplied by the measurement from 1 to 3. M01 is the distance between 0 and 1, which is 1. M1 to 3 is the distance between, measurement of the distance between 1 and 3, which is 3 minus 1 equal 2. Therefore, it is equal to the height between 0 and 1 is 1. 1 times the measurement, which is 1, measurement of the horizontal distance, plus 2, which is the height for the second interval between 1 and 3, multiplied by the distance of the interval, which is 3 minus 1 equal 2. So 1 plus 4 equal 5. Lebesgue integral. Lebesgue integral is simply the classical integral. So evaluate integral from 0 to 1, x dx. First, x is continuous between 0 and 1, and 0 and 1 is a compact interval, which means it is closed and bounded. The Lebesgue and Riemann integrals coincide, thus integral from 0 to 1 of x dx is equal to x squared over 2 between 1 and 0, which is 1 over 2. Almost everywhere convergence. Consider f and x is equal to x to the power of n on the closed and bounded interval 0, 1. Determine the pointwise limit. First, consider x between 0 and 1. 0, 1, this time the interval is open from one side, which is to the right side. X is greater than or equal to 0, less than 1, strictly. So between 0 and 1, with 1 excluded. We have x of n approaches 0 at x equal 1, 1 to the power of n is equal to 1. So fn of x approaches 0 for x between 0 and 1. As for x equal to 1, it is equal to 1. Since 1 as a singleton has measure 0, the convergence is to 0. And this is almost everywhere. Hence, fnx approaches 0 for the interval 0, 1. To lay it out in some simpler terms, you see x, whenever it is between 0 and 1, with 1 being excluded at first for the first demonstration. So whatever x would be, let's say 0 or 0.001 or 0.005, whatever x would be in such case, x to the power of n would decay because n is a natural number. So let's say 0.5 to the power of 3, you would see that it would decay quickly and approach 0. Only 1, okay, as a value for x would remain 1. So every other value would decay to 0, hence it is convergent everywhere on 0 and 1. Because in the first case, if it's 1, then it always stays 1, so it always converges. Dominated convergence theorem, evaluate limit as n approaches infinity of integral from 0 to 1 xn dx. We already know that xn approaches 0 almost everywhere on the interval 0, 1. Also, x to the power of n in absolute value is always less than or equal to 1, because its maximum would be 1. And 1 is integrable on 0, 1. Thus, the dominated convergence theorem applies. Therefore, limit as n approaches infinity of integral between 0 and 1 xn dx is equal to integral from 0 to 1 limit n approaching infinity of x to the power of n dx. That would be the integral of 0 equal 0. Thus, limit as n approaches infinity of this integral is equal to 0. And again, as a side note, so the dominated convergence theorem implies that the limit as n approaches infinity of the integral xn dx is equal to the integral of the limit as n approaches infinity of xn dx. Monotone convergence theorem. Let fnx equal to 1 minus 1 over n times x on 0, 1 closed interval. Show that integral fn approaches integral of f, where f of x equal x. Observe fnx over x pointwise. Each fn is measurable and non-negative. By the monotone convergence theorem, limit as n approaches infinity of integral 0 to 1 fnx dx should be equal to integral from 0 to 1 of limit n approaching infinity fnx dx, which is, since you have 1 minus 1 over n times x, as n approaches infinity, this becomes 0, so you end up with integral from 0 to 1 x dx. which is x squared over 2 between 1 and 0 equal to 1 Fatou's lemma. State Fatou's lemma theorem. Fatou's lemma states that if fn is greater than or equal to 0 are measurable functions because it is a sequence of functions, then integral of limit inf fn as n approaches infinity, which is the lower bound of fn, is less than or equal to limit of inf integral fn as n approaches infinity. Hence, integral of limit inf fn is equal or less than or equal to the limit of the inferior of integral fn. LP norms problem. Compute L square norm of f of x equal x on interval 0, 1. The norm is f2 equal integral from 0 to 1 fx in absolute value square dx to the power of 1 half. Why? Because it is L square that is equal to integral from 0 to 1 absolute value of f of x square dx. Hence, L is the square root of that value. So, integral from 0 to 1 of f of x square dx is equal to f of x, of course, is x square. You remove the absolute value dx, which gives us x3 over 3 between 1 and 0. You end up with 1/3. Now, L square is equal to 1/3. Hence, L is equal to the square root of 1/3 or 1 over square root of 3. Holder's inequality. Let's state it. According to Holder's inequality, let's say you have a number p between 1 and infinity. 1 is included, so p greater than or equal to 1, but less than infinity. And measurable functions f and g. We have integral of the absolute value of f plus g to the power of p on the outside to the power of 1 over p is less than or equal to integral f absolute to the power of p to the power of 1 over p on the outside plus integral g power of p to the power of 1 over p. So equivalently, the norm of f plus g on p is less than or equal to the norm of f plus norm of g. Finally, so what we've seen in measure theory, we've covered sigma algebras and measurable sets, almost everywhere convergence, dominated and monotone converges theorems, LP spaces, measurable and simple functions, Lebesgue measure, Lebesgue integration, and fundamental inequalities in analysis. Measure theory provides the rigorous foundation for modern probability theory, harmonic analysis, ergodic theory, stochastic processes, and advanced functional analysis. 11. Fourier analysis. Fourier analysis is going to cover Fourier series, orthogonality of trigonometric functions, Fourier coefficients, even odd functions, complex Fourier series, Parseval's identity, Fourier transforms, convolution, Dirichlet conditions, and applications for differential equations. 1. Orthogonality of sine functions. Show that integral from minus pi to plus pi of sin nx times sin mx dx is equal to 0 for n different than n. First, as a reminder, going back to the trig equations, cosine a plus b is equal to cosine a cosine b minus sine a sine b. You always flip the sense, okay? Now, cosine a minus b is equal to cosine a cosine b plus sine a sine b. So what characterizes the cosine is that you multiply it by itself and the sine by itself. As for the sine, you flip it. If it's positive on the inside, it becomes minus on the outside and vice versa. So to get sin A, sin B, you need to multiply above by minus, then add up both of the equations. So you end up with, When we multiply by minus, this becomes minus, this minus, and this plus. We add both equations, 1 and 2. This cancel out. You end up with 2 sin A sin B is equal to cosine A minus B minus cosine A plus B. In our case, A is nx, B is equal to mx. So, sin nx times sin mx is equal to cosine n minus m times x minus cosine n plus m times x divided by 2. Thus, sin nx sin mx becomes 1/2 multiplied by integral of this quantity, which is cosine n minus m x dx, minus 1/2 integral from minus pi to plus pi cosine n plus m x dx. Why? Because the integral of a sum is the sum of integrals. That's why you can break it down into two integrals. So for n different than m, both cosines would have a non-zero frequency. Hence, whatever k would be, the integral to the left would be equal to the integral to the right, and they cancel each other. Okay? So their sum becomes 0 because it is 1/2 of a value minus 1/2 of the same value with a different frequency. Hence, the integral is equal to 0. Orthogonality of cosine functions shows that integral from minus pi to plus pi cosine nx cosine mx dx is equal to 0 for n different than m. Again, we use the identity. As we know, cosine nx plus mx is equal to cosine nx times cosine mx minus sine nx sine mx. Cosine nx minus mx is equal to cosine nx cosine mx plus sine nx sine mx. We add these two equations together. This cancel out. So you end up with 1/2 cosine n minus m or nx minus mx or n minus m times x plus cosine nx plus mx, which is cosine n plus mx. You integrate the terms. Okay, so you end up with 1/2 integral, because 1/2 can be removed to the outside, integral from minus pi to plus pi cosine n minus m x dx plus 1/2 integral from minus pi to plus pi cosine n plus m x dx. Since n is different than m, these two terms vanish because you have a non-zero frequency. In other words, for each one, you would have 1/2 multiplied by cosine's integral becomes sine pi minus sine minus pi, which is, okay, so sine pi and sine pi doesn't matter. It's a zero angle. It gives you 0 on both sides. Fourier coefficient. Find the constant Fourier coefficient A0 for f of x is equal to x on interval minus pi plus pi. Now, as a reminder, this is the formula for a coefficient of Fourier. It is given by an is equal to 1 over L, which is the length, which is one strand between minus pi to plus pi. That would be 1 over pi, integral from minus L to plus L, L being pi, of course, of f multiplied by cosine, because we are searching it for cosine, okay, and also for sine, the same thing. Okay, so f times cosine n pi x over L plus integral, or plus within the integral, f sine n pi x over L. dx. Now, for the constant coefficient, where you would have neither of cosine or sine, a0 is equal to 1 over pi, integral from minus pi to plus pi, fx dx, which is equal 1 over pi, integral from minus pi to plus pi, x dx. Since x is odd, hence the integral is 0. Okay? Odd meaning f of minus x is equal to minus f of x. Because this is the equation of x, or the plot. X is y equal x is simply symmetric according to the origin of the axis. And even if you solve it, okay, you end up with x squared over 2 between pi and minus pi. So it is pi squared over 2 minus pi squared over 2, which is 0 anyways. So a0 is equal to 0. As for Fourier sine coefficient, find b1, which is the sine argument here, okay, for f of x is equal to x between minus pi and plus pi. So that would be b1, or let's say, okay, so bn, what would be the form of bn? It would be 1 over L, integral between minus L plus L, f times sine npx over L dx. In our case, that would be b0 is equal to 1 over pi, integral minus pi to plus pi, fx is x times sine npx over L, which is sine n equal to 1. Okay, so this is 1 times p over p, so it's sin x dx. So this is b1. Since x sine x is even, and we know it is even, okay, because f of x is equal to f minus x. Here is y, okay, so f of x is equal to x sine x, f of minus x sinus minus x would give you also x sine x. Hence, the integral would give us 2 over pi. Okay, so you split the integral, so you end up with 2 times 1 over pi, integral between 0 and pi, x sine x dx. So here we need to do an integration by parts. Let u be equal to x and dv be equal to sine x dx. du is equal to dx and v is equal to integral of dv, which is minus integral of sine x is minus cosine x dx. Now, integral of u dv, as a reminder, is equal to uv minus integral to v du. This is the formula. Thus, integral of x sine x dx is equal to minus x cosine x, which is uv, or x times minus cosine x, plus integral of v du. Okay, v du is minus cosine x times dx. Okay, so v is minus cosine x times dx, so hence you have minus x cosine x plus integral of cosine x dx. There might be an error here, I'm not sure, to be honest. Okay, because it is v du, it is integral of minus cosine x. So anyway, integral of cosine x gives you sine x, you have a minus, and you evaluate, okay, so that would become integral of 0 to pi x sine x dx is integral of these two. Thus, integral of x sine x dx is equal to uv, which is x times minus cosine x, or minus x cosine x, plus integral of v du, which is minus cosine x times dx. Here, I think there might be an error. So, this gives us minus x cosine x, integral of cosine x is sine x, and you have a minus on the outside, between pi and 0. So between pi and 0, okay, now sine x is 0 anyways, so you end up with minus x cosine x, which is minus pi cosine pi is negative, okay? So it is plus pi, and as for 0, everything cancel out, so it is equal to pi. Therefore, b1 is equal to 2 over pi, because you have a multiplier on the outside of the integral, which is 2 over pi, multiplied by pi, which is equal to, hence b1 is equal to Fourier series of an odd function. Explain why the Fourier series of an odd function contains only sine terms. If f is odd, then f of minus x would be equal to minus f of x. Now an is equal to 1 over pi, integral from minus pi to plus pi, fx cosine np or nx dx. Since cosine nx is even, the product fx cosine nx is odd. The integral of an odd function over minus pi to plus pi is always 0. Thus, an and a0 also would always be 0. That's why this term cancels out. So odd functions have Fourier series with only sine terms. Now let's explain why the Fourier series of an even function contains only cosine terms. If f is even, then f minus x would be equal to f plus x. Now, bn is equal to 1 over pi, integral from minus pi to plus pi, f of x sine nx dx. Since sine nx is odd, the product fx sine nx is odd. This means that fx sine nx is odd and is always 0. So bn is equal to 0, therefore only cosine terms remain. Hence, even functions have Fourier series with only cosine terms. Parseval's identity, let's state it. If f of x is approximately equal to a0 over 2 plus sigma n equal 1 to infinity an cosine nx plus bn sine nx, then the Parseval's identity states that 1 over pi integral from minus pi to plus pi of absolute value fx square dx is equal to a0 square over 2 plus sigma n equal 1 to infinity an square plus bn square. Hence, 1 over pi integral from minus pi to plus pi fx square dx is equal to a0 square over 2 plus sigma n equal 1 to infinity an square plus bn square for any value of n. Write the complex Fourier series form of a periodic function. F of x is approximately equal to sigma n equal minus infinity to plus infinity Cn EINX. This is the complex format, where Cn is equal to 1 over 2 pi integral from minus pi to plus pi f of x times exponential of minus INX dx. So f is approximately sigma n equal to minus infinity plus infinity Cn EINX. Now remember that E minus INX is simply cosine nx minus I sine nx. So this is where you get the cosine and sine terms from. State the Fourier transform of f of x equal e minus x square. One of the most important formulas in Fourier analysis is the transform f of e minus x square epsilon is equal to the square root of pi times e minus epsilon, or key square, divided by 4, depending on normalization conventions. Thus, fe minus x square key is equal to the square root of pi e minus key square divided by 4. Define the convolution of two functions f and g. The convolution is defined by f convoluted with g x is equal to integral from minus infinity to plus infinity fx minus t times gt dt. So it is a sum of product between f shifted with t Okay, so f starts shifting each time. F is shifting to the right, let's say, and it is multiplied with g. Then for each multiplication, for each shift, you add up the outcome. So to give you an example, let's say g is given by 0, 1, 0, and or let's say actually g is a sequence of bits, let's say, which is 0, 1, 1, and f is 0, 1, 0. So now at first, nothing changes, it's all 0, okay? But then, once you have this enter into, like, yeah, once this shift to the right, so you get actually 0, 1, 0. So you add them together, you multiply them together, and you end up with 0 times 0, 0, 1 times 0, 0, and 1 times 1 is equal to 1. Then it shifts another time, so 0, 1, 0 shifts again. So here you have 1 times 0, 0, 0 times 0, so 1 times 1, 1. You end up with 0, 0, 1. We add them all together, okay? So you end up with 0 plus 0 plus 0 is 0, 1 plus 1, 2, and 1 plus 1, 2, okay? This is just an example, an attempt to hopefully not complicated, but a little bit simplifying it, breaking it down, okay? Provided the integral exists, hence fg, f convoluted with gx is equal to integral from minus infinity to infinity fx minus t times gt dt. State the convolution theorem for Fourier transforms. So f of f times g is equal to f times f to g. That is, convolution in physical space corresponds to multiplication in frequency space. Hence, f of f times g is equal to f of f, okay, the frequency space of f, multiplied with a normal multiplication, no longer convoluted, with the frequency of g. Dirichlet conditions state Dirichlet's conditions for convergence of Fourier series. A periodic function f satisfies Dirichlet conditions if, first of all, f is piecewise continuous, then f has finitely many maxima and minima, not infinite number of maximums and minimums, and f has finitely many discontinuities. Under these conditions, the Fourier series converges to f of x plus, which is the point right after x, plus f x minus over 2 at every point. Hence, Dirichlet conditions guarantee Fourier series convergence. Solve ut is equal to uxx using separation of variables. Assume uxt is equal to x of x multiplied by t of t. So substitute into the PDE. Okay, xt prime is equal to x second t. Divide by xt. So you divide both by xt, you get t prime over t, because x is removable, is equal to x second over x equal minus lambda. Thus we obtain two ordinary differential equations, which is x second plus lambda x equals 0 and t prime plus lambda t equals 0. Solutions depend on boundary conditions. The separated solution takes the form uxt is equal to a cosine nx plus b sine nx times e to the power of minus n squared t. That is the solution for this ODE. Hence, uxt can be written as a cosine nx plus b sine nx times e to the power of minus square t. Fourier transform of a derivative. State the Fourier transform rule for derivatives. If f prime is integrable, then f of f prime key is equal to I key f of f key. F is the frequency domain again. More generally, f of n is equal to I key to the power of n f of f. Hence, f of f prime is equal to I key f of f. Parseval type computation. Compute 1 over pi integral from minus pi to plus pi sine square x dx. First, we know that cosine 2x is equal to, which is cosine x plus x, equal to cosine square x minus sine square x. Then cosine 0, which is cosine x minus x, it becomes 1, is equal to cosine square x plus sine square x. So you multiply by minus on the above, you get minus cosine 2x minus cosine square x plus sine square x. Hence, sine square x is equal to, you add them together, it's equal to 1 minus cosine 2x divided by 2. These two terms cancel out. So 1 minus cosine 2x divided by 2. You simply replace it in the equation. Now you have 1 over pi integral between minus pi to plus pi. So 1 over 2, you remove it to the outside. So you get integral of 1 minus cosine 2x dx between minus pi to plus pi multiplied by 1 over 2 pi. So it is integral of between minus pi to plus pi cosine 2x dx. Now this part is equal to 0, okay? Given that you have cosine pi minus cosine plus pi also. Why? Because cosine x is equal to cosine minus x. Okay? So it gives you cosine pi minus cosine minus pi, which is also cosine pi. So all of that becomes 0. You are left with 1 over 2 pi integral between pi and minus pi of 1 dx, which is x, of course. So 1 over 2 pi multiplied by pi minus minus pi, which is plus pi, which is 2 pi. So it is equal to 1 over 2 pi multiplied by 2 pi, which is 1. Hence, the integral is 1. Finally, Fourier analysis, which is chapter 11, covers orthogonality of trigonometric systems, complex Fourier expansions, Fourier transforms, Fourier coefficients and Fourier series, even and odd symmetry, convolution and frequency analysis, applications to differential equations, and Parseval's identity. Fourier analysis forms the mathematical foundation of signal processing, quantum mechanics, PDE theory, harmonic analysis, communications engineering, definitely, and modern mathematical physics. Chapter 12, complex analysis. In complex analysis, we're going to cover complex numbers, Cauchy's integral formula, Taylor and Lorentz series, polar form, complex differentiation, residue theory, conformal mappings, analytic functions, Cauchy-Riemann equations, complex integration, and Cauchy's theorem. Compute 2 plus 3i multiplied by 1 minus 4i. Of course, we need to split them into real and imaginary parts. Let's multiply them together. So 2 plus 3i multiplied by 1 minus 4i gives us 2 times 1 minus 4i times 2. So it is 2 minus 8i plus 3i minus 12i squared. Now I squared is equal to minus 1. So this becomes plus 12. So 2 minus 5i plus 12, or 14 minus 5i. This is the final answer, with real value being 14 and imaginary value being minus 5. Second, write z is equal to 1 plus I in polar form. Now, as a reminder, 1 plus I on the trigonometric circle would be represented as 1 on the x-axis and 1 on the imaginary axis, which is the y-axis. So this is I, and this is 1. Hence, it would be this arc, or this vector, so to speak, if we can call it a vector. So what would be the polar form? It would be the magnitude and the angle. As for the magnitude of this segment is simply, according to Pythagoras' theorem, square root of x square plus y square, with x square being, of course, x is the real part, and y being the imaginary part of the complex number. As for the angle, so this is the magnitude. For the angle, we know that tan alpha is equal to opposing segment divided by the adjacent segment, or 1 over 1. So the angle itself is arctangent of 1 over 1, which is, in such case, by the way, that would be square root of 2 over 2 divided by square root 2 over 2. So the angle is 45 degrees, or pi over 4. So the modulus of z is equal to square root of 1 square plus 1 square equals square root of 2. Now determine the argument. X equal 1, y equal 1. The point lies in the first quadrant. Thus, theta is equal to pi over 4. Therefore, z is equal to square root of 2 multiplied by cosine pi over 4 plus I sine pi over 4, which is the angle, by the way. So this is a value that can be replaced by exponential of I of pi over 4. So this is a different writing, which is Euler's formula, by the way. EI pi over 4 can be broken down into cosine pi over 4 plus I sine pi over 4. And square root 2 is the modulus. So z is equal to square root of 2 multiplied by EI pi over 4. This is the polar form. Compute 1 plus I to the power of 4 using polar form. This is the Moivre formula. Okay, so 1 plus I at first is represented like this. This is 1, the real part. This is I, the imaginary part. The modulus is square root of 1 square plus 1 square, because this is 1 times I, which is square root of 2. As for the angle is pi over 4. Okay? We've mentioned that before. We've explained it, actually. So z can be represented as square root of 2 times EI pi over 4. Now, we raise this z value to the power of 4. So it gives us square root of 2 times EI pi over 4 to the power of 4, which is square root to the power of 4 is 4 times EI to the power of 4. You simply multiply the exponent, so you end up with 4 times EI pi. Now, EI pi, I think it is minus 1. Okay, so cosine I pi minus sine I pi. Yeah, minus 1, and this is 4, so it should be minus 4. Let's check it out. So, square root of 2 to the power of 4, EI pi. Square root of 2 to the power of 4 is equal to 4. EI pi is equal to minus 1. Hence, this entire z to the power of 4 elevated to the power of 4 gives us minus 4. Determine whether f of z is equal to z square is analytic. First of all, remember that z is a complex number, so it can be written as x plus I y, with a real part x and imaginary part y. F of z is equal to z square, which is equal to x plus iy square, equal x square plus I square y square plus 2x y I. I square is equal minus 1, you know. Okay, I square equal minus 1. Hence, f of z is equal to x squared minus y squared plus 2xyi. Let us split this result into real part and imaginary part. The real part is uxy. It's given by everything that is in the equation that's not multiplied with I. So uxy is equal to x squared minus y squared. Vxy, it is the part that is imaginary, multiplying I. So Vxy is this part, 2xy. For f to be analytical, we should at first have partial derivatives of f in respect of x and y. Let's remember what was u and vxy. Okay, uxy equal to x squared minus y squared, vxy equal to xy. So ux, which is the partial derivative of u in respect of x, is equal 2x. uy is equal minus 2y. As for vx, partial derivative in respect of x of v is 2y because x becomes 1, and vy is equal to x. The Cauchy-Riemann equations require that ux should be equal to vy and vy should be equal to minus vx. Now, or uy should be equal to minus vx, which holds. It holds true. Both conditions hold, hence this partial derivative is analytic. So f of z is equal to z squared is analytic given that ux is equal to vy equal to x and uy is minus 2y, which is equal to minus vx. Complex differentiation. Find the derivative in respect of z to the power of 3. We simply use the standard power rule, which means that the derivative of z to the power of n is equal to n times z n minus 1. Hence, d over dz of z to the power of 3 is equal to 3z squared. Harmonic functions, uxy is equal to x squared minus y squared. Let's show that this function is harmonic. For this function to be harmonic, uxx plus uyy should be equal to 0. In other words, the second derivative of u in respect of x plus second derivative of u in respect of y should be equal to 0. Let's start with ux. Ux is equal to 2x. Uxx for the second time equal to uy equal minus 2y. Uyy second time is equal to minus 2. So uxx plus uyy is 2 minus 2, which is equal to 0. Hence, uxy equal x squared minus y squared is a harmonic function. Contour integration. Evaluate integral over a curve or a contour of z dz, where c is the line segment from point 0 to 1 plus I, which is this line from 0, this is 0, to 1 plus I, which is 1I. It is like the equation of y equal x. Let's parameterize the equation. At first, this is how you get the equation of a line. Z, which would be y, an xy reference, is equal to rise over run multiplied by t plus y-intercept. Y-intercept is at the point or like where does the line clip the z-axis in such case, okay, or z-intercept in such case. So in other words, to make it a little bit simpler, you have x and y, okay? So the equation of a line here, let's say it clips the y-axis at A, and the rise over run is for each one, it steps 2. So for each one step in altitude, it steps 2 horizontally. So the equation of the line in such case would be y equal rise over 1, which is 1 over 2 in such case, times x plus y-intercept, which is it's clipping the y-axis at y equal a. So 1/2 x plus a. So you can say, for example, a is equal to 1, so that would be y equal 1/2 x plus 1. Let's parameterize the line. Parameterization at first is given by z of t is equal to 1 minus t times z0, which is the first point, plus t times z1, or the second point. z0 equals 0, so the first part is annihilated. z1 is 1 plus I, hence z of t is equal t times 1 plus I, with t is between 0 and 1. Now dz is the derivative of z in respect of t, so it's equal to 1 plus I dt. Thus, integral z dz over the line, and as we've seen before, so it is between 0 to 1 plus I. So on the real axis, it's changing between 0 and 1. Hence, integral from 0 to 1 of z, which is t times 1 plus I, dz, or 1 plus I. Okay, so this is integral between 0 and 1, t times 1 plus I squared, which is equal to 1 plus 2I plus I squared, which is minus 1. They cancel out, and you are left with 2I on the outside of the integral from 0 to 1 t dt, which is t squared over 2 between 1 and 0 times 2I. Okay? So t squared over 2 between 1 and 0 multiplied by 2I, which is 1/2 times 2I equal I. State Cauchy's theorem. Okay, so if f is a function that is analytic on and inside a simple closed contour, like this one I'm drawing, it means that you are finishing where you started as you go about this curve. It's not only a curve, it is a closed loop. Hence, it makes sense that the integral of f of z dz around c should be equal to 0. Cauchy's integral formula: evaluate integral of 1 divided by z minus 1/2 dz for absolute value of z equal 1. The point z equal 1/2 lies inside the unit circle. Now, this means that this would be half the distance of the radius. By Cauchy's integral formula, so integral over the curve or the closed loop of f of z over z minus a dz is equal to pi I f of a. Here, f of z is equal to 1 and a equal to 1/2. So this entire quantity, which is integral z equal 1 of 1 over z minus 1/2 dz, which is the integral to be found, is equal to pi I f of a, which is 2 pi I. Hence, this integral is equal to pi I, according to Cauchy's integral formula. This is how we found it out. Taylor series. Find the Taylor series of Ez about z equal 0. As a reminder, what is Taylor series? Taylor series is the development of a function f x such as it is the sum of f0 of x times x to the power of 0 over 0 factorial plus f prime of x, which is the first order derivative of f, times x to the power of 1 divided by 1 factorial plus f second x times x squared divided by 2 factorial, etc. So the formula is f of x, or Taylor series of f of x. Let's say it is t, okay? Referring to Taylor, is equal to sigma I equals 0 all the way to n of f of I x times x to the power of I divided by I factorial. Now it changes a little bit when we talk about the complex space. So Ez is equal to sigma n equals 0 to infinity z to the power of n divided by n factorial, which is 1 plus z to the power of 1 over 1 factorial plus z squared over 2 factorial, etc. plus z3 over 3 factorial, which is this formula, sigma n equals 0 to infinity z to the power of n divided by n factorial. Find Lorentz series of 1 over z times z minus 1 about z equals 0 for z absolute value less than 1. Lorentz series is very close to Taylor series, actually. We need to use partial fractions. 1 over z times z minus 1 breaks down into minus 1 over z plus 1 over z minus 1. We're going to find out how we separated both terms. Now, 1 over z minus 1 can be actually rewritten as minus 1 over 1 minus z, which is a geometric series equivalent to sigma n equals 0 to infinity of z to the power of n. Now, let's go back on how we split this fraction into minus 1 over z plus 1 over z minus 1. Basically, 1 over z times z minus 1 equal to a, you place an arbitrary variable, a over z, plus b over z minus 1. Okay, so 1 over z times z minus 1 is equal to, you multiply here a by z minus 1, so az minus a, plus you multiply b by z, bz, over z times z minus 1 to have a common denominator. So this can factor out, okay, and we are left with minus a equal 1, and az plus bz, so we don't have any z to the left, hence a plus b times z is equal 0, because we don't have z to the left, okay? So a plus b is equal 0. You remove z. Hence, minus a equal 1 or a equal minus 1, and b is equal minus a, which is minus minus 1 plus 1. That's why we have here plus 1 over z minus 1, and to the left we have minus 1 over z. These are simply the values of a and b. Thus, 1 over z minus 1, which is minus, if you will, of 1 over 1 minus z, becomes equal to minus sigma n equals 0 to infinity of z to the power of n. Hence, this fraction is equal to minus 1 over z minus this series, which is sigma n equals 0 to infinity of z to the power of n. This is how we achieved it. Residues. Find the residue of f of z is equal to 1 divided by z times z minus 2. The residues are the values of z for which the denominator becomes 0. Residue of f at 0 is equal to the limit of z, f of z, as z approaches 0, which is limit of, if you multiply by z in the numerator, we end up with 1 over z minus 2 as z approaches 0. equal to minus 1/2. Hence, the residue is equal to minus 1/2. Okay, why? Because z is approaching 0, so it is removed. Evaluate integral for z equal to of 1 divided by z minus 1 dz. First, the function has a simple pole at z equal 1. Okay, why? Because for z equal 1, the denominator becomes 0 and the entire fraction blows up to infinity. Now, inside z equal 2, here, the residue at z equal 1 is 1. By the residue theorem, the integral of f of z over the curve C dz is equal to pi I multiplied by the sum of all residues of the function. Therefore, integral over z equal to of 1 over z minus 1 dz is equal to pi I times 1. We have only one residue. 1 plus 0 because no other residues. Actually, 1. Okay? Nothing else. Hence, this integral gives us 2 pi I. Conformal mapping. Show that f of z is equal to z squared is conformal at z different than 0. First, when is a function conformal? First criteria that should be met is that f should be analytic and its derivative should be non-zero. The derivative of f of z is equal to z, so different than 0 whenever z itself is different than 0. Since f is analytic everywhere the derivative exists, it is conformal at all values of z where z is different than 0. Therefore, f of z is equal to z squared is conformal for z different than 0, whenever z is different than 0. State the maximum modulus principle. Maximum modulus states that if f is non-constant and analytic on a domain D, then absolute value of f of z cannot attain a maximum value at an interior point of D. Hence, any maximum must occur on the boundary. Therefore, a non-constant analytic function cannot attain its maximum modulus inside its domain. Finally, we covered in this chapter of complex analysis the following terms or titles: complex arithmetic and geometry, analytic and harmonic functions, Cauchy-Riemann equations, complex integration, Cauchy's theorem and integral formula, Taylor and Laurent expansions, residue calculus, conformal mappings. Complex analysis forms one of the most elegant and powerful areas of mathematics, with applications in fluid dynamics, electromagnetism, quantum mechanics, number theory, engineering, and mathematical physics. Probability Theory, Chapter 13. Here we cover probability spaces, conditional probability, Bayes' theorem, random variables, probability distributions, expected value, variance, and standard deviation. Also, common discrete and continuous distributions, law of large numbers, central limit theorem, and moment generating functions. Probability axioms. A fair die is rolled once. Find the probability of obtaining an even number. First, what is the sample space? What are the different values possible? These different values range from 1 to 6, 1 or 2, or 3, or 4, or 5, or 6. The even outcomes are the following: 2, 4, or 6. Thus, the favorable outcomes are 3 possible outcomes that can actually hit the target, and the possible outcomes are S, an absolute value, which is 6 possible or potential outcomes. PE is equal to number of favorable outcomes divided by the number of possible outcomes, or all outcomes, which is the even outcomes divided by the entire sample space, which is 3 over 6, or 1/2, or 50%. A card is drawn from a standard deck. Given that the card is a face card, find the probability that it is a king. The first question is, how many faces are there within a card deck? Okay, you have four types, four geometric shapes like the hearts, the diamonds, the spades, and the other fours I don't remember. But for each one of them, you have the queen, the king, and the young man, I don't know, the prince, so to speak. Okay, so three faces per type, and having four types, so it makes them 12 faces. How many kings are there? Since you have four types, so you have four kings. Thus, the probability of retrieving four kings from all different faces, this is probability of king over all face cards, not the entire card, which is 4 over 12 or 1 over 3, around 33.33%. Bayes theorem. The Cliff Note version of Bayes theorem postulates the following, that probability of A given that B has already happened is equal to probability of B supposedly that A is true multiplied by probability of A divided by probability of B. So for this example, PAB is equal to PBA, which is 0.8 or 80% times PA, 0.4 divided by 0.5. Let's check it out. So PBA times PA over PB, correct, 0.8 times 0.4 over 0.5, 0.32 divided by 0.5, which is 0.64 or 64%. Let's try to simplify Bayes' theorem by referring to an example a little bit simpler, hopefully. So let's say a city has 1% of its population having a disease. At first, let's turn it into probabilistic lingo. So probability of having a disease, or PD, would be equal to 1% or 0.01. Then automatically, probability of not having a disease, or PN, would be 99% or 0.99. Now, the probability of people that have a disease to test positive is P plus, this is how you write it, so probability of having a positive test given that the subject has a disease is 99% according to the proposition, or 0.99, which means that probability of having a negative result given that the subject has a disease is 0.01. Automatically, that would be 1 minus P plus given that he has a disease. So 1 minus 0.99. The probability for a person to test positive given that he doesn't have a disease, which would be a false positive, so to speak, is 0.02. Hence, the probability for testing negative, given that he doesn't have a disease, would be 80% or 88%, 98%, okay, which is 0.98, or 1 minus 0.02. So what is the probability of someone to have a disease given that he tested positive? Now, here it is inverted. How do we get that? It is the probability for the positive result given that he has a disease times probability of having a disease in general divided probability of having a positive result. Now, the first two we already know, we already have, which is P plus D, P plus given D, probability of having a positive result given that a person has a disease, and probability of the disease, which is 0.01. How to get the probability of positive test. P plus is equal to probability of having a positive test given that someone has a disease times the probability of disease, which is 0.99 times 0.01, plus probability of testing positive while the person does not have a disease, or 0.02, multiplied by the probability of not having a disease, which is 0.99. The result is 0.0297, so you place it back in this equation, 0.297, and in the numerator it is 0.99 times probability of disease 0.01, and the final result is 0.333, which is 33%. Expected value of a discrete random variable. Let x be a random variable with px equal 1 equal 0.2, probability of x being 2, 0.5, px equals 3 equal 0.3. Find e of x. E of x is the expected value. The expected value is calculated by e of x equal x times probability of x. Okay, x equal 1, meaning that this would be 1. Okay, let's state it as x0 multiplied by p of x0 by its probability plus x1, which would be the second value, 2 in such case, times the probability for that second value plus x2 times p x2. So 1 times 0.2 plus 2 times 0.5 plus 3 times 0.3, which gives us 0.2 plus 1 plus 0.9, or 2.1. And this is the expected value. For the random variable in exercise 4, compute var of x. Variance of x, or variance of x, is equal to e x squared minus e of x squared. So what is e of x squared at first? Okay, e of x squared is equal to 1 squared times probability of 1, which is 0.2, plus 2 squared times probability of 2, plus 3 squared probability of 3, which is 0.2 plus 2 plus 2.7 equal 4.9. Okay, now e of x squared, which is the value of e of x raised to the power of 2. If you remember, it was 2.1 square equal 4.41. Thus, var of x is equal 4.9 minus 4.41 equals 0.49. This is the variance of x. Binomial distribution. A fair coin, fair by the way means that the probability for different values of the coin is the same, okay? So 50-50 for face or heads. So a fair coin is tossed 5 times. Find the probability of obtaining exactly 3 heads among the 5 times of throwing the coin. We use the binomial formula, which is p x equal k is equal to n k, p to the power of k times 1 minus p to the power of n minus k. Now, first of all, n is the number of trials, which is 5 times we are throwing the coin. K equals 3, which is the number of favorable outcomes, and p equal 1/2. P is the probability of each trial. So each time you throw the coin, you have 50% of getting heads or tails. So, or face or heads. Yeah, something like that, head or tail. So, px equals 3 is equal to 5 over 3, or 3, multiplied by p to the power of k, which is probability 50% to the power of 3, times 1/2, which is 1 minus p, also 50% for the tails, to the power of n minus k, n being 5 minus k minus 3, which is 2, equal 10 times 1/2 to the power of 5. So 1/2 to the power of 3 times 1/2 to the power of 2. You add the power together, and you end up with 10 times 1/2 to the power of 5, which is 10 over 32 or 5 over 16. As a side note concerning this quantity here, this is the combination CNK equal to n factorial, which is the number of all trials, divided by k factorial, the favorable outcomes, multiplied by n minus k factorial, equal to 5 factorial divided by 3 factorial times 5 minus 3 factorial, equal 5 factorial, which is 5 times 4 times 3 factorial, divided by 3 factorial times 2 factorial. 3 factorial can be factored out, so you end up with 20 divided by 2 factorial, which is 10. This is where this 10 came from. Poisson distribution. Suppose X has a Poisson distribution with parameter lambda equal 2. Find Px equal 3. This is also another formula. So Px equal k is equal to exponential of minus lambda times lambda to the power of k, k being 3 of course, divided by k factorial. So Poisson distribution for x equals 3 is equal to exponential of minus 2 minus lambda times 2 to the power of 3 divided by 3 factorial, which is the probability for 3. That's why equal 8 exponential minus 2 over 6, which is 4 over 3 e to the power of minus 2. So hence Px equals 3 equal 4/3 exponential minus 2. Uniform distribution. Let x be approximately equal to u01. Find probability of x less than 1 over 4. Now for a uniform distribution, p of x less than 1 over 4 divided actually on an interval between 0 and 1, that would be 4 chunks, okay? 0, 1/4, 2 over 4, which is 1/2, then 3 over 4, that's the third, and 4 over 4, which is 1. Hence, the probability would be equal 1 over 4, which is 25% chance. Normal distribution standardization. Okay, suppose x is within a set n between 10 and 4. Standardize x equal 12. Z is equal to x minus mu divided by sigma. This is the standard we're talking about, we're trying to find. Therefore, again, z equal x minus mu over sigma, mu equal 10, x equal 12, so z is equal to 12 minus 10 divided by 2, which is equal 1. Therefore, z equal 1. Moment generating function. Find the moment generating function of a Bernoulli random variable with parameter p. A Bernoulli variable satisfies the following: px equal 1 is equal to p, px of 0 or x equals 0 is equal to 1 minus p. The moment generating function is mx of t equal e of exponential tx, thus equal e to the power of t times p plus 1 times 1 minus p. Therefore, mxt is equal to 1 minus p plus pet. Independence. Suppose pa equals 0.4, pb equals 0.5, and pa enter b equals 0.2. Determine whether a and b are independent. Now, pa enter b is equal to PA, or should be equal to PA times PB, probability of B, for A and B to be independent. Now, PA times PB is equal to 0.4 times 0.5, which is 0.2. Indeed, it is independent. So when you compute PA times PB, it gives you 0.2, the same value as PA enter B. This is the condition that should hold for A and B to be independent. State the law of large numbers. The law of large numbers states the following. If x1, x2, x3, all the way to xn are independent identically distributed random variables with mean mu, then x1 plus x2 plus all the way to plus xn divided by n, the number of these random variables, would approach mu, which is the mean, okay, as n approaches infinity. Thus, simple averages converge to the expected value. So 1 over n sigma k equal 1 to n of xk approaches mu. Central limit theorem. Let x1, x2, xn all the way be independent, identically distributed random variables with mean mu and variance sigma squared. Then sigma k equal 1 to n of xk minus n mu divided by sigma square root of n. This would converge in distribution to the standard normalization or normal distribution, n0, 1. Hence, sigma k equal 1 to n, xk minus n mu divided by sigma square root of n approaches n0, 1. Covariance. Let y equal to x plus 1. Find covariance of x, y. The covariance satisfies cov x, ax plus b equal a var x. So what is A in such case? It is 2, the argument multiplying x, and variance x, okay, so it is 2 times variance x. So you get the variance of x, you multiply it by 2. Correlation coefficient. State the formula for the correlation coefficient. The correlation coefficient between x and y is given by rho xy is equal to the covariance of xy divided by sigma x, sigma y, where sigma x and y are the standard deviations of x and y respectively. Finally, in probability theory, we covered probability spaces and conditional probability, Bayes' theorem, random variables and expectation, variance and covariance, classical probability distributions, independence limit theorems, statistical foundations. Probability theory provides the mathematical foundation for statistics, machine learning, stochastic processes, financial mathematics, statistical physics, information theory, and modern data science. Chapter 14, Differential Equations. This chapter covers the following: first order differential equations, separable equations, linear differential equations, exact equations, second order DEs, homogeneous equations, non-homogeneous, Laplace transforms, systems of differential equations, partial differential equations, heat, wave, and Laplace equations. Separable differential equations. Solve dy over dx is equal to xy. So we go about it by separating the variables. Here is how. Okay, so dy over dx is equal to x times y. You multiply y here in the denominator and the x in the numerator. So the extremes, you flip them. You end up with dy over y is equal to x dx. Let's integrate both sides. So it is integral of 1 over y dy equal integral x dx, which is ln y equal x squared over 2 plus c. Now, y, okay, so how do we get rid of the logarithm? You raise everything to the exponential. So e ln y is equal to e x squared over 2 plus c. Hence, y in absolute value is equal to exponential of x squared over 2 plus c. Let a equal exponential of c. Okay, so this argument here. Hence, y equal a ex2 over 2. Okay, because when you add something in the exponential, for example, ex2 over 2 plus c is equivalent to ex2 over 2 times exponential of c. So this is a, because it's a constant, hence you multiply it to the outside, so y is equal to a exponential x2 over 2. Okay, so this is a constant basically. This is what he's trying to say. Initial value problem. Solve dy over dx equal to x, and for y, which is the initial value, y of 0 equal 3. First, we separate the variables, so dy is equal to x dx. We simply multiply the x in here. Now we integrate both sides, so integral dy is equal to integral to x dx. This gives us y equal integral to x dx, which is equal to x squared over 2 plus c, or x squared plus c. Then we apply the initial condition, which is y0 equals 3. In other words, for x equals 0, y is equal to 3 in the equation. So you replace x by 0 and y by 3, and we get the value of c, which is 3. Hence, y is equal to x squared plus 3 is the solution for the differential equation. Linear first order differential equation. Solve dy over dx plus y equal ex. The form of the linear equation is y prime, which is the first derivative of y, okay, plus p of x, y equal qx. Now, p of x is equal to 1. That's the one multiplying y to the left, equal q of x, which is ex. Let's get the integrating factor. Mu of x is equal to exponential of the integral of p of x dx, equal exponential of integral p of x is 1 dx, which is x, okay? We end up with ex. Let's multiply, after that, the entire equation with ex. So you end up with ex y prime plus ex y equal, you have to the right ex, you multiply it by another ex, so you end up with e2x. Notice something, that exy prime plus exy is simply the derivative of exy in respect of x. Why? Because the derivative of exy is derivative of the first, this is a product, times the second, plus the first times the derivative of the second, which is y prime. So exy prime plus exy is simply derivative of exy in respect of dx. So dexy over dx is equal to x. Okay, we replaced the entire left side with this derivative, and we placed it equal to the right side, which is e to x. Now you integrate, so the integral gets rid of the derivative to the left, and integral of e to x to the right, dx is equal to 1/2 e to x plus c. Therefore, y equal 1/2 ex plus c e minus x. Okay, plus c e minus x. That would be the solution. Exact differential equation. Determine whether 2xy plus y squared dx plus x squared plus 2xy dx is equal to 0 is exact. So what is the criteria for it to be exact anyway? Here we have two components, the one multiplying dx, which is mxy, and the one multiplying dy, or nxy. mxy equal to xy plus y squared, and xy equal x squared plus 2xy. For the equation to be exact, the derivative of m in respect of y should be equal to that of n in respect of x. Okay. Partial derivative of m in respect of y is equal to 2x plus 2y. Partial derivative of n in respect of x is 2x plus 2y. 2x plus 2y. Hence, since partial of m in respect of y is equal to partial derivative of n in respect of x, the equation is exact. Second order homogeneous equation. Solve y second, which is the second derivative of y, minus 3y prime plus 2y is equal to 0. Now, this one looks a little bit like a second order polynomial equation. Let's see how we solve it. You simply replace y with, for y second derivative, r square minus 3 for y prime, that would become 3r, plus 2 is equal to 0, and you solve it just like any polynomial second order equation. So, in order to solve it, okay, we can use this method. The discriminant delta is equal to, okay, this is of the form ar square plus br plus c is equal to 0. Delta is equal to b square minus 4ac equal 9 minus 8 minus 4ac, which is equal to 1. The first root r1 is equal to minus b minus square root of delta over 2a, which is 3 minus 1 over 2 equal 1. Second root is equal to minus b plus square root of delta over 2a. So 4 over 2 equal 2. Thus the roots are r1 equal 1 and r2 equal 2. Therefore, the general solution is given by y equals c1 e r1 x plus c2 e, or exponential, r2 x, with r1 equal 1 and r2 equal 2. So y equal c1 ex plus c2 e2x. That's the general solution of the equation. Repeated roots. Solve y second minus 2y prime plus y equal 0. Going to the same characteristic equation, so it is r squared minus 2r plus 1 equals 0, which is r minus 1 squared, by the way. You can use the delta method, but it's clear here that it is r minus 1 squared. We have a repeated root, which is a double root of r equal 1. Hence, in such case, the general solution is simply y equal c1 plus c2x times erx equals c1 plus c2x ex, with r equal 1. Complex roots, where the discriminant in such case would be less than 0. So for instance, if we flip this equation to the characteristic one, you get r squared plus 1 is equal to 0, because y prime is not available. So r squared is equal to minus 1. It has no solutions in r, hence you flip minus 1 with I squared, the complex characteristic value. So r squared is equal to I squared, hence r is equal to plus minus I. Since you're getting a complex number, it has both real and imaginary parts. Okay, the real part is 0 here, because you have 0 plus minus 1i. The imaginary part is beta is equal to 1. Okay, so real and imaginary parts are designated respectively as alpha and beta. The general solution in such case is given by y is equal to e alpha x multiplied by c1 cosine beta x plus c2 sine beta x, with beta equal 1 and alpha equal 0. And we explained why, because here for the root we have no real parts, the real value is 0, and the imaginary value is 1, the part multiplying I. So you plug them into this equation. E alpha x with alpha equals 0 is E0, which is 1. So y is equal to c1 cosine beta x, beta is equal to 1, plus c2 sine beta x. Non-homogeneous equation. Solve y second minus y is equal to ex. First, we solve the homogeneous equation by considering the right side of this equation as 0. So y second minus y is equal to 0. We can flip it into the characteristic equation as usual, and we get r squared minus 1 is equal to 0. So r is equal to the square root of 1 equal plus minus 1. Two distinct roots. The homogeneous solution, as we know in such case, is given by y equals c1 e r1x plus c2 e r2x, where r1 and r2 are the distinct roots. So yh is equal to c1 e x, because r1 is equal to 1, plus c2 e minus x. Since ex already appears in the homogeneous solution, so let's try a particular solution. At first, yh is equal to c1 ex plus c2 e minus x. Okay, so trying a particular solution, yp is equal to ax ex. Let's get the derivative. So y prime is equal to a times 1 ex plus, okay, u prime v plus u v prime plus ex. Okay, second derivative gives us a times ex plus ex, the derivative of the second, because ex doesn't change, which is a times 2ex plus ex. Then we substitute y second and yp in the original equation. So y second is equal to 2aex plus axex, what we found earlier by deriving the particular solution, and yp, which is the particular solution, is equal to axex. So it is y second minus yp. This cancel out. We end up with 2aex. Then you place it equal to ex, hence you get 2a equal 1 and a equal 1/2. And this, you place it back as an addition to the homogeneous solution. So y is equal to c1 ex plus c2 e minus x, which is yh, by the way, plus the particular solution yp given by a xex with a equal to 1/2. Clear? So again, y is equal to yh, the homogeneous solution, plus axex, the particular solution, with a being solved as 1/2 by replacement of y second and y with their values as we derived the particular solution. This is how we got the value of a. Laplace transform. Find L of t squared. Here we refer to a table of transforms. This is how we can find these things out. For the Laplace transform of t squared, the formula is L of t to the power of n is equal to n factorial divided by s to the power of n plus 1. Now n is equal to, therefore the Laplace transform of t squared is given by n factorial, or 2 factorial, divided by s to the power of 2 plus 1, which is s to the power of 3. Hence, LT squared is 2/s3. Find the inverse Laplace transform of 1/s minus 3. Now, remember, and again, you can look up the table for this transformation, but in general, the inverse Laplace transformation, or Laplace transformation of E alpha t is equal to 1/s minus alpha. So this should give us, if I'm not mistaken, with alpha equal 3, E 3t. That should be the inverse Laplace transform. Let's check it out. So L E alpha t is equal to 1/s minus alpha. Hence, L minus 1 of 1 over S minus 3 equal E3t, which is correct. System of differential equations. Solve the system dx over dt equal x and dy over dt equal minus y. At first, the equations are independent. The first one is dx over dt equal x. It gives a solution x equals c1 et. Second, dy over dt equal minus y gives y equals c2 e minus t. Therefore, x and y are respectively c1 et and c2 e minus t. State Laplace's equation in 2 dimensions. So it is given by uxx plus uyy equals 0. Functions satisfying this equation are called harmonic functions. Hence, uxx plus uyy is equal to 0. Use the separation of variables to solve dy over dx is equal to ky. You multiply y beneath dy, and dx you move it to the upper side on the right of to the right of the equality. We end up with dy over y is equal to k dx. Integrate both sides, so integral 1 over y dy is equal to integral k dx, straightforward, which gives us ln y in absolute value is equal to kx plus c. Hence, y is equal to c e kx. Why? Because you elevate both sides to the exponential equal e kx plus c. So y is equal to e kx plus c, or e kx times ec. Okay, here ec you can rename it as capital C or A. That is the constant. So finally, differential equations covered: first order differential equations, separation of variables, exact and linear equations, second order homogeneous and non-homogeneous equations, characteristic equations, Laplace transforms, and systems of differential equations without heat, wave, and actually Laplace, yes, but without heat and wave equations. Differential equations from the mathematical foundation of physics, engineering, biology, economics serve like a big purpose for signal processing, fluid mechanics, quantum mechanics, and dynamical systems theory. At the end, thank you so much for watching, and I hope you enjoyed this lecture. Bye bye. See you next time.